Hey everyone, welcome to this course on application security. My name is Derek Fisher and I'm happy to be able to walk you through application security and security in the software development lifecycle. We're going to cover a lot of different topics in this class, so we're going to be talking about analysis tools, threat modeling, vulnerability management, risk assessments, the OWASP top 10, SANS 25, and everything in between. So we're going to cover a lot of ground in this. I hope you find the information in this course valuable, and I look forward to presenting these topics to you. So, just a little bit about myself. I have 20 plus years experience in engineering, both on the hardware side and software side. The past 8-9 years I've been in the security space, both as a leader, as an instructor, as an architect. So I have a bit of experience in this space. If you want to look me up on LinkedIn, I'd be happy to connect with you, so feel free to look me up. And with that, let's get into the software development lifecycle. So we're going to lay some groundwork for what actually the software development lifecycle is and how security plays into that. So when we look at the SDLC, or the software development lifecycle, there's several different ways that this cycle works. And you'll see some variations on this, but generally you have these concepts. So you have a requirements phase or analysis phase. You have a design phase, a development phase, or an implementation phase, a testing phase, and then an operations or evolution phase. So in that requirements phase, you're really gathering up all the requirements from the client of what it is that they want to build. So if you're building a website, the client's going to provide you with the information of what it is that they want. Then you're going to go into the design phase where you're going to start picking different technology stacks that you're going to work with. You're going to make some architectural decisions. And then the implementation phase, well, that's the fun phase. That's where you're actually writing code. Once the code is written, you go into a testing phase, and that's where you take your code that you produce and you run it through some tests to make sure that it actually, number one, works, and then it meets the client's what the client wanted. And you may layer in some security testing there as well. And then in that evolution phase, and the operation phase is once you push that code out into a production environment, you're going to have some monitoring going on and making sure that, number one, there's no defects that are found in production, and that any issues that come up are then fed back into your requirements phase, or the pre-design phase, where you're taking that the bugs or the defects that are found in production, and you're putting it back through that life cycle again, where you're going through some design work, you're doing some development work, you're going through some testing, and then you push out to production. So from that initial requirements phase, a little bit deeper dive here, you're getting those, again, requirements and goals from the client. You're taking those requirements, you're doing some analysis. So you're making sure, do you understand what those requirements are? And then you want to have an agreement with the client to make sure that what it is that they're saying in the requirements, or what they want is being captured appropriately in the requirements. Now, the important thing is that the client knows what they want, but they don't know how. So your job is to figure out how that gets done. The client just wants to tell you what it is that they want to have done. And then you want to make sure that the scope is agreed upon between you and the client. So you're going to look at the scope of or the requirements, make sure that the boundaries and the scope of that end product is going to meet both the client's needs and also make sure that you can actually achieve those. So the scope is defined, agreed upon. And then internally, you're going to take those requirements. You're going to prioritize the requirements and say, maybe if you have just a simple example, maybe you have 15 requirements and you're going to, the top 5 or 5 of them are critical ones that the client can't, negotiate on. And then maybe a handful of them are less of a priority, and then some of them are nice to have. So you want to then prioritize, well, obviously the ones that the client wants the most, those are going to get the most amount of attention. Then you're going to slot your resources and make sure that you have the appropriate amount of developers and architects and testers associated with making sure that the work actually gets done. So then during the design phase, this is where you're going to start looking at maybe making some wireframes. You're going to do some screen layouts. You might even do some prototype work that you allow the client to take a look at and make sure that they agree that you're heading in the right direction. And at that point, you might be able to make some changes if the client finds issues with it. You're also going to detail some of the design decisions that you're making, whether it's from the architecture point of view or the technology point of view. You want to make sure that you document that information during that design phase. But this is really where you're laying the framework for what it is that you're going to develop. And then the fun part, you're going to take all that information that you got from the requirements phase and from the design phase, And this is where you sit down and you write code. So you take all the input in from those first two phases, and then you create some code that hopefully works. But if it doesn't work, then you go into the testing phase, and this is where you're going to start identifying any of the issues where maybe the code is having some issues with running, or maybe the code that you wrote doesn't work in the overall system. So this isn't all-encompassing, but there are several different ways of testing code. So you have the static analysis, which is just looking at the code as it sits. So it's not running code, it's just looking at the text of the code. And it's looking for things like code quality. You may have it configured to look for security issues. And then there's also dynamic analysis, which is actually looking at the code while it's running. And we're going to get more into these things as we talk about some of the security analysis tools that are available. But some of you that may be developers may be familiar with some of these other concepts around testing. So unit testing is looking at very small code changes. So it could be in a function or a method. It's going to look at those. The unit test is going to be the smallest, method of testing. And then you have integration, interface, and systems tests, which gets more and more broad in terms of what it covers from a testing perspective. The system test is looking at the code that you just changed. What is the impact of that code across the entire system? So that could be not just in the application that you're working in, but also across all the touch points that application has. So then when you get into the operation phase, you're going to hopefully have monitoring out there that determines whether defects are found, and if they are found, that you have a way of taking those defects in and making sure that that you have a way of bringing them back into the design phase. You're going to create a patch, you're going to build your software, put it back through the testing, then push it out to production. So it's really a method of understanding if there's defects out there, how do we get that back into our development process and get a fix pushed out to production. So from a security point of view, and this is really what we're going to talk about in the rest of this class, is the Secure SDLC fits nicely into the regular software development lifecycle, where from that design perspective and requirements perspective, you're looking at the security frameworks that already exist. You're looking at the standards and guidelines that are already out there. So things like OWASP and NIST, we're going to talk a lot about those throughout this course, and we're going to weave in a lot of their standards and guidelines into this course. And then in the design phase, you're going to look at things like threat modeling. Again, we're going to cover threat modeling in this course as well. But that's where you're identifying the different threats that you may have that are applicable to your system or your application that you're building. And then in the testing phase, not just static analysis and dynamic analysis, but we're going to also talk about interactive testing. We're going to talk about some of the other tools that aren't necessarily testing tools, but are protection tools like runtime security protection, WAFs, and so forth. And then in that evolution or operation stage, we're going to talk about some of the vulnerability management techniques that can be used, and also risk rating. So getting a vulnerability in from perhaps a external party, you want to be able to take that vulnerability information and put it in the context of your application and build a risk rating around that. So is this really, the vulnerability that you get from a third party, is that really something that we need to, is there really something actionable there? You don't know that until you do a risk rating on it. So again, we're going to talk about all these concepts and more throughout this class. So thank you for joining me in this lesson, and I look forward to seeing you in the next one. Hey everyone, welcome to this course on application security. My name is Derek Fisher, and I'm happy to be able to walk you through application security and security in the software development lifecycle. We're going to cover a lot of different topics in this class, so we're going to be talking about analysis tools, threat modeling, vulnerability management, risk assessments, the OWASP Top 10, SANS 25, and everything in between. So we're going to cover a lot of ground in this. I hope you find the information in this course valuable, and I look forward to presenting these topics to you. So just a little bit about myself. I have 20 plus years experience in engineering, both on the hardware side and software side. The past 8-9 years I've been in the security space, both as a leader, as an instructor, as an architect. So I have a bit of experience in this space. If you want to look me up on LinkedIn, I'd be happy to connect with you, so feel free to look me up. And with that, let's get into the software development lifecycle. So we're going to lay some groundwork for what actually the software development lifecycle is and how security plays into that. So when we look at the SDLC, or the software development lifecycle, there's several different ways that this cycle works. And you'll see some variations on this, but generally you have these concepts. So you have a requirements phase, or analysis phase. You have a design phase, a development phase, or an implementation phase, a testing phase, and then an operations or evolution phase. So in that requirements phase, you're really gathering up all the requirements from the client of what it is that they want to build. So if you're building a website, the client's going to provide you with the information of what it is that they want. Then you're going to go into the design phase, where you're going to start picking different technology stacks that you're going to work with. You're going to make some architectural decisions. And then the implementation phase, well, that's the fun phase. That's where you're actually writing code. Once the code is written, you go into a testing phase, and that's where you take your code that you produce and you run it through some tests to make sure that it actually, number one, works, and that it meets the client's what the client wanted. And you may layer in some security testing there as well. And then in that evolution phase, and the operation phase is once you push that code out into a production environment, you're going to have some monitoring going on and making sure that, number one, there's no defects that are found in production, and that any issues that come up are then fed back into your requirements phase, or the pre-design phase, where you're taking that the bugs or the defects that are found in production, and you're putting it back through that life cycle again, where you're going through some design work, you're doing some development work, you're going through some testing, and then you push out to production. So from that initial requirements phase, a little bit deeper dive here, you're getting those, again, requirements and goals from the client. You're taking those requirements, you're doing some analysis. So you're making sure, do you understand what those requirements are? And then you want to have an agreement with the client to make sure that what it is that they're saying in the requirements, or what they want is being captured appropriately in the requirements. Now, the important thing is that the client knows what they want, but they don't know how. So your job is to figure out how that gets done. The client just wants to tell you what it is that they want to have done. And then you want to make sure that the scope is agreed upon between you and the client. So you're going to look at the scope of the requirements, make sure that the boundaries and the scope of that end product is going to meet both the client's needs, and also make sure that you can actually achieve those. So the scope is defined, agreed upon. And then internally, you're going to take those requirements. You're going to prioritize the requirements and say, maybe if you have, just a simple example, maybe you have 15 requirements, and you're going to, the top 5 or 5 of them are critical ones that the client can't, negotiate on. And then maybe a handful of them are less of a priority, and then some of them are nice to have. So you want to then prioritize, well, obviously the ones that the client wants the most, those are going to get the most amount of attention. Then you're going to slot your resources and make sure that you have the appropriate amount of developers and architects and testers associated with making sure that the work actually gets done. So then during the design phase, this is where you're going to start looking at maybe making some wireframes. You're going to do some screen layouts. You might even do some prototype work that you allow the client to take a look at and make sure that they agree that you're heading in the right direction. And at that point, you might be able to make some changes if the client finds issues with it. You're also going to detail some of the design decisions that you're making, whether it's from the architecture point of view or the technology point of view. You want to make sure that you document that information during that design phase. But this is really where you're laying the framework for what it is that you're going to develop. And then the fun part, you're going to take all that information that you got from the requirements phase and from the design phase, and this is where you sit down and you write code. So you take all the input in from those first 2 phases, and then you create some code that hopefully works. But if it doesn't work, then you go into the testing phase, and this is where you're going to start identifying any of the issues where maybe the code is having some issues with running, or maybe the code that you wrote doesn't work in the overall system. So this isn't all encompassing, but there are several different ways of testing code. So you have the static analysis, which is just looking at the code as it sits. So it's not running code, it's just looking at the text of the code. And it's looking for things like code quality. You may have it configured to look for security issues. And then there's also dynamic analysis, which is actually looking at the code while it's running. And we're going to get more into these things as we talk about some of the security analysis tools that are available. But some of you that may be developers may be familiar with some of these other concepts around testing. So unit testing is looking at very small code changes. So it could be in a function or a method. It's going to look at those. The unit test is going to be the smallest, method of testing, and then you have integration, interface, and systems tests, which gets more and more broad in terms of what it covers from a testing perspective. The system test is looking at the code that you just changed. What is the impact of that code across the entire system? So that could be not just in the application that you're working in, but also across all the touch points that that application has. So then when you get into the operation phase, you're going to hopefully have monitoring out there that determines whether defects are found, and if they are found, that you have a way of taking those defects in and making sure that that you have a way of bringing them in back into the design phase. You're going to create a patch, you're going to build your software, put it back through the testing, then push it out to production. So it's really a method of understanding if there's defects out there, how do we get that back into our development process and get a fix pushed out to production. So from a security point of view, and this is really what we're going to talk about in the rest of this class, is the Secure SDLC fits nicely into the regular software development lifecycle, where from that design perspective and requirements perspective, you're looking at the security frameworks that already exist. You're looking at the standards and guidelines that are already out there. So things like OWASP and NIST, we're going to talk a lot about those throughout this course, and we're going to weave in a lot of their standards and guidelines into this course. And then in the design phase, you're going to look at things like threat modeling. Again, we're going to cover threat modeling in this course as well. But that's where you're identifying the different threats that you may have that are applicable to your system or your application that you're building. And then in the testing phase, not just static analysis and dynamic analysis, but we're going to also talk about interactive testing. We're going to talk about some of the other tools that aren't necessarily testing tools, but are protection tools like runtime security protection, WAFs, and so forth. And then in that evolution or operation stage, we're going to talk about some of the vulnerability management techniques that can be used, and also risk rating. So getting a vulnerability in from perhaps a external party, you want to be able to take that vulnerability information and put it in the context of your application and build a risk rating around that. So is this really, the vulnerability that you get from a third party, is that really something that we need to, is there really something actionable there? You don't know that until you do a risk rating on it. So again, we're going to talk about all these concepts and more throughout this class. So thank you for joining me in this lesson, and I look forward to seeing you in the next one. Hey everyone, welcome back. And in this lesson, we're going to be talking about some of the definitions within security. So the simple definition and textbook definition of security can be shown here, and we'll just read through them. So security is a state of being protected or safe from harm. It's also things done to make people or places safe. And then you can also think of it as an area. So places like an airport where there's a section that's dedicated to security. So this is kind of the textbook definition of what security is, but we're more interested in, for our purposes, what security is in the software development lifecycle and also from a cybersecurity perspective. So security is anything you do to protect an asset that is vulnerable to some attack, failure, or error. Now, some of these terms are underlined for a specific reason because we're going to walk through them here in a second. So an asset is anything that you deem to have value. And an asset can be valuable because it holds value. It can be valuable because it produces value, or it could be valuable because it provides access to value. So what does that mean? So an asset that holds value could be something, and I want you to think about this as well, an asset that you have that may hold value, right? So that could be something like a precious metal, gold, silver, whatever. Or it could be your car, because it holds value. It has some, you could sell it and you could not, obviously your car, it depreciates pretty quickly, but it does hold value. So you could think of the holding value as something that in and of itself is valuable. An asset can be valuable because it produces value. So if you think about factories or places like that where the machinery is producing goods that are then sold for currency. So those machines are producing value. So those machines in turn are valuable because the things they produce are then sold and produces revenue. So an asset can also be valuable because it provides access to value. So this one's a little bit trickier, but think about it. Your debit card, you go to the machine to get. We used to call them Mac machines in the Northeast of the United States. They're called ATMs in reality. So, but you go to the ATM, you put your card in there, and you put in your PIN to get access to your account to withdraw money. So that PIN number provides access to value. Your Social Security number does the same thing. Your username and password can do that as well in the sense of logging into your banking account online. So those are the different ways that an asset can hold value, it can produce value, or it can provide access to value. So vulnerability is any weakness in an asset that makes it susceptible to attack or failure. Okay? And an attack is an intentional action that can reduce the value of an asset. So if you think about your vehicle, like I said, your car, if for some reason somebody decides that they're going to bash it up, or cause some kind of damage to your car, well, that's going to reduce the value of your asset there, your vehicle, right? So they may do several $100s worth of damage to the car, and therefore it's no longer worth as much as it was. Okay, so that's an intention. That attack is an intentional action that has reduced the value of your asset, in this case, your vehicle. A failure or an error is an unintentional action that can reduce the value of the asset. So we talked about providing or assets that can produce value. So think of the machines that produce some kind of widget or something that is being sold. Well, if something happens to that machine, and maybe it's some kind of a hardware failure or user error or something to that effect that takes that machine offline and it's no longer producing whatever goods you're trying to produce with that machine, well, that's just reduced the value of that asset. That machine's no longer running. You've lost revenue because it's not producing. And it wasn't an intentional attack there. It was a failure or an error that produced that was an action that reduced the value of that asset. So attacks, failures, and errors are actions that we collectively refer to as threats. So therefore, security is anything you do to protect an asset that is vulnerable to some threat. All right, so that is the purpose of this course and what we're going to be talking about in terms of the secure SDLC. But we're going to talk about how do we protect our assets that could be vulnerable, and vulnerabilities can come in many different shapes and forms, and we're going to talk about those. But the whole point is to make sure that those vulnerabilities can't be exploited by some threat. So we're going to talk about security goals as well. Cybersecurity can be understood as a set of goals, and we're going to talk about defense in depth and things like that as we go on. But these goals are defined by how we measure an asset's value. All right, so that's the important part. We don't, there's a silly picture here of a peanut butter and jelly sandwich in a safe. You're not going to buy a $500 safe to put your peanut butter and jelly sandwich in to protect it. Same thing with a car, like we gave the example earlier. If your car is only worth $500, you're not going to go out and buy a $10,000 security system to protect that vehicle. So we really want to understand what is the asset's actual value, and then we want to appropriately allocate security to meet that asset's value. So when we're looking at the total picture here, we want to know number one, what assets we want to protect, and this is actually a very difficult part of, especially around development security, is knowing where your assets are, whether they need to be protected. If you're in development, you already know this, that information and data that's in a database is, it's in the database, but it can be called by a lot of different functions and pulled in a lot of different ways. So understanding where your assets are and who's using them is a very important part of being able to protect it. So understand how the asset works and interacts with other things. Like I mentioned, you may have an application that has APIs that are called by a lot of different endpoints. You want to know who's calling that, how are they using that data, because again, those are your assets, whether it's the data or whether it's the system that you're running. And then you want to determine how your assets value can be reduced indirectly or directly. And again, we're going to talk a lot about this when we get into threat modeling and risk assessments and things like that. But you really want to think about what can go wrong. Is there a very common concept around development outside of the security scope is high availability. And the reason why we architect systems with high availability is so that when maybe one server goes down, there's other servers that are waiting to pick up the slack. So that's a very common way of protecting an asset from something like being out of commission or unavailable. So once you understand the asset's value and how it can be reduced, whether it's indirectly or directly, through an attack, or whether it's through an error or failure, then you want to start taking steps to mitigate that. So how do we put guardrails around that to make sure that that the vulnerabilities that may be inherent within our system can't be taken advantage of by a threat? All right. So thank you for joining me in this lesson. Look forward to seeing you in the next. Welcome back, everyone. In this lesson, we're going to talk about cybersecurity specific goals. So when we talk about issues in the cyberspace or digital space compared to the physical world, obviously things are different. So we want to make sure that we're addressing the issues in cybersecurity appropriately. So when we look at the digital space or cyberspace, we're looking at the assets. A hard drive is going to be the security that you put around a hard drive is going to be different than the security you put around your home, right? Obviously. So when we think about the assets that we're trying to protect in the digital space, we want to make sure we take those into consideration when we're creating security goals to protect those assets. So if you take nothing else away from this class, make sure you understand the concept of CIA. And we're going to talk about these here in a minute. But again, CIA is basically the bedrock or the foundation for everything in security. So confidentiality, integrity, and availability. Those are the three concepts that basically everything in security boils down to. So again, if you take nothing else away from this course, make sure that you at least understand what confidentiality, integrity, and availability mean. So when we talk about confidentiality, we're talking about that information is only available to those that should have access. So the important part to remember there is the should have access. So in other words, data can be available in a database, but you want to make sure, depending on the type of data that's in there, if it's protected information, you want to make sure that not everybody has access to it, that it's reserved for only people that are properly authorized to view it. And in integrity, we're talking about data is known to be correct and trusted. So in other words, if I send information from one endpoint to another, I expect that what I sent from endpoint A is what was received at endpoint B. So that means that it wasn't tampered in transit. And for those that have downloaded software off of websites, you've probably seen the fingerprint or the hash or the checksum that is typically appended to that file. And the purpose of that is that you can make sure that that file hasn't been tampered with if you run it through your own checksum. And we're going to talk about that later on when we get into encryption. And the last one, availability, is information is available for use by a legitimate user when it's needed. So if I go to google.com, or if I punch in google.com into a browser, I expect google.com to load. If it doesn't, then that's an availability issue. Also, maybe a server is down or something like that. That's an availability issue. So when you think of something that should be up and isn't up and running, that's an availability issue. So when we protect something that provides access to value, we're maintaining its confidentiality. So you can think of the example that we gave before with you go to an ATM with your debit card and you put in your PIN code to get access to your bank account and withdraw money. Well, that PIN code is supposed to stay confidential. So same thing with when you go to your bank account online. Your username and password, that should be confidential as well, because you don't want anybody to have that information in order to access your ATM, your checking account, or so forth. So when we protect something that holds value, we're maintaining its integrity. So there was a good example of this way back in 1982 with the Tylenol murders. It happened in Chicago, Illinois in the United States, where way back, again, this is in the 80s, the Tylenol, it's a medication that you can take for headaches and things like that. They didn't used to have a seal on it. So basically somebody was able to tamper with the bottles and put cyanide inside of it. So there were a couple people that were killed due to the fact that there was the Tylenol bottles were tampered with, and so since then Tylenol had put in place those seals around around their bottles, and you see a lot of other medications doing the same thing. But that's basically a case of where the integrity of the product was compromised because someone was able to basically manipulate the capsules that were inside, and obviously that's not a good thing. So when we protect something that holds value, again, in this case it was the Tylenol is a product that's produced that people purchase, so therefore it holds value, then we're maintaining the integrity of it. So when we talk about protecting something that produces value, we're maintaining its availability. So again, the example of Google being up when I want it, maybe that's not that big of a deal. If Google's down for a little bit, a lot of people may be upset about that, but Google's probably losing money off of it, but we're not. But for instance, there's a lot of stories around betting, like gambling sites that will be extorted basically before a big fight or a big race, where they know that there's going to be a lot of bets placed. Typically, somebody that's out to try to get money out of that site will send them a note saying, "Hey, if you don't pay us X amount of money, we're going to bring your site down during the big fight, and therefore you're not going to be able to be online, and you're basically out of commission at that point." So when we provide protection for that against something like a DDoS type of attack against a site that we need to be up at a certain time, and you can think of Amazon, not going down the gambling site, but think of Amazon. If Amazon was offline for a couple hours, that's a lot of money. That represents a lot of money for Amazon that's lost. So they do a lot of they take a lot of pains to make sure that their site is up and running when it's needed, because that when it's down, that's a loss of revenue. So what about a real world example? So let's talk a little bit about a rocket. So launching a rocket into space. So when we talk about launching a rocket into space, we want to talk about the CIA, the confidentiality, integrity, and availability of that rocket, and making sure that it gets out into space. So the different type of assets that we may have for a rocket, we can talk through some of these things, but from a high level, you have the crew, you have the rocket itself, you have the food, the fuel, the cargo that it's sending to wherever it's going. Maybe it's a satellite, maybe it's supplies that are going to the International Space Station, and so forth. So those are all the different types of assets that are part of that rocket. And then when you think about the vulnerabilities, well, you have problems with maybe the heat shield in re-entry. Maybe there's some faulty equipment, a thin hull, in terms of the structure of the rocket itself. You can kind of go through again some of the vulnerabilities that may impact a rocket, especially when it comes to launching it into space. And what are some of the threats? Well, space debris, the atmosphere itself, maybe some error from ground control or the people that are monitoring the launch. So again, these are the different the assets, the vulnerabilities, and the threats that may impact a rocket. So how will we secure something like that? Well, it comes down to how do we secure the assets? Again, we have the rocket, we have the fuel, we have the food, we have all those different components that are part of it. We want to make sure that if it's the crew, we want to have the proper safety considerations for the crew. If it's the heat shield, maybe we want to make sure that we do some tests on the heat shield and make sure make sure that it's going to survive re-entry and things like that. From a vulnerability perspective, if you have space debris as a concern, then maybe and I'm not a rocket scientist, so you have to bear with me here. But from a space debris perspective, we want to make sure that we have the right detection in place to make sure that the rocket's not going to be blindsided by space debris as it comes through. And even from an attack perspective, what are we trying to do from maybe another space agency is trying to perhaps steal data or perhaps steal information, or just even not even steal, but just trying to get information about the mission itself. That could be information that we want to maintain the confidentiality of. So how do we make sure that we protect the information that perhaps is very important to the mission, and we don't necessarily want to be in the hands of other space agencies? So we would do things like provide encryption, make sure the communication channels are properly secured, and things like that. So that's kind of a simple, silly example of protecting a rocket, in a real world example. But obviously, when we get into the cyberspace, it's a little bit different. So we want to make sure we have well-defined goals and security mechanisms, but some mechanisms are better because they fit security principles. And we're going to talk about the security principles here in a second. So security principles, and these are just basically the framework for selecting, designing mechanisms. So it's basically the groundwork that we, similar to what CIA is, in the sense of this is what security kind of boils down to. Security principles are the things that have generally been in place for decades, really, that help us design better systems. So as I said, a lot of this has been in place for decades. We're going to talk about the protection of information in computer systems that was developed by Salzer and Schroeder. I think this is back in 1972 or something like that. It was the early 70s. So I point that out because although these are 40, 50 years old, these concepts are still very relevant today in the security space. So when we talk about economy and mechanism, we want to make sure that we're keeping things simple. Complexity is the enemy of security. So in other words, the more complex your system is, the more difficult it is to secure. And especially in today's development environment, where you have containers, you have cloud, you have DevOps, and you have a lot of different third-party libraries being pulled in. It's very difficult to secure that type of landscape because it's a very complex landscape. So economy and mechanism means, keep it simple, make sure that the stuff that you're building can be easily understood in a short period of time. Fail-safe defaults means that, if a system fails, you want to make sure that it fails to a default state that is safe and secure. So in other words, if your authentication, just take an example here, if your authentication to your website fails, you don't want it to allow someone to just basically log in as admin, right? You want it to fail, meaning that it will respond saying, hey, I'm sorry, you don't have access to this site right now, because that's more safe and secure than allowing that person to just log in without being authenticated. Complete mediation just means to check every resource for to make sure that every time there's a call to a function or to a service, that you're verifying that the user has access to that information that they're trying to access. So in other words, you want to make sure that every single call to a resource is being verified for authorization and authentication. Open design just basically means that there's no security through obscurity, and we're going to talk about that later on. But the example I like to give with security through obscurity is that I don't do this, and I don't know too many people that do this, but there is the concept of hiding your house key underneath of a rock outside of your house. In case you get locked out. So your house key could be sitting right outside the front door underneath of a rock, and sure, general passerbys aren't going to see that your key's there, but that's not really security, because you hid it underneath of a rock doesn't mean that that's secure. A lot of people are obviously wise to that people hide their house keys underneath rocks or in mailboxes or wherever they put them. So again, hiding something doesn't make it secure. So that's what open design means. Separation of privilege really means that you want to make sure that for critical workflows, that you don't have a single person or a single account or single user that is able to initiate like a high, a critical type of workflow. So the example we like to give on this is that to launch a nuclear missile, you need two people to turn keys at the same time. In other words, not one person can launch a nuclear missile on their own. So again, hopefully with your applications, you're not managing nuclear missiles, but you can think of cases in the financial space where perhaps you don't want people, the ones that are able to change the address on an account are not the same people that can issue like a checkbook. So you want to make sure that for those kind of high value type of workflows that there's a separation of privilege. Keeping kind of with that theme, you want to have least privilege is another concept that's stayed with us for a very long time. And least privileges basically means that you should only have the rights to a system that allow you to do your work or your job, and no more. So in other words, in order for me to access a certain system, like for instance Amazon, let's say I'm going to Amazon.com, I don't need admin privileges to access Amazon.com in order to go shopping on Amazon.com. I only need general user access. From Amazon's perspective, they're not going to give everyone admin credentials or an admin account to access Amazon. So the point of least privilege is only provide the access to an end user that they need to do their job. Least common mechanism just basically comes down to, and I don't always agree with this, but this is maybe one of those things that hasn't aged well. But least common mechanism just basically means stay away from shared components. And I think in reality, like you're seeing security more or less coalesce around let's have shared components, because instead of having to fix something in multiple different places that are being used differently in every different location, have one central location where, like, let's say it's a library or something like that can be updated. If there's an issue with that library, you can update it rather quickly as opposed to trying to fix it in multiple different locations. Psychological acceptability just means basically that you want to make security usable enough that somebody's not going to try to circumvent it. So if you make security difficult, it's going to make end users try to figure out ways around it because it's so difficult. So we want to make sure that security is approachable, something easy that everybody can do, and not something that requires a degree to figure out. Work factor, and we're going to get into this when we talk about more about encryption, but work factor just basically means you want to make sure that the effort that somebody has to put into breaking your security should be higher than the asset that they're trying to get. So, earlier on in one of the lessons we gave the example of, putting a peanut butter and jelly sandwich inside of a $500 safe. Well, you want to make sure that, if the peanut butter and jelly sandwich is worth $3, you want to make sure that the person that needs to break into that safe needs to buy $15 worth of tools or something, something obviously higher than the value of the asset they're trying to get to. And then compromised recording just basically means audit everything. So you want to make sure that you have information on all your workflows, where data is going, who's accessing what. That's basically audit everything is a simple way to think about it. So the pyramid. So at the top, our goal is to get the CIA to make sure that we're maintaining the confidentiality, the integrity, and availability of systems and assets. And the principles are the principles that I just walked through here. So all the ones that we just talked about: economy and mechanisms, fail-safe, least common mechanism, psychological acceptability, and so forth. And then the bottom of this pyramid here is really the mechanisms that that we're building those principles, or we're building off of those principles to get us to our goal of CIA. And that's really what this course is about. We're going to talk about a lot of that throughout this course. So thank you for sticking with this, and thank you for joining me in this lesson. And I look forward to seeing you in the next one. Hey everyone, welcome back. And in this lesson, we're going to go over WebGoat. So WebGoat is from OWASP. And if you go to owasp.org or just do a search in your favorite search tool like Google or Bing, if you use that, and do a search for OWASP WebGoat, it's going to bring you to the OWASP page, which is going to show you some information on WebGoat and also some options for download. Now, there's two ways that you can do this. You can do it through a Docker image, or you can do it as a standalone jar. What I found simpler is downloading the jar and running it as basically just as a command java-jar with the jar file. You do need to have a Java runtime and the JDK installed, but it's pretty cut and dry to be able to fire this up. Now, I am doing this in Ubuntu, so Linux distribution for those that aren't familiar. I find that it's much simpler to do it this way, but obviously you need to have the Linux distribution running somewhere. I have this running in a virtual machine. So again, mileage may vary depending on how you want to run this, but there's plenty of, there's a lot of different flavors and ways to do this, so I'm not going to walk through all of them. But just giving you my experience here, what I find is easier is to run this as a Linux distribution, download the jar file, and run it that way. So again, if you go to OWASP, you're going to get a lot of different information regarding WebGoat, but the bottom line is that WebGoat is a purposely insecure web application where you are able to perform different types of attacks, a lot of the ones we're going to talk about in this class. So once the script is done, the jar file is running. If you just go to localhost, port 8080, context root is WebGoat. You will have to create an account, which I've done already in advance. Creating an account isn't an online type of thing. It's a local account just for you to run WebGoat. So I already created my account, Mr. Robot. I'm going to go ahead and sign in. And what you're going to see here is a bunch of different lessons here on the left-hand side. And there's obviously injection, broken authentication, sensitive data exposure, cross-site scripting, insecure deserialization, all of these that we've talked about with the OWASP top 10. So we're going to start out just as a sample here. I just want to walk through a little bit here with SQL injection. And again, the goal here is to provide a bit of a lesson, not just on SQL injection, but SQL in general. So it's going to give you some information here around SQL, what structured query language is, which is SQL. Hopefully you're familiar with that. And then you can start kind of working your way through this lesson. So you can see that there's 12 different steps here. We're not going to go through each one of these, but the types of or the information in this lesson is going to be driven by this employees table, which you see here mocked up. And so in the first, and this is meant to be interactive, so in the first step here, they want you to try out your SQL chops here. So it says, look at the example table, try to retrieve the department of the employee Bob Franco. And so for those of us that are familiar with SQL, although it's been a while for me, it's a select star from employee or employees, right? Where last name, name, right, equals Franco. Hopefully I got that right. And okay, good. So I still remember my SQL, so that's good. All right, so it says here, we were successful, and we can go ahead and go to the next lesson. So here it says we're still working on the employee table. It says try to change the department of Toby Barnett to sales. So again, we're going to draw on some SQL foo here. Update employees, set department to sales, where last name, we're going to stick with the last name, keep it simple, equals Barnett. And again, hopefully I got that right. Okay, good. So we were able to update it, okay? So we can see that we have that option. And we're not going to go through the rest of these, but basically we'll walk you through the different data definition languages, control language, and so forth. But we want to get to the juicy stuff here. So with SQL injection, it's going to give you some examples here of what SQL injection is, how it works, and we're going to go over some of these things too as well, obviously in the class. But this is just to give you some opportunity for you to learn these things on your own. But so you see here an example of SQL injection. Select star from users where name equals username. This is how you would append maybe user input. Maybe you're pulling this out of your web application on a request, and you plug that in to a SQL statement. And in most cases, what you would expect is that somebody's going to put Smith as a name. But if I'm an attacker, here it says, if an attacker supplies an attacker supplies an unexpected input which could be part of a SQL query, the query itself can be modified in that way, be used to perform other malicious actions on the database. So if I have, again, this input field and says select star from users where name is, it's basically the same thing as we saw up here. So here are some examples of what a hacker could supply to the input field to perform actions on the database that go further than just reading the data of a single user. So if I put in there Smith or 1 equals 1, for those that are paying attention here, 1 equals 1 will always work out to be true. So what this is basically saying is if I put in Smith or true, well, that's going to evaluate to always, that statement's going to evaluate to always being true. All right, so that's just a simple way of a very simple SQL injection. You can see some other options here where this is a way to comment out the remainder of a SQL statement. Here's a way to end a statement and start a new one that basically drops the tables. So you can see that basically when you are accepting user input and putting that into a concatenated SQL string, and not reviewing that input as it comes in, there's potential there for a malicious actor to change or influence the way the SQL statement works. All right, so this example here is just giving you kind of the overview of what SQL injection is and some possibilities. So some consequences of SQL injection, and again, we're going to talk about a lot of these throughout this class. But obviously we saw there some of the examples where dropping tables would be bad. Also being able to retrieve data that they shouldn't, that an attacker shouldn't be able to retrieve. All those things are potential SQL consequences. And again, we're going to talk about these throughout the class. Some of the severity issues related to SQL injection. All right, so let's actually try a SQL injection here. So what you see is gives us the query here. The query in the code builds a dynamic query as seen in the previous example. The query is built by concatenating strings, making it susceptible to string SQL injection. So you see the query here, select star from user data where first name is John and last name is some variable that we're going to enter in. So using the form below, we're going to try to retrieve all the users from the user table. So that's our goal here. So I think the first thing we're going to try to do here is manipulate this where we wanted to evaluate the true. So maybe this works. Okay, so that didn't work. But what we did get out of this is that it does show us that your query was select star from user data where first name is John and last name equals Smith or 1 equals 1. So because we added, so what we actually want to do here is I think we want to get rid of that first name look up here. So okay, so that worked. So here we got basically all the users from the database. And again, it's going to show our query here where it shows select star from user data where first name equals John and last name equals basically this ends here and states that that this portion of the query could be true or 1 equals 1, which is true. So it's saying that either this portion of the query here could evaluate to true or true. So in other words, based on this query, it's going to ignore this first name equals John and last name could be anything. So here it gives you better explanation where It works because one equals one always evaluates to true, which we know, and because we closed the first part of that query. So, I encourage you to play around with WebGoat. There's a lot of different content in here aside from SQL, injection. Like I mentioned, there's a lot of other opportunity for you to hear, and there's also additional injection attacks that you can try through this. So there's a lot of different goodies in here, and I strongly encourage you to work through this. And thank you for joining me in this lesson, and I look forward to seeing you in the next one. Thank you. Welcome back, everyone. In this lesson, we're going to go over the OWASP Top 10. OWASP stands for the Open Web Application Security Project. And Top 10 is their most mature project that they have out there, or at least probably the most well-known project that they have out there. And it's really just an accumulation of the top 10 most severe vulnerabilities that OWASP categorizes here. We're going to go through each one of these. The last version that they have out is 2017. They periodically, every few years, release a new version, so there may be one coming out soon. But right now, the most recent version is the 2017 version. So we're going to go into each one of these here. So starting with injection and broken authentication. So injection is really, just reading here, injection flaws such as SQL, NoSQL, OS, LDAP occur when untrusted data is sent to an interpreter as part of a command or query. So this is just basically input from a user into your web application that's not properly sanitized. We'll call it sanitization. And basically that means your application takes in input from an end user without properly making sure that it's secure and that it's not going to do something malicious to your application. So injection attacks can come in several different ways. SQL injection is probably the most common one or the most well-known one, but there is a lot of other different ways of performing injection attacks against web applications. Broken authentication, in the last lesson we talked about authentication and authorization. So broken authentication is obviously authentication that's not performing its role. So this just basically means that session management or authentication is not stopping unauthorized or unauthenticated there users from accessing the web application. So you can think of maybe somebody with lower credentials being able to get admin functionality, so like an elevation of privilege type of vulnerability. So that's broken authentication, when the web app's not properly keeping users from accessing things that they shouldn't be able to. Sensitive data exposure, this is pretty self-explanatory here, but basically it's the exposure of sensitive data. So you might have maybe credit card information or account information, social security numbers. Applications are going to have a lot of different content in it that can be lucrative to an attacker if they want to try to get to it. So sensitive data exposure is basically not securing whether it's your application, the APIs, the database, or configuration files, or anywhere where this information could be stored. Not properly providing protections around that leads to a sensitive data exposure. XML external entities. So this is, for those that are familiar with XML, this is just basically a way of getting XML to perform being able to access resources outside of the application. So just like an injection style attack, you may be able to influence the XML to be able to make calls to parts of the system that it shouldn't have access to. Broken access control, similar to broken authentication. Again, we talked about authentication, authorization. Broken access control is the authorization portion that's broken. So this would be where I'm an authenticated user, but I perhaps shouldn't have access to certain parts of the application. So that's basically meaning that the access control has been broken, allowing me access to portions of it that I shouldn't be allowed to. So kind of stepping back to what I said earlier, this is more related to like an elevation of privilege, where the authorization has not been properly put in place in order to stop you from gaining access to something you shouldn't have access to. Whereas the broken authentication is basically allowing you into the application without properly authenticating you. So security misconfiguration, this is again kind of self-explanatory, where basically the security features of a product or a platform or program are not properly engaged. So one of the examples I like to give about this is that for those of us that have Wi-Fi routers in our house, it used to be, maybe not so much nowadays because a lot of people are very attuned to this, but it used to be that you would get your Wi-Fi router. It may be set up by your internet provider, and then you would turn it on, you would get connected to the internet, and you would just move on. And maybe you never changed the password, or maybe you didn't shut off ports that were exposed externally. Maybe you still had remote access available. So there's a lot of different ways to configure something like a router to be more secure. And sometimes if those aren't set by default, you have the tendency of just, it works, I'm not going to touch it, so therefore I'm just going to leave it go. So security misconfiguration, that's an example of it, but in a web application space, things like not properly securing your HTTP headers or your web server or your database, not putting proper controls around it, or at least setting the security configuration within each one of those products. You want to make sure you have them set to the most secure features available. So not doing so is security misconfiguration. So cross-site scripting, this is another pretty popular one up there with SQL injection. This is basically being able to inject script into a web page. So we're going to talk a lot about cross-site scripting. We're going to show some examples of that when we get into WebGoat and Zap. But cross-site scripting, again, simple version of that. It's sort of like an injection style attack where you're able to send script to a web page or a website and make it, could steal cookies, it could scrape data off the page and send it to some other domain. So there's a lot of different things, obviously, for those that are familiar with writing script or JavaScript, you understand that there's a lot of power in JavaScript. So anything you can do with JavaScript, think of being able to do that with malicious intent. So there's a lot of opportunity there. Insecure deserialization. So it's fun to say, but deserialization is basically it's similar to what we talked about with other interpreters. Is that if you take if a application or program takes a serialized object, so basically anytime an object in like object-oriented programming, if you're taking an object and you prepare it to be sent somewhere, whether it's to a database or across a network, you serialize that object when you send it. So deserializing it is the reverse of that. So you've accepted that serialized object, and now you're deserializing it. So in those cases, when you deserialize, you're acting as an interpreter. So if anybody was able to inject information into that object, either before it was serialized or after it was sent, then your application has the potential there to interpret that object into something potentially malicious there. So it's the same thing as with injection, where your application is interpreting something that's been sent to it. And the reason I kind of reiterate that is that you're going to see a common theme around protecting web applications. A lot of that's going to come down to making sure that you don't trust your user input. So that's really what it comes down to. So using known vulnerable components. So this is basically, we all know as developers that you don't write every single line of code. Sometimes you're pulling code from other libraries or other locations. Using those components that are potentially vulnerable. So maybe you're using a version that's several, maybe even years old, that have several vulnerabilities in it. If you continue to use that component with known vulnerabilities in it, you're obviously at a higher risk of being compromised. Insufficient logging and monitoring. So this is basically not, again, pretty self-explanatory here, not logging or monitoring, not just not logging and monitoring, but even if you do, making sure that you log the interesting components of your application. So things where perhaps a high-value transaction, maybe you want to log login failures or change in privilege and things like that. So because the point is that you want to be able to recreate a possible incident. So you want to gather all that information together so that you can recreate that incident. All right, so let's talk a little bit about some of the other options that are available in OWASP. So OWASP has a couple different ways that they classify their projects. There's a flagship project, which is basically it's the cream of the crop. It's well maintained. There's a lot of documentation around it. There's continuous updates on it. Then there's the lab, where things are sort of stable, but there's some value there, but it's not raising to the level of flagship. The incubator are projects that are just starting up. There's still some work that's going on. It's very experimental, and then low activity is basically ones that are either they're not being maintained well anymore, or there's just not enough interest in it to keep it going. So that's just to level set the different OWASP projects that are available out there. So we'll talk through some of these projects here. So there are some tutorials on OWASP's page. As I mentioned, the top 10 that we just went through, that's the classic guidelines. There are cheat sheets that will allow, the cheat sheets have information in it that very specific to certain programming languages, certain functionality that you're trying to implement. So it's basically a quick reference for, hey, I need to understand how to secure a particular function in a language. Your first stop should be something like the OWASP cheat sheets to get you started. So some of the tools, and again, these aren't all encompassing. There's a lot of tools on OWASP, but this is just to get point out some of the high level ones that are of interest. So some of the tools are Security Shepherd. It's a web and mobile application security training platform. WebGoat, we're going to talk about WebGoat here in this course. OWASP Juice Shop is another one that's very similar to WebGoat. They have some capture flag type of work there available in Juice Shop. And then Vulnerable Web Applications Directory is kind of a landing page for all the different vulnerable web applications that you can use for testing. So we're going to talk about ZAP, Zed Attack Proxy. In fact, we're going to talk about ZAP here coming up soon. And ZAP is basically what we would consider a dynamic scanner. So you point it to a URL and you let it go ahead and do some testing. And it's going to uncover things like SQL injection, cross-site scripting, but it's basically a scanner, an application security scanner. And then the OWTF, Offensive Web Testing Framework. It's a penetration testing framework for scanning sites, very similar to ZAP. And then web testing environment, again, sort of sticking with the application security testing tools. The web testing environment is basically, as it states, it's an environment where you have tools available, and they come in VMs, Linux distribution packages, cloud-based installations, and ISO images. So it's a one file package that you're able to use to get an environment up and running to be able to start testing application security. So we're going to talk about ASVS in this class as well, Application Security Verification Standard. So that's just basically a good way of, it's a checklist that you can review application security of a web app. So it's so that you don't have to think for yourself of all the things you should be testing. The ASVS will help figure out, or at least point you in the direction that you need to go for looking at a web application. And then secure coding practices, the reference guide. That's similar to the cheat sheets, just a little bit more robust. So it's going to give you a lot of information on secure coding practices. App Sensor is it's code that you can implement within your application to help detect, respond, and defend your code. So it's and in fact it's similar, sort of similar to eSAPI there that you see at the bottom, where it's basically code that you're able to implement. App Sensor, it's code that you can implement into your own personal code to help you detect issues that are coming in, security issues coming in, and then log that information. Cross-site request forgery guard project is a way to create unique IDs for cross-site request forgery vulnerabilities. And then eSAPI is basically, it's a Java set of libraries that you can use and leverage in your own Java project. And it takes care of things like encryption, hashing, logging. There's a lot of different functionality in there that you're able to use. You can just pull it in as you would any other library and be able to begin to use it immediately in your application. Or if you want to just cruise through the code and use the same concepts in your own language, you're welcome to do that as well, because it's all open source. So Security Knowledge Framework, another thing we're going to cover in this course, is basically a way of, when you have a project that you're getting ready to start, you can use the SKF, or Security Knowledge Framework, to be able to identify areas of concern that you need to focus in on based on the way you're creating your application. So you may say things like, I have a SQL database, I have text boxes, I have authentication. You're basically building out this profile of the application or the feature that you're building out. You can use a security knowledge framework to help you identify what areas of concern that you may have from a security point of view. And then it'll give you a checklist of things to check after you develop the application. So it's very, very useful. And then the testing guides, it's going to be documentation regarding what and how to test your web and mobile application. So very similar to some of the other tools that are out there, like the other projects that are out there, like the ASVS and the checklist. It's going to help guide you through testing web and mobile applications. So there are code review guidelines, which are very helpful if you're performing a security code review. Then dependency check and dependency track are two not identical, not very similar, but dependency check is going to be able to look at all the libraries that you pull in during your build lifecycle and be able to determine whether there's any known vulnerabilities. It goes out and looks at the NVD, the National Vulnerability Database, which we're going to talk about later on, and determines whether some of the packages that you've bundled in your build have vulnerabilities that are known. Dependency track does what they call software bill of materials. So it's looking at your entire package for the code that you're for the application that you're building, and keeps a bill of materials about around that, so that you're able to track any kind of issues that may arise. So it's very sort of similar to dependency check, but not quite the same. And then Defect Dojo is a vulnerability management tool that you can plug in vulnerability information from different tools. You have dashboards. You have the ability to manage those vulnerabilities to closure within Defect Dojo. So it's basically a vulnerability management dashboarding tool. And with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about the SANS Top 25. Now, the SANS Top 25 is very similar to OWASP Top 10, and we're going to talk a little bit about the differences here, but you can think of the SANS 25 as the 25 most dangerous software errors. And very similar to the OWASP Top 10, you're going to see some of the usual suspects that you would see in the OWASP Top 10. But here you can see the Top 25. The other thing to point out here is that each one of them has a CWE, or Common Weakness Enumeration, and we talked about that in previous lessons. But this helps you tie back to the CWE for those specific types of vulnerabilities that are found. So the top 25 is broken down into 3 different categories. The first one is insecure interaction between components. And you can think of that one as your injection style attacks and things like that. So you can see here it says these weaknesses are related to insecure ways in which data is sent and received between separate components. Category 2, risky resource management. And a good way of thinking about these is memory type issues or buffer overflow. And you can see it says the weakness in the category are related to ways in which software does not properly manage the creation, usage, transfer, or destruction of important system resources. And in category 3, porous defense. This is a weakness that's related to defense techniques that are often misused, abused, or just not used. So you could think of this in the sense of issues with authentication and authorization. So specifically, the issues that are within each one of these categories, again, as I mentioned, with insecure interaction, talking about injection style attacks. So you see here SQL injection, command injection, cross-site scripting, cross-site request forgery, and so forth. With risky resource management, we talked about that. It's memory management and like buffer overrun. So you see these as, the buffer overflow, path traversal, incorrect calculation of buffer size, uncontrolled format string, and so forth. And then for porous defense, as I mentioned, missing authentication and authorization, use of hard-coded credentials, incorrect authorization, execution with unnecessary privileges, and so forth. So again, these are the different vulnerabilities that are in each one of these categories. So really, what's the difference between OWASP and SANS, other than there's 15 more in SANS than there is in OWASP top 10? But with OWASP, the focus is on web applications, whereas with SANS, the focus is not just on web applications, but also on desktop and server applications as well. So it's much more broad than what you see in the OWASP top 10 that's geared towards web applications. The other thing between the two is that OWASP focuses more on risk. So each of the vulnerabilities are categorized and prioritized by risk. So whereas with the SANS top 25, the vulnerabilities are rated according to prevalence. So how prevalent is that given vulnerability? Is it widespread? So that's why you see something like cross-site scripting that in the OWASP top 10, it's number 2, but in SANS 25, it's number 1. So it's more prevalent. Therefore, SANS ranks it higher, whereas OWASP says it's not from a risk perspective. We think that injection is a higher risk, so therefore cross-site scripting is second. So with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back to this course, and today we're going to talk about threat actors and definitions. So we talked a lot about confidentiality, integrity, and availability in the last lesson. And just a reminder that those are the top 3 things. If you take nothing away from this course, confidentiality, integrity, and availability are the 3 things you should take away from this. So when we talk about confidentiality, we're talking about things remaining private or secret. You usually reach confidentiality using things like encryption. When we talk about integrity, that means that something that was sent from one point to another should not be changed in transit. So in other words, what I send from point A should be what's received at point B. Availability means that when I make when I'm trying to access a resource or a system, a web application or something to that effect, that it's available for me at the time that I make that request. Some of the other concepts we're going to talk about throughout this course, authentication and authorization, they sound very similar, so it's easy to get confused here, but authentication is a way of proving your identity. So one easy way that I like to think about authentication and authorization is that authentication is something like an ID, whether it's maybe a driver's license, a passport, or a government ID, a student ID. So that has your picture on it, has your name, might have some other information on it, but it basically just proves that, yes, that's you. So for instance, on my driver's license, it's going to say Derek Fisher, it's going to have my picture on it, it's going to have some other information about it. But the difference between that and authorization is that that ID, showing my authentication, is not going to allow me access to something like a military base or a nuclear plant. So just because I have an ID doesn't mean that grants me automatic access to some resource. So and you can also think about maybe your student ID, or if you have a badge at your employer. If you swipe that badge to get access to some rooms, you may not have access to every single room. So that is authorization, that you only have access to things that you should have access to. Accounting or auditing is really another term for something like logging, which just means that user activity or system activity is being collected and viewed. So accounting, think of that as logging. Non-repudiation means that I can't deny sending something that I sent. We'll get into this more when we talk about digital signatures and encryption. But basically this means that if I send a digital message to somebody, that I can't prove or I can't say that I didn't send it. There's ways of proving that I did actually send that, and that's more about digital signatures, and we're going to talk about that later. So least privilege, we talked about this in the last lesson, some of these items. So least privilege just basically means that I should only have access, and this ties into like authorization, but this means that I should only have access to things that I'm required to have access to do my job. So whether I'm a user, whether I'm a system, you don't want to grant root level access or admin level access to an account that maybe only needs to access a very small portion of a system or a website. Separation of duties means that you shouldn't have extreme control in one account. So in other words, if I need to process a high value transaction, that perhaps that means that two accounts should be involved with that transaction, and it shouldn't just be one person being able to process that transaction. Defense in depth, we're going to talk a lot about that throughout this course, where it really means that all the different components of security build out a larger defensive structure. So things like analysis tools, penetration tests, threat modeling, risk assessments, all these things are components of that defense in depth that really build out a large and more robust, secure posture. So fail safe and fail secure. Fail safe means when a system experiences a failure, it should fail to a safe state. So if there's a fire in a room, you don't want the doors to slam shut and lock and potentially lock everybody in. Failing safe means it would open up or at least allow exit in that kind of a situation. A fail secure means that the default state is locked or secured. So a fail secure lock will lock the doors when power is removed. So think of maybe like a bank or a prison where maybe if the power goes out, you don't want all the doors to open. You want to make sure that everything gets sealed up. Single point of failure. This just is a concept in security where you don't want to have all your eggs in one basket. So for instance, if you have a database server that has all of your sensitive information on it, that's a single point of failure. If somebody is either able to access that database or take it offline, then you have a security issue on your hands. So let's go through some of the threat actors that are out there. So we talk about script kiddies, and these are going to get progressively more difficult and also in terms of skill, get higher skilled. But first, we're going to talk about script kiddies here. So these are low-skilled people. They're looking for easy and simple attacks. So in most cases, they're going to grab code that's already been developed by probably a much more skilled hacker, and they're going to take that and use that for some gain. Their motivation is usually revenge or fame. And it's important to understand motivation when we talk about these threat actors, because that helps you understand how to better defend your system. Hacktivists, so these are a little bit more skilled than your script kiddies. So they have moderate to high skill. They're looking to make an example of an organization. So it could be a nonprofit, it could be a hospital, it could be a company that they're trying to make an example of. And they're motivated by activism. So they might have a grievance against that company or that organization. So therefore, they may try to do something like deface the website or create a spam campaign or a DDoS attack or something like that. But their whole point is to try to call attention to some grievance that they have, whether it's theirs or somebody else's. Hackers, now the term hackers gets a bad connotation sometimes, but really hackers are engineers who are able to really understand the nuts and bolts of a system. So these are high-skilled people. They're looking to understand how things work. Their motivations vary because you can have hackers that are in it for nefarious reasons, or you may have hackers that are trying to do the right thing and make sure that software and systems are secure. But these are very high-skilled, very knowledgeable, can look at a system and quickly understand it, and more importantly, quickly understand how to break it. Cyber criminals, again, we're going up the scale here in terms of skill and the ability to defend against. But cyber criminals, they have higher skills. They're in that hacker category, and they're looking for financial gain. So their whole point is to steal money. So they're going to go after banks, they're going to go after financial institutions or people that have wealth that they can potentially steal. So cyber criminals, you'll see them in a lot of spam campaigns or phishing campaigns, ransomware, cryptojacking. Their whole point is to try to siphon off money from either organizations or people. And then the last one we're going to talk about here is advanced persistent threat, or APT. They're also called nation states. You might see that term thrown around about APTs as well. These are very highly skilled, very deep pockets. These are government-backed teams or organizations in some cases. And they're looking to commit cyber attacks in order to weaken a political adversary or create some kind of chaos in a political adversary or another country, rival country. So they're driven by national interests. So, and when you think about advanced persistent threat in nation states, we're talking about the United States, Israel, China, North Korea, Russia. And a lot of times these advanced persistent threats are a component of the overall military of that nation. So again, very deep pockets, very highly skilled, and it's almost a 9-to-5 job where they come into work, they sit down at their computer, they attack foreign governments, and then they go home for the evening. So as I mentioned, we kind of went through low skill to high skill, and what that really means is that from a defense perspective, it's more difficult to defend against those advanced persistent threats compared to, say, the script kiddie. So you'll see that a lot of automated tools or a lot of the security tools that are, I don't want to say run of the mill, but a lot of the security tools that are standard are very good at protecting against script kiddies. As you move up that prism here up to advanced persistent threat, it gets much more difficult to defend against those types of actors because it's just they're higher skilled. They know your system. A lot of times they're in your system for the long term. They're not trying to do a quick extort some money out of you and move on. They're looking to gain a persistent foothold into a network, and that's much more difficult to try to defend against. So let's talk a little bit about identifying some vulnerabilities. We're going to go through some different organizations and different acronyms that produce information that can help you identify some of the vulnerabilities that are out there. So CVE, Common Vulnerability and Exposure. This is basically a way for, it's an industry standard for creating a listing of vulnerabilities. It's really a dictionary of vulnerabilities. So every time a new vulnerability comes out, it gets a unique number called a CVE. And it is developed based on the year. So you're going to see the way it's identified. It's going to be CVE- this is 2020, so it would be CVE-2020, and then a month date and another identifier. But the whole point there is that for every vulnerability that comes out that's been classified as a vulnerability will be submitted to MITRE, and MITRE will produce a CVE number that identifies that specific vulnerability. So what this really gets the industry is that there's a single language or a single way of identifying a vulnerability that's common across the industry. So it really helps with being able to identify not just the vulnerability, but how to mitigate it or remediate it by having this common language around it. CVSS, so when you get a CVE, when a vulnerability gets a CVE, there's an associated CVSS score. Now, not just with CVEs, you can use CVSS for other scoring abilities, but basically this is a way to score a vulnerability, and it gives you a way to say, this vulnerability is either a critical or maybe it's a low. So it's a 1 to 10 scale. And basically, the higher it is, the more critical that vulnerability is. So one little caveat about CVSS is that it depends on your organization, and it depends on the scope or where that vulnerability has impact. So in other words, you may not always want to take the CVSS score as at face value because if you put it into your environment, you say, okay, maybe this vulnerability is remote code execution, but you need to be running this specific version of this software. And yes, you may be running that software, but maybe you're not running that, or you may be running that software in that version, but maybe it's in a lower environment that has other controls around it. And so the CVSS score that comes out might rate it as a 9 or 10, which means it's critical. But because in the context of your application, maybe that is behind, again, some other mitigating factors or controls, which will reduce that from a 9 to a 10 to maybe something lower. And we'll get into more of that when we talk about risk rating and risk management. But there is a calculator here for how you can calculate a score of a vulnerability. You can see the link here. So common weakness and enumeration. So this is another industry method of understanding the different vulnerabilities that are out there. So we're going to talk about OWASP Top 10. We're going to talk about SANS 25. Common weakness and enumeration is sort of similar to that in the sense that it's a grouping of different types of vulnerabilities or weaknesses that impact systems. The CWE is not specific to web applications, but it is a very good indication of all the different vulnerabilities or weaknesses that impact app systems, technical systems. So they are broken down into 3 different types of weaknesses: research, development, and architecture. For the purpose of this class, architecture is probably the one that you want to take the most stock into. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over the anatomy of an attack and defense in depth principle. So we talked a bit about vulnerability. That's just basically a weakness in a system that allows an actor, a threat actor, to gain access or to do something nefarious. So here you see a real world example of a military plane hiding underneath of a bunker. And this is kind of typical in military space where planes would be put in these bunkers where they're protected from not just aerial view, but from potentially bombs. And you can see how thick that concrete is. But a lot of the militaries around the world have developed what they call these bunker busting bombs that are able to burrow into that concrete and then deliver the explosive. So in this example, the vulnerability is the concrete's weak, or at least the type of missile being used is able to get through that concrete. So the exploit is basically that missile coming through, and then the payload is that explosive that comes, that is delivered by the exploit. So in a digital example, the vulnerability could be Adobe Flash. We're probably going to pick on Adobe Flash a lot because it's been picked on quite a bit. So we could say the vulnerability in perhaps a web application is that it's running Adobe Flash, and the exploit is code that's been written by an attacker to take advantage of that vulnerability. And then the payload could be something that the attacker wants to deliver, a keylogger or ransomware or Trojan or something along those lines. So when we talk about a defense in depth principle, a castle is a great way to think about defense in depth, is where you have a keep, you have walls, you have a moat, you have a drawbridge, you have perhaps other things around the moat to be able to keep people out. Maybe you put alligators and snakes in your moat, but the principle there is that basically not just one system is going to stop attackers. So you want to build multiple systems that work together to be able to stop an attack from happening. So again, in the castle example, you pull up your drawbridge, you're hopefully protected by the moat that's there. Nobody, an attacker would have to get across the moat or try to take your wall down. Even if they are able to take your wall down and get across the moat, you still have your keep, where a lot of your troops and the important people would be in that keep to make sure that the attackers can't get in any further. So it's that whole layered approach. And in cybersecurity, we have that same principle where there's a lot of different techniques, policies, processes, and technology that we put in place to make sure that we're properly protecting the assets that we're trying to protect. So what does this really look like in the cyber world? Well, you can see this bit of spaghetti here, where you have things like DDoS protection. We have things like DLP, antivirus, IDS, IPS, and we're not going to talk about a lot of that stuff, not necessarily on the network side. We're going to talk somewhat about DDoS attacks when we talk about availability. But you can see that there's a lot of different components that go into protecting against cyber types of attacks. So the important thing to remember is not to rely on a single item to be able to protect your assets against a cyber attack. Systems fail, they can be circumvented by the weakest link. So remember, a very complex system, we talked about this before, keep it simple. So a very complex system can be difficult to manage and maintain, but more importantly, a weakness in one of those things can then create a chain reaction that makes the entire system weak. Your app may not always be behind all those components that you have in that defense in depth. So that's another important thing to consider, is that when we develop software or web applications, we put it inside of a data center in an enterprise. We put a lot of different controls behind that. Like I mentioned, intrusion detection, intrusion prevention, firewalls, VPNs. We have all these different things that are there to make sure that the application is secured, and we have antivirus and monitoring, and so. But and we see this today, where a lot of those applications are being moved to a cloud type of footprint. Well, in that case, there's a lot of similarities in the sense that there are options in a cloud that you can leverage that are similar to what you have in your data center, but they're not always going to be the same. And there's an opportunity there for things to be missed or dropped. So it's important to remember that as we talk about defense in depth, that you shouldn't rely on all those components that are there, because your application may not always be behind those different defenses. Okay? And with that, I appreciate you joining me for this lesson, and I look forward to seeing you in the next. Thank you. Welcome back, everyone. In this lesson, we're going to go over proxy tools. So what are proxy tools? Well, we're going to get into that, but just before we do, there's a couple ones that you should be aware of. So Charles Proxy is one. Fiddler is a pretty well-known one. OWASP has a Web Scarab, although I'm not sure what the state is of that right now, and may be different by the time you see this. And then browser tools have some level of proxying ability within the developer tools within each of the browsers, so like Chrome and Firefox. But the one that I have most familiarity with, and one that's pretty well known throughout the industry outside of the developer tools, is Fiddler. So why do we want to talk about proxy tools? Well, so you may know, and as we'll get into later on, the HTTP request response model is between a client and a server. So when you go into your browser and you make a request to, let's say, Google.com, you're going to punch in Google.com in your address bar, and the browser is going to make a request to the server. So there's a server that is serving up the Google.com page. The server responds back with an HTTP response, and usually a 200 code, so an HTTP code of 200. And then for every subsequent request that you make to Google, it's a brand new request response. So the client makes a request, server responds, and so forth. That's doesn't matter whether you're doing a get, a post, or some of the other web service verbs that are out there. But this is all the same. It's a request response. And the reason I bring this up is because it's good information as we get into what proxies do. So proxies act as a intermediate between your browser and the server that you're trying to actually access. So the server you're trying to access could be, like I said, Google.com or Amazon or any other website that you're going to, or it could be your local host. So think about this in the sense of some of the development that you do in a web application. Tools like proxies like Fiddler or some of the developer tools within Chrome and Firefox, they're good ways of being able to debug and see what the traffic's doing. So if you're running into issues and you want to try to track down what the issue is, using a proxy or the developer tools to be able to figure out what's being sent in the request and what's actually being responded in the response. So those proxy tools, and here it just shows an example of Fiddler, really sits in between your browser and the web server, and it has the ability to capture the request that you're making and basically forward that request over to the web server. And then when the web server responds, the proxy will capture that information and send it back to your browser. So it's acting really as a proxy, somebody that's in the middle. And why that's kind of important, not just from a developer perspective and being able to debug, It's also important from a security point of view because some of you may already be thinking about this, but in the case where you want to protect against information that's being put into a text box, let's say on your web application, you want to make sure that you're not exposed to SQL injection. So you're going to put protections into that text box. Well, if you put those protections on the client side, let's say through script, the ability to fire up a proxy and change the values before it gets sent to the server basically circumvents any checks that you have within your script. So you'll hear a lot as we go through this course where we talk about sanitizing inputs and ensuring that you trust the data that's coming from your client or your user. You want to make sure you do that both on the client side and on the server side. The client side is good for providing feedback, immediate feedback to the client, but it's not a good security mechanism. In other words, you want to be able to check on the server side as well. And with that, we're going to go in and do some demos of Fiddler. So thank you for spending some time here on this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over Fiddler, which is a proxy tool, and show you some of the ins and outs with using a proxy tool, as well as some important things regarding capturing data and replaying. So what I have up here is called Juice Shop, and it's run by OWASP. This is a Heroku app. Basically, it's free domain hosting. Anyway, so Juice Shop is up here running. This is a capture to flag project, so you can go in here, and if you feel confident enough, there are some capture to flag goodies that you can try to capture and earn points. That's not the point of what we're trying to do here. So I do have Fiddler up here running. I want to make sure that I don't have my breakpoints, so they're disabled. I'm going to start capturing here. And if I go ahead and reload the page, you should see over here on Fiddler, I'm going to stop capturing just to stop the noise. But you should see here, what you do, the loading of the Juice Shop website. So you see all the requests being made, and just so you know, the top portion here is the request. So that is what your browser is requesting of the server. And down here is the response. And if you were paying attention when we were talking about HTTP request and response, you'll understand this is what's being requested by your browser. This is the response that comes back from the server. So you see here a bunch of JPEG files. There should be some JavaScript files loaded in here as well. JS files here, some other information or some other files and folders that are being requested by the browser in order to create the web page. So just to clean this up a bit, I'm going to clear out the screen. I'm going to go ahead and set a breakpoint here. I want to do a before request, which means I want Fiddler to stop basically before it makes the request to the server. So I'm going to say before request, and then I'm going to make sure I'm capturing. And let's leave a review for green smoothie. I like green smoothie, so I'm okay with that. Okay, so Juice Shop here broke. All right. We're going to let it run just to clean out the noise here. And I'm going to go ahead and put in my review, which is going to be, this is fantastic. Okay. And say submit. And once it says, my review has been processed, actually, I'm just going to let these guys run because it doesn't show yet. Should see it here in a second. So here we go. So here it says this is fantastic, right? So that's the review that I left. I'm going to get rid of my ID here and change it to something else. And while I do that, or once I do that, so it no longer shows my ID. I changed it to Fudu. And I'm going to leave an awful review. All right. I'm going to go ahead and say run to completion. All right. Got a 201 back, so that's good. I'm going to stop capturing just for good measure here. I'm going to close. And if I go and look now in the reviews and scroll down and see the most recent review is the one that I left. So it wasn't the one that actually was submitted. It's the one that I changed. So the reason that's important to understand is that when we talk about validating user input, it's important to recognize that validating user input on the client side or through your scripts or through your HTML is not sufficient. So if you have, for instance, a validation check to make sure that somebody's putting in a phone number, you're only expecting to get numbers in that text box. This shows that once that request is submitted by the browser or by the user, that the user has the ability to intercept that, pause it, break, and change the value to something that you're not expecting. So it's important to realize that you need to be able to do those checks on the server side as well. So I hope this is a good indication of and get your thoughts going on ways of making sure that you're protecting yourself against user input. So I appreciate you joining in this lesson, and I look forward to talking to you again. Thank you. Hey everyone, welcome back to this lesson, and we're going to talk about insecure deserialization. So what is it? Before we get into insecure deserialization, let's talk a little bit about what serialization is. So basically it's the taking of an object and getting it prepared to be transmitted somewhere. So you can think of some of the examples here: remote and inter-process communication, so RPC, wire protocols, web services. It's basically taking an object in code and getting it prepped to be transmitted somewhere. So that's the act of serialization. And it can go to memory, it can go to database, and go to a file. But it's basically packaging something, an object, and sending it, or preparing it and sending it along to another location. So you may be thinking about this. So deserialization means that on the other end, somebody has to receive that serialized object and unpackage it or deserialize it. So the most common way of serializing objects today is through JSON. It used to be XML. And so for those that have been paying close attention to this class, you may realize that, okay, this could be a potential issue. Same thing as when we've been talking about things like SQL injection or other types of attacks where basically your application is taking inputs from a source and acting on those inputs. Well, deserialization isn't much different. So somebody can send something to whether it's a database or a file or something like that, and it then gets unpackaged. If that obviously where we're heading with this is that if that package is malicious, well, that could be problematic. So applications that are susceptible to insecure deserialization are susceptible because those objects that get sent could be structured in such a way that it could create arbitrary remote code, could execute arbitrary code, or somehow influence the application that it's targeting. The other option or the opportunity there is that the data could be manipulated inside of that object. So both of those are concerns, either being able to execute code that the application is not expecting, or being able to manipulate data that's in that object being sent. So there's some prevention options here. So one of the, I don't want to say easy, but one of the more common ways of trying to protect against this is using integrity checks. And we'll talk a little bit about hashing and digital signatures and things like that, which sort of plays in those integrity checks. But you may know that when you go and download an application from a website, you might get something like a thumbprint or an MD5 hash. That's basically the signature of that application you're getting ready to download. So very similar, and again, we're going to talk more about that stuff later on in this course, but very similar, you can have an integrity check on an object that basically shows it hasn't been tampered across the wire. And that gets into the integrity, the CIA, and the CIA triad that we've been talking about. You can enforce strict type constraints, so in other words, you know what the object should deserialize to, so you shouldn't get any other types of data sent to you. You can isolate that code to make sure that anything that you deserialize gets executed or deserialized in a secure area of your application. You want to make sure you log any deserialization exceptions or failures, because that could be an indication that there's an attack going on. You want to also monitor incoming and outgoing network connectivity to make sure that nobody's doing anything nefarious there as well. So here's an example of just a very simple example using a cookie where there's an issue with or a potential opportunity here for unpackaging a serialized object. So what we have here is a cookie. Malloy is a user here. There's a password that's associated with it. That's the bolded hash there. So an attacker, in this case could be Malloy, is able to change the object to basically upgrade their privileges or elevate their privileges to an admin using Alice's username and the role of admin. So therefore they were able to tamper with it. And obviously this is a little, very simple example. The password is the same. So maybe it's only just checking to see whether the password is valid and letting that account in. But there would be other checks in place here. But basically, again, this is just a simple example of a serialized cookie that somebody was able to manipulate and send over to elevate their privileges. Again, hopefully in most cases there's enough checks going on to make sure that this simple attack doesn't occur. So with that, I appreciate your time with this lesson on insecure deserialization. I look forward to seeing you in the next one. Thank you. Welcome back, everyone. In this lesson, we're going to go over insufficient logging and monitoring. So exploitation of insufficient logging is basically what every attacker is looking for, because in a physical sense, if you don't have things like cameras or monitoring systems or security guards, you're not going to catch things happening. So likewise, in the digital world, if you don't have proper logging and monitoring on top of that logging, then attacks can just go by without being noticed. Here you see a note there at the bottom. In 2016, identifying a breach took an average of 191 days. I don't think that's improved much in the years since, but obviously 190 days is a long time for an attacker to be able to do what they came to do. So when we talk about insufficient logging, some of the things that come to mind, or some of the more important things here are, not logging auditable events. So things like logins, login failures, high value transactions that are occurring. You want to make sure that, or the lack of having warnings or errors generate either unclear messages or no messages at all, obviously is an example of insufficient logging. Not logging or not monitoring logs around APIs, who's calling them, what's the request and response on those APIs, and not monitoring them for suspicious activities is a good example. Logs are only stored locally. That's a problem as well, because if an attacker is able to compromise the web server, then in theory they can blow away the logs, and you would have no tracing back to what actually happened. You want to make sure that there's escalation process in place for when alerting has met some kind of a threshold. So many of us may be familiar with threshold alerting on things like CPU usage or memory usage. So you want to make sure that that there's an escalation process in place for when those thresholds are go past the threshold. So one other good clue that you don't have good logging is when penetration tests or some of your scanning tools don't actually trigger any kind of alerts or any kind of logs. That's a good example that your logging is insufficient. And an application is unable to detect, escalate, or alert for active attacks. Now that's a little bit more, it's a little more difficult to do. So that's, I would say, a mature process there, but it's something that's definitely considered an insufficient logging if you're not able to alert for things that are actually happening in real time. Now, I don't mean that it's mature in the sense that that it's difficult to do or that not a lot of people are doing it, but there's a problem in the industry where we get alert fatigue, and basically just means that alerts are constantly coming. It's very difficult to keep up on those alerts. So getting alerts that are actionable is really key. So what are some of the good practices around logging? So basically the reverse of what we've just talked about, making sure that failures are logged, especially around high value transactions and logins, password attempts, those kind of things. You want to, things that would raise suspicion that somebody may be doing something that they shouldn't be doing. You want to make sure that those are being logged. You want to make sure that logs are being generated in a format that could be sent to some kind of a centralized logging system. We'll talk about that here in a second. You want to make sure that high value transactions have an audit trail. So you want to be able to see the process end to end. You want to make sure that suspicious activities are detected. And you want to make sure that there's an incident response and recovery plan that's established so that if something does happen, you're not trying to build that plan after it occurs. So security information and event management, or SIM, is what we typically call it. You'll see a lot of these. Splunk is typically used these days for something like this. But basically the reason why you want to make sure that your logging that you're creating is put into a format that can be consumed by some of these larger products is that a SIM acts as a way of correlating all the data and all the logs that are being pulled from a lot of different systems and applications and putting it into one location so you have a dashboard. And more to the point, not just a dashboard or one single pane of glass, but being able to act upon all that different information to be able to spot an attack happening, because something that happens in your web application may not necessarily trigger an alarm to make you think that something's happening, but maybe there's something going on the network, or maybe there's something going on in a system that's near yours or similar to yours. Having that level of information to be able to correlate with potential information that you have locally or within your application provides a larger view of a potential attack that's occurring. So that's why it's important for these SIMs and centralized logging to be in existence, and making sure that the logs that you create are able to be consumed by those larger systems. So with that, I appreciate your time today, and I look forward to seeing you in the next lesson. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over security misconfiguration. So security misconfiguration is basically, you can think of it as the absence of security settings. It can be in your hardware, your software, your configuration, in your applications, your framework, your database, your web server, your platform. You can see some of the examples here. But basically, it's if you get something, you take it out of the box and you plop it onto your network or install it and never touch any of the configuration settings in it. That's an example of security misconfiguration, because a lot of those configuration settings aren't typically set when you take something out of a box and run it. So, because a lot of times the reason for that is that if you think about it, you want to make sure that when say you get a brand new application and you want to install it on your laptop or your mobile phone or wherever you're installing that application, you want to make sure that it works as soon as you install it or right after you install it. And what typically happens with security settings is it makes things more difficult to work out of the box. So a lot of times security configuration or more secure settings are turned off by default. So not going back in and making sure that those security settings are set is an example of security misconfiguration. So like I said, security misconfiguration can be lack of patching. It can be the lack of setting up secure configuration, such as in your parsers, using outdated security configuration, default settings, and passwords. And that last one's a pretty good example, especially in the real world. If you get a router from your ISP, depending on where you're located, your ISP is going to be different, but I have Verizon, Comcast is the other one. We only have obviously two, a lot of places that way, but they bring in a router for you to use their services. And not so much anymore, but it used to be that you would get that router, you would take it home, or they would, a person would come and do the install. And the default username and password would be left on there and never changed. If you didn't go in there and change that, or if you didn't log into your routing and change some of these settings, like turning off WAN access or setting up your DNS resolve, So some of those things, if you go in there and make those changes, you're creating a more secure router. However, out of the box, that isn't the case, and it's very common. Again, maybe not so much anymore because a lot of people have become wise to this, but it used to be that a lot of router or a lot of network appliances would have default username and password like admin. Everybody knew what that was, and a lot of times you could go and just do a simple search in say Google for what a default username and password is if you knew what the device was, and it would be widely available. So not changing that, again, is an example of misconfiguration. So that's just a real world example of security misconfiguration. So here's an example in Java, basically not setting up in your config where you have the role name. It's highlighted here. So for any JSPs, it's allowing any role to have access to that JSP. That may be okay, but chances are you don't want that type of wide open access. You probably want to have a little bit tighter access controls on it. And in a .NET example here in the web config, you see here that the compilation default language C debug equals true. Here the example being that the debug is set for true. That may be okay in a lower environment like a testing or QA environment, but you certainly don't want that getting set in production. And if something like this was done in production, it would be a case of security misconfiguration. So another example here is being able to enumerate HTTP responses from a server. So we haven't really talked a lot about the different HTTP codes that you can receive. We talked about 200s on request and response, but there's other examples for like redirected 300 range. Then you have 403, 404, which we may be familiar with seeing. And in general, that's not terrible, but there are cases where, for instance, like a 403, meaning that it's forbidden, or 404, meaning it's not found. It allows an opportunity for someone to basically determine whether a file exists. So, for instance, if I'm trying to enumerate all the possible pages within your application, and I go through and I keep getting 404s, meaning that what I'm trying to brute force doesn't show up. But if I get a 403 back in one instance, that tells me, and some of you are probably drawing this conclusion right now, but that tells me that the file does exist, but I just don't have access to it. So it's an opportunity for someone to try to basically enumerate the different files that you have on your web server. So maybe that's probably not a great thing. It depends on your situation. It depends on the application. But again, this is just an example of where not having or providing better response codes that don't give away so much information is a better way to address that, as opposed to just the raw HTTP response. So what are some of the defenses? Well, as you can guess, with security misconfiguration, it's difficult to have a tool or something like that. To a lot of things, like when we talk about secure coding, we're gonna be talking a lot about the different tools that are available there. There's not really a tool that can protect you against security misconfiguration. So it really just comes down to understanding what it is that you have, understand what those default settings are, and the ones that are probably insecure and ones that you may want to change. And then keep in mind, the basics that we've been talking about, and we're going to continue to talk about in this class, is confidentiality, integrity, and availability. How do you maintain configuration in a way that's going to protect the CIA triad? And always remember, aside from the CIA, that you want to maintain least privilege. Meaning, again, we talked about this too, but making sure that the people that have access to something only have the access required to do what it is, what they need to do in terms of necessity. So you don't want to over privilege someone so that they have extensive access to things that they really shouldn't have over the course of their use of your system or your application. And with that, thank you for tuning in on this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about sensitive data exposure. So when we talk about sensitive data exposure, it's pretty simple. It's basically the breach of data that should have otherwise been protected. So if you're paying close attention, that means that we've lost confidentiality. So it's a breach of confidentiality. And so attackers are able to steal data through whether there's a weakness in the application, a vulnerability. Sometimes it's very simple in cases where maybe hard drives are left unattended, computers are left unattended, and somebody's able to grab information that way. That's a pretty low tech way, and then it goes all the way up to someone actually breaching a network and gaining access to a system or database. So there's a lot of different ways that confidentiality can be broken and sensitive data can be exposed. So primarily when we talk about protection in this area, we're really talking about encryption, of course, because if you make the information or the data unreadable to the human eye, then it's no longer valid or it's no longer valuable to someone that steals that information. So there's a couple different, and we're going to talk about these as we go along throughout the class, but from a high level, there's a couple different types of sensitive data that we don't want to expose. So there's PHI, which is protected health information. There's PII, which is personally identifiable information. There's sensitive financial information. And depending on which type of industry that you may be working in, whether it's financial or health or through consumer products, the data that you're trying to protect or data that you call or classify sensitive may vary. So some of the things that are pretty common are things like names, dates. You can kind of see here in the PHI and PII. And then there's some things that are fairly obvious, like social security numbers, credit card numbers, PIN numbers, things like that, which are pretty obvious that you want to have being confidential. So, like we talked about before with assets, when we're trying to protect assets, think about things that provide access to value, things that hold value, and things that produce value. Right? Those are the three types of things that we talked about when we were talking about assets and wanting to protect them. Sensitive data falls into that category of things we need to protect in terms of those types of assets. So some examples of data leakage we can see here. There's using memset and C++. The purpose of memset is to get rid of the content in memory. But sometimes, depending on which compiler you're using, it could optimize out that memset call, and basically it doesn't run. So therefore, the data that you think that you think is going to be scrubbed out of memory isn't, because the compiler decided for you that it's not going to do that. Data and log files. So as a developer, you may be taking data from a production environment to help troubleshoot issues that you come across. When doing that, you have to be mindful that there's possible data in those log files that could contain sensitive information. So what happens to that log file when you bring it to your local machine or share it with the rest of your team, or put it into something like a ticket, or Jira ticket or some other ticketing system for development. What happens when that log file gets appended to something like that? So just an example of being careful with the information that's in the log file and what you're doing with that log file. And then a lot of times in databases, there's obviously a lot of data in databases that is potentially sensitive. So you want to make sure that passwords and other sensitive information, social security numbers, PIN numbers, things like that are properly managed in those databases, or properly either obfuscated or hashed or encrypted, so that it's not available to be read in plain text. So when we're talking about protecting data, there's a couple different ways. There's protecting data at rest, protecting data in motion, and protecting data in use. And we'll start with protecting data at rest. So this is data that sits on a file system, or in a file, or on a hard drive, or in database, or the application configuration files, all that stuff. So it's basically data that's sitting in some form. And you want to make sure that, especially sensitive information that's at rest, you want to make sure that it's encrypted. It's a lot easier these days to do that, especially with the database technology that's out, to make sure that you can get down to field level encryption or table level encryption, transparent encryption. There's a lot of different ways of encrypting databases these days. With access control too, you want to make sure that, especially around sensitive information, that you practice least privilege. So make sure that that only those that require access to that sensitive information are the ones that have that access. but you want to make sure that you have proper logging around that, and make sure that you have proper access control, so that lower users that don't need to have that type of access are properly inhibited from gaining access to it. Protecting data in motion, that's especially when we're talking about web applications, that really means HTTPS or secure FTP for file transfer, and a lot of other different techniques for doing protecting of data in motion. So with that web applications, again with HTTPS, that's pretty ubiquitous these days. It wasn't that way even a couple years ago, but you're starting to see a lot more wider adoption of HTTPS. And more wider adoption of techniques like PGP for payload encryption. So it encrypts before it sends, and you can decrypt on the other end. We're going to get more into that when we get into encryption and certificates later on in this class. So with data in use, protecting data in use, that's really, we're talking about memory. And so there's a lot of different ways that you want to make sure that you're protecting, like I mentioned before with the C++ and the compiler example. You want to make sure that your compiler is configured to not optimize away certain memory controls that you put in place. Also, you want to make sure that you're doing code quality and cleanup issues to make sure that there's no references to memory that shouldn't be there. And then you want to make sure that you don't have insecure direct object references, which is basically where the code is able to access objects in memory that it shouldn't. So a couple different ways, again, of protecting, but it all really kind of comes back down to configuring your like things like your compiler, or configuring your systems to provide protection of the different types of data that you're trying to, sensitive information you're trying to protect. But more importantly, it comes down to encryption. And again, we're going to get more into encryption later on. But when you think about securing data from data exposure, think encryption, think security configuration. And with that, I hope you enjoyed this lesson, and I look forward to seeing you next time. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over XML external entities. So this is basically, as we've been talking about some of the other examples of potential attacks, where a processor is attempting to extract information from an external input. So it could be coming from a user, from a file. In this case, we're talking about XML files. So basically, an attacker can send an XML file that the processor, or in this instance, like an interpreter, will be able to take that file that comes from an attacker and potentially execute arbitrary code, maybe gain access to data or files or areas of the system that you shouldn't have had access to, or even bring the system down, which we'll talk about here in a minute. So again, this comes back down to interpreters, processors, anything that is its sole purpose is to take input from an external party and try to act upon that, leads to the possibility of an attacker leveraging that. So there's a couple different ways that an application or XML can be vulnerable to this. So if a application accepts XML documents through, whether it's an API or through a file upload, specifically from untrusted sources or anonymous sources, that could lead to potential compromise there. If your application uses SAML, SAML uses XML to transfer assertions. So in that case, your application is going to be processing XML documents in that case. If you're using a lower version of SOAP, that will potentially lead to a vulnerability there. And then, as we'll show here, there's a possibility that processing XML files could actually exhaust the resources on your application or your hardware, and that leads to something that we're going to talk about here, the billion laughs attack. So in the billion laughs attack, this actually consists of 10 entities having 10 entities within it, and it basically becomes an exponential type of attack where the XML processor will basically go through all of those possible entities and preload them, and it will essentially just exhaust the resources of the application. So this was found quite a while ago. 2002 was when it was first seen. Why it was still being done in 2008. And there's a couple of different defenses to this type of attack: capping the memory, making sure that that the application doesn't over-process, a file that comes in. So what does it actually look like? Like I mentioned, it's 10 entities with 10 entities within it, and basically the first entity will go to LOL, the first entity in that, and it spans. And what actually happens is that first entity will walk through each of the other entities and all the other entities, and basically it's just processing this entire document up to a billion entities. So that's why they call it the billion laughs. In this example, LOL was used as an entity name, but basically what's happening here is that it goes through and tries to process each one of those entities, and that will exhaust the resources on the server, make it come to a crashing halt, and as we know, that's a denial of service attack. So here's another example where an XML file is attempting to gain access to a password file, and if you don't have proper controls around who can access that password file, there's a potential opportunity here for an attacker to be able to view that password file through an XML file here. So what are some of the options for trying to stop an XML external entity attack? You can make sure that you're using more robust types of ways of exchanging information, say like JSON. Make sure that you patch all your XML processors to make sure that they're using the latest and greatest, which typically come with a lot of security benefits. You want to make sure you're using the higher version of SOAP. You want to make sure that you are disabling any kind of XML external entity processing unless you need it. You want to be able to provide whitelisting for where the XML or where your application can go process or grab information. Like I mentioned with the password file, perhaps your application doesn't need access to the password file. It shouldn't. So you want to make sure that you want to whitelist the areas of the application and different URLs that your application can access, so that somebody can't send an XML file that tries to make a request to either a malicious website or files that it shouldn't have access to. And then you want to make sure that you're using some of the scanning techniques that we've talked about before. Even penetration testing will uncover these issues as well. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about broken access control. So when we talk about access control, think of authorization. And we've spoken about authorization versus authentication in the past. But just remember that authentication is proving your identity, whereas authorization means what do I have access to? So it's a process where requests to access a resource should be granted or denied based on that individual. And as I mentioned before, one of the good examples of remembering the difference between authentication and authorization is that a driver's license provides authentication. It shows a picture, your name, your address, some other details about you. But that doesn't mean it's going to grant you access to something like a military base or a nuclear plant. So having a license provides authentication. It doesn't provide authorization. So access control enforces policy such that users cannot act outside of their intended permissions, and failures will lead to unauthorized information disclosure, modification or destruction of all data, or performing a business function outside of the limit of that user. So taking Amazon.com as an example, if I'm a general user at Amazon.com, I shouldn't, if Amazon didn't have proper access control in place and I was able to, say, elevate up to an admin level access, well, that's going to grant me a lot of access to information I otherwise would not have access to, maybe see things that I shouldn't be able to see, or perform activity that I shouldn't otherwise be able to perform. Access control weaknesses are commonly due to not having proper testing in place, automated detection, and not having testing within the development lifecycle. And then the technical impact is an attacker acting as a user or administrator, being able to elevate their privileges, creating, accessing, updating, or deleting every record. So in other words, again, as I mentioned before, if you're able to elevate your access to a higher privileged user, that's going to grant you a lot of latitude in being able to access information, modify it, delete it, or what have you. At that point, you're acting as an elevated user. So some of the common vulnerabilities around access control is bypassing checks by modifying the URL. So this is actually a very old way of, if you were on the internet browsing for cat pictures and you went to catpicture1.jpg, if you went up into the URL and changed it to 2.jpg, well, you went and saw the second picture. So this is a very common method of changing stuff that you're looking at on the internet. Now that's pretty harmless there, but if you're able to say on a web application change the account number in the URL to some other account number that's not yours, and it doesn't stop you from doing that, then that's a problem. Allowing the primary key to be changed to another user's record, like I just mentioned, if you're in the URL and perhaps the URL has your account number in there and you change it to a different value, that may be able to allow you to access information you shouldn't be able to. So elevation of privileges basically just means acting as a user without being logged in, or acting as an admin when logged in as a regular user. So just basically no control or no access control around a URL. And this could be perhaps somebody sends you or you're able to get a URL that perhaps goes to a bank site, and in that URL is a user's account number, and you're able to access that account even though you don't even have an account on that bank site. That would be obviously a big problem. Metadata manipulation, such as replaying or tampering with a JSON web token. We're going to talk about JOTs or JSON web tokens later on. An access token or a cookie. So again, being able to grab data like a cookie or a JOT or some other type of token, and being able to replay that as a different user, that's broken access control. CORS misconfiguration allows unauthorized API access. So this just basically means that if CORS is not properly configured to make sure that you're staying within the resources that are allowed, and that's basically what CORS comes down to, is locking in resources that you're allowed to make calls to. Then this will allow you to have access to unauthorized APIs. So forced browsing to authenticated pages as an unauthenticated user. So again, maybe you're logged in or you're not logged in, as going to Amazon as an example. If you're not logged in, you shouldn't be able to just browse to, say, your shopping cart, or even worse, somebody else's shopping cart without being logged in. So some of the preventions around access control. So aside from public resources on your website, make sure everything is denied by default. So in other words, nobody's allowed to have access to it unless they're authorized. So unless it's a public resource like your help page or something, or an FAQ that you don't really need to have access controls around, but certainly your admin functionality needs to be locked down. Shopping cart, all the other parts of your application need to be locked down. So by default, they should be configured to be locked down. So implement access control mechanisms once and reuse them throughout the application. And really that means sharing that access control functionality across your application, so that you're not implementing the same access controls in multiple different places. And the reason for that is that if you discover an issue with the way you're implementing access control, you only have to fix it in one place and not multiple places. Model access controls should enforce record ownership rather than accepting that the user can create, read, update, or delete any record. So this just basically means that that the user should be tied to a specific record and not be able to access any record within a database, for instance. And obviously, when you're talking about a web application, the user doesn't have direct access to the database, but you should have a concept of this record belongs to this user, and only that user is allowed to make the changes there. Disable web server directory listing and ensure file metadata and backup files are not present within web routes. So this basically just means that you shouldn't allow just open access to browse the directory that your application is running in without implementing access controls. You want to log access control failures, especially around admins when they're perhaps having access failures, because that might be an indication that an attack is occurring. You want to rate limit API and controller access to minimize the harm from automated attacks. So that's pretty self-explanatory, similar to what we talked about with like brute forcing and passwords. You want to have rate limits in place for things where they might potentially be under attack. JSON web tokens should be invalidated on the server side after logout. So, and not just with JSON web tokens, but just in session management in general. You want to make sure that when there's a logout event, that the user is that's invalidated on the server side once that user logs out. So here's an example, and this is very similar to what we talked about with SQL injection, but the application here uses unverified data in a SQL call that is accessing account information. So you see the statement here, and again, we can kind of recall what we talked about with SQL injection, but there's no checks on that parameter for account when it comes in. So an attacker can just basically change in the URL you see at the bottom there. Maybe their account number is 123. They can change it to 345, and maybe perhaps gain access to information that's not theirs if there's not proper access controls in place. And then another example here is, as I mentioned before, is just being able to change the URL in the browser. In this case, get app info. The first line there is presumably just for users, but there on the bottom, that's the admin functionality for that same page. A standard user shouldn't be able to just change it to admin _ get app info and be able to get there without having their access challenged. So with that, I hope you enjoyed this lesson, and I look forward to seeing you next time. Thank you. Welcome back, everyone. In this lesson, we're going to talk about broken authentication. So directly from OWASP, it states here, application functions related to authentication and session management are often not implemented correctly, allowing attackers to compromise passwords, keys, or session tokens, or to exploit other implementation flaws to assume other users' identities. What that really means is basically a breakdown in the authentication mechanism that allows someone to pose as a different user. So how does this happen? Well, sometimes this happens because developers develop custom authentication mechanisms that just don't work. And really, you see here at the bottom, it's kind of reiterated here that building authentication and session management is difficult, and to do it correctly is even more difficult, and to do it securely is even more difficult. So building these types of functions into an application is not easy to get it right and to get it secure. So as a result of some of these custom schemes, there's flaws in areas like the logout functionality, password management, timeout, remember me, secret questions, account updates, all of these different areas within an application where somebody has the ability to modify or maintain some information about their authentication poses a possible security issue. And sometimes finding these flaws are difficult because a lot of times the implementation for the authentication mechanisms are unique per application. So there's not a standard way of trying to uncover authentication issues. So how can authentication be broken? Missing authentication, just flat out not having authentication, to access a web application or certain parts of the web application. You may have an authentication or login page for you to log into the main page, and then from there never check authentication again. That would be broken or missing authentication. Poor credential strength, so maybe locking your users into only using 6-character password and saying you can't accept any more. That's pretty bad security practices. Not managing those credentials once you have them, not encrypting them, not hashing them, not storing them in the correct location, or worse, keeping them in plain text, especially passwords, can be problematic. Poor account recovery practices. So for example, using secret questions with answers that can be easily social engineered via the internet. So for those of us that are on social media, it may be easy to know what high school you graduated from, or what's your dog's name, or things like that. That kind of information can be sometimes readily available on the internet. And then last point here is unlimited attempts, and this isn't like everything that can break authentication. This is just some sampling here, but unlimited attempts to authenticate. That's obviously an issue too, because that allows somebody to do brute forcing. So some of the attacks. So for social engineering, this is a legitimate attack. Somebody from IT or somebody that's posing from IT may call you and say, hey, we're having a production issue. We desperately need to get in access to the server. You're the only one that has the credentials for it. Can you please share it to us? The CEO is upset, and it basically a typical social engineering attack, which plays upon people's need to or desire to be helpful, and not only that, but to put them under pressure to respond quickly. So you see that those types of attacks actually happen, and they work. Dictionary attacks, brute force attacks, we'll talk about them when we get into password management and hashing and encryption later on. But this is basically the brute forcing, trying multiple types of combinations to gain access to an application to get through the authentication. Username enumeration, so this is guessable patterns of usernames or login failure messages that reveal too much. So we may all be familiar with the fact that if you go to a login page and you type in the wrong credentials, typically it's going to come back and say login failed. It's not going to say username incorrect, or it's not going to say password incorrect. It's just going to say login fail. For sites, that's more commonplace now, but it wasn't that way a few years ago, where you could get messages come back say you got your username right, but the password's wrong. That's a lot of information for an attacker that's trying to gain access to a system. And then of course phishing, where similar to the social engineering, could be a link that gets sent to you that maybe you click on the link and it looks like your company portal with a login page, and you go ahead and type in your credentials, and maybe it's actually a malicious attacker's own site. So there's issues around the account recovery as well. Emailing a password reset form without using something like two-factor authentication, or again, the easily guessable security questions that may be found through social media. Email or passwords being sent through insecure channels like email. Another point about that is that no site should ever be able to send you your password, and we're going to get to that when we talk again about hashing later on. But if a website is able to send you your password in email, that means that they know what your password is. The bottom line is that nobody should know your password except for you. So that's a problem. But furthermore, if they do have your password and they're able to send it to you in plain text, that should not be coming through email. And then things like where a password change isn't required. There's a lot of different schools of thought on this around how frequently you should be changing your passwords. But at the very least, there should be some policy in place to enforce a policy that states that you should change your password at least when the account is first set up. You need to change that on the very next logon. And with that, I appreciate your time, and I look forward to speaking to you next time. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over injection. So what is injection? Well, it's any time a user is able to influence the behavior of an application based on input that they've provided. So there's a lot of different types of injections, or several different types of injection. One we've been talking a lot about is the query type injection, so things like SQL injection. There's also other types of query types of injections like LDAP and XPath. Other injection types are like OS command and HTTP redirects. So how does injection happen? Well, it's basically not trusting or having a high level of trust in the user input and not validating or, as it says here, sanitizing the input. So you want to make sure that if you're expecting certain input, that's what you're getting. If you're expecting a phone number and you get script in a text box, well, that's a problem. Also, it happens when there's no separation of that untrusted data versus trusted data. So, for instance, just again having a high level of trust of the input that comes in, and not really providing any kind of separation from your critical data or your more trusted data. So, what is SQL injection? Well, we've shown a little bit about SQL injection when we were going over things like WebGoat. But basically, it allows an attacker to manipulate a SQL query and potentially execute it in an application. So it exploits inadequate validation and sanitization. Again, if you're expecting a phone number and someone injects a SQL command, that's a problem. And some of the impacts of SQL injection, pretty much anything you can do in SQL, and for those that are familiar with database writing SQL, you know that there's a lot of opportunity there for data to be stolen, for data to be corrupted, data to like drop tables. So there's a lot of different ways of potentially getting to data, manipulating data, or erasing data. And a lot of times that could be very critical data, and it could be a very critical issue with the application. So basic SQL example, and again, we showed some of this when we were going over WebGoat, but as we know, 1 equals 1 is always going to evaluate to true. So in this case, in the text box, you see 105 or 1 equals 1, and again, since we know 1 equals 1 equals true, or is true, this statement basically says that the value can be either 105 or true, and based on that logic, it's always going to evaluate to being true. So here's an example of a login page where, again, A equals A is going to always evaluate to true. It's just another way of writing 1 equals 1. And so in the user ID here, and you can see the SQL statement below too, but in the user ID we put in foo, which basically doesn't really matter what the user ID is here, or true. So again, it's saying my user ID can either be foo or true, and in this case, true is always going to win. The hash tag at the end there, and some of you that are very familiar with SQL will know that is a way to comment out the remaining statement. So in this case, we know that if we know what the SQL statement is, this more or less says I don't need my username can be anything, and I don't need a password because I commented out the password validation in the SQL statement. It runs, it executes, and the question there at the bottom, do I need a password? The answer is no. So this isn't going away anytime soon. Most recently there was injection attacks with. It was a very academic style of attack, but there was a proof of concept where an attacker was able to provide voice commands to Alexa and gain access to data in the back-end database that Alexa was plugged into. So again, there was a proof of concept using voice commands, using Alexa, and this was a high-profile type of example, but there are a lot of more common and up-to-date examples of SQL injection. It's not going away. It's not an old problem. So here's an example of some bad coding habits in terms of SQL injection. So one thing that should be a surefire trigger if you're looking at code that code could be susceptible to SQL injection is if it's concatenating a SQL statement. So you see here on line 4, it says string query, and then you see that it's concatenating together a SQL statement. The problem here is that it's getting the data from the request. So it says get parameter in line 1 and 2. It's getting the parameter, user, and password, and then concatenating that into that SQL string to create a SQL statement. Well, the issue there is that, number one, there's no validation of the user information that's coming in from that request. Same thing with the password. And then it's just appending that into the SQL statement. So that allows us to be able, or allows an attacker to be able to inject their own user or password data there that could be SQL. So in the example, the input is Adam single quote dash dash. Again, dash dash, depending on the SQL technology you're using, is a way to comment out the remaining statement. So in this case, you put in your username Adam. hopefully it matches to a username that's in there, and then you don't need a password to log in because you commented out the remaining SQL statement. So again here, same thing, just a similar example of this, where instead you use an input A or 1 equals 1 and then comment out the rest. And that's an example of what we shown earlier, where you don't, 1 equals 1 is always going to evaluate the true. So in this case, you don't need a username. You comment out the password validation. You don't need a password. You don't need username or password in this case. So here's another example where in the input field, I'm putting in a single quote, end the statement, start another statement called delete, or type in delete from username, and then do a select. And I think that's a bit of a typo. It should be delete from user, because as you see at the bottom there, in the bottom where it shows the actual statements that are being executed. But basically here, it's doing a select on the username A that I put in, and then in the statement after that, it's actually going to delete from users, which is going to basically delete all the information in the user table. And then you're just going to do a validation to check to see whether that actually deleted everything out. So in this case, you're getting rid of all the users in the user database, which is bad. And then one last example here is the ability to be able to execute commands. Now, SQL Server used to allow this. I believe they've disallowed that so far, or more recently in the past couple of years, because there was a lot of issues with this, where you could inject an execute command within a SQL statement to go on the server that the SQL database is running, and actually execute commands like shell commands. So that's probably not what you want, especially if you have a SQL injection issue. You don't want people being able to execute commands on that box or on that host that the SQL server is actually running on. So here's an example of just doing an exec master XP command shell, and then doing a directory listing, which should actually spit out the directory that that this is executing in. So again, it's not what you want, the behavior that you want. Again, SQL Server, I believe this only impacted SQL Server, but SQL Server did get rid of this in the past couple of years, or at least you can still do it, but you have to enable it. I believe it's disabled by default. So what are some of the preventions, specifically around SQL injection? Well, as we showed, concatenating strings to create a SQL query is not the ideal method for querying your database. Writing parameterized queries, for those that are familiar with writing in SQL and creating prepared statements, stored procedures, or parameterized queries, that's the recommended method. And the reason for that is that it allows you to strongly type your variables and making sure that things are executed in the way that you want, and not susceptible to injection. The parameterized queries are different in every language, so you need to obviously know what language you're programming in and how those are created. And you should be using whitelist in terms of the parameters that you're expecting to get in. You want to make sure, as we talked about before with secure misconfiguration, is that you want to make sure that your SQL database is configured to in the most secure manner, so that, for the example, don't allow it to execute commands on the host. You want to make sure that you have your actual instances of the database properly segregated, and so forth. And again, it's going to depend on the SQL technology that you're using, but you want to make sure that you have the most secure type of settings possible to make sure that there's no issues there. So here's an example of a prepared statement where, in this case, you are creating a prepared statement. You're getting a set string, or you're taking the username and the password as a set string, and then you're actually executing that query. But it's not a concatenated type of statement that you're just passing to the SQL object in order to execute. So in this case, because you have set string, you're able to make sure that that you have a strongly typed input for the user ID and password. So as I mentioned before, there's other injection type of flaws. There's OS command, which we'll show here in a little bit, and then there's LDAP and XPath. So with OS injection, this is basically for a given script or batch file or executable that takes parameters, and most executables do. If you're familiar with creating scripts or executables, in order to execute them, a lot of them will take parameters in as an expected input. So in that case, again, similar to what we've seen with SQL injection, you want to make sure that you're scrubbing those inputs when they come in. Otherwise, you're possibly opening yourself up to hear this type of an attack. So here you see this cat wrapper, and the input that it's taking is the story.txt. And you can see here in the code that there's no scrubbing of the input coming in. It's just taking whatever information is coming in and concatenating it. So in this case, we're going to execute that cat wrapper. We're going to input story.txt, but we're also going to input ls, which means list in Windows. So you're going to see here that it starts to output the text that's in that story.txt, which it says when last we left our heroes, and then immediately after that, it's going to execute that ls, and here you see it's going to spit out the values or the files within that directory that it's executing in. So in this case, we're going to look at an XPath injection style attack. And for those that aren't familiar, XML is a way of organizing data similar to a database in a flat file format. In this case, presumably there's a login function that is reaching back into an XML file to validate whether the user is correct or not. So we're going to go ahead and show here in the what we're going to input here in the username and password. If you see that down there at the bottom left, it shows blah or 1 equals 1 or a equals a, and then password is going to be blah. And basically what this means is you can see here on the right, it says logically this is equivalent to, and then it shows employee username blah or 1 equals 1, which we know is true, or a equals a, and password equals text. So both the username and the password lookup is both going to evaluate to being true, because 1 equals 1 and a equals a both evaluate to true. So in other words, it's basically more or less just bypasses the username password lookup. So with LDAP injection, lightweight directory access protocol, for those that aren't familiar, LDAP is a way to access user information from a directory service. And similar to the other types of attacks, this is users being able to influence that lookup. So LDAP runs over internet transport protocols such as TCP. Web applications may use user-supplied input to create custom LDAP. So in other words, it may request information from the user in order to do a more fine-grained type of lookup. So when an attacker is able to modify LDAP statement, the process will run with the same permissions as the component that executes the command. And again, this is very similar to some of the other types of injection attacks that we've seen. So here's an example where in the URL it says example HTTP example / default ASPX, and then there's a user equals, so that's a parameter. And if we, in this case, are able to send a star character in the user parameter, that will create the filter basically on the LDAP lookup for the SAM account name. So this will result with the server return any object that contains the SAM account name attribute. So presumably that's going to be every account that's in that directory service. So again, this is just an example, and we've shown before with Fiddler that there is the ability to pause a request coming from a browser and be able to change the parameters being sent. So if the server side is not validating that the user characters that are being sent in are valid characters, then it's susceptible to this type of an attack. So when we talk about testing for input, especially injection types of attacks, input unexpected data into all parameters. So you want to make sure this is sort of along the lines of something called fuzzing, where you want to be able to just basically input a lot of different text into an input field and make sure that it's properly handling all that input. Another way of testing is just do the simple check of put a single quote, and if it doesn't throw an error that you would expect to see, and instead potentially executes or doesn't give you an error, then that means that it's potentially susceptible to SQL injection. You want to make sure you're checking all the parameters that are being sent. So again, not just on the client side, but on the server side. You want to use automated code review tools like static analysis, dynamic analysis, and also penetration testing obviously is going to be able to uncover a lot of these issues. So some of the defenses, never trust user input. If you learn nothing from this course, you always want to make sure that you have a healthy distrust for your users and the way that they're using your application. You want to make sure you scrub in all the inputs, that it's properly encoded, that it's that you're properly checking for boundaries, and that the character set is what you're expecting. You want to whitelist expected parameters. So again, if you are looking for phone numbers, then you know the size, and you know you're looking for numbers. So you shouldn't be getting a 20 character alpha, or 20 alpha characters. You should be getting, depending on where you're at, 10 or so digits. So things like that, you want to make sure that you're locking in the expectation of what those parameters should actually have. And as I mentioned, with especially around SQL statements, you want to make sure you're using prepared statements and not concatenating strings in order to create your SQL queries. So with that, I hope you enjoyed this lesson, and I look forward to talking to you again later. Thank you. Welcome back, everyone. In this lesson, we're going to talk about cross-site scripting. So cross-site scripting is a security vulnerability that allows attackers to inject scripts into an application. So very similar to what we've been talking about with the other types of injection attacks, specifically like SQL injection, where the lack of user input, validation, sanitization leads to this type of an attack. It can lead to bypassing of controls, gaining access to information that the attacker should otherwise not have access to, elevating privileges, and so forth. There's a lot of different types of ways that an attacker can leverage cross-site scripting to get up to malicious types of attacks. So there's two types of cross-site scripting attacks. The first one we're going to talk about is reflective, and this is when an attacker is able to append script to a URL that is basically reflected back to the end user. Some simple examples of this is basically being able to get like an alert, a JavaScript alert to pop up. But obviously there's other ways of doing, or other things that can be done with reflective types of attacks. So a malicious attacker can craft a URL, send it to a user, and say, hey, click on this link. And obviously, it's not that overt. Typically, it's done in a way to get the user to actually click on the link. So you might see a spoofed email that looks like it's coming from PayPal or Amazon or something like that, and it's going to get you to click on the link. But in reality, there's a script that's embedded into that link that's able to then do something nefarious on the end website. And it could do things like steal passwords, credit card numbers, account information, depending on where you're going, the site that's susceptible to it. So here's an example. An attacker finds a cross-site scripting issue on a website. So the attacker will then craft a URL that will work on the site and will send the unsuspecting user an email that says, again, we've all probably seen these types of emails. I know I get them frequently from like PayPal or Netflix or Amazon or Apple, and I don't even have Apple devices, that say, hey, your account's been flagged as something going on. You need to act immediately, or otherwise your account's gonna be shut down. Click here to go fix your issue. And so the attacker will craft an email like that, and looks very looks very convincing, but the URL that's in there is specially designed to have script execute once it gets to that site. So for instance, if in this case, where the banking site is the ultimate goal of the attacker to gain data, access, information from that banking site, specifically around that user. If the banking site is susceptible to cross-site scripting, the attacker is going to create that URL, put it in an email, send it to the user, and when the user goes to that banking site and logs in or accesses their account, If they're susceptible to cross-site scripting, the attacker more or less has the ability to gain information about that user, specifically at that banking site. So it could be stealing cookies and maybe replaying the user's logged in session. Maybe it's scraping the screen to get information like a bank account number and so forth, or just gaining just general information about the user. But so that in a nutshell is how a reflected type of cross-site scripting attack would work. So here's an example of a phishing attack using cross-site scripting. And this is a pretty convincing email. So it shows here Google security team. So, makes you want to sit up in your seat a little bit and pay attention. It says, thank you for your note. I read the hacker news regularly. So you must have, this email must have came to this user, maybe not, that they submitted some kind of note or information to the Google security team. So it says here, we took a look, it seems like cross-site scripting you reported actually executes on one of our sandbox domains, and it goes on to say, for more information about sandbox domains and vulnerability rewards, click here and get some more information on that. But if you look in the link there down at the bottom right, you can actually see where it's creating a script. So in that second line, you can see it's encoded. It says script and then document write, iframe, source. So it's basically writing out a little HTML in a iframe. So you're probably not going to see it once it runs. But it looks pretty. Again, the email itself looks pretty convincing when you hover over that link and see that. If you're paying close attention, you might pick out there that this is a script about to execute. But unless you're hovering over that link and seeing that, it's unlikely that you're going to notice that you've clicked on a link that allows for cross-site scripting and potentially stealing data that you obviously don't want to have stolen. So another type of cross-site scripting is what we call persistent, and this is basically, because of the name, as the name suggests, it's a stored vulnerability. And this means that if I'm a malicious attacker and I go to a site and the site is susceptible to cross-site scripting to a point where I can store that into a database where it can then be reused multiple times, that's a more devastating type of attack. So a good example of this is message boards, product review sites. So you think about Amazon, where you're allowed to leave a product review. If I'm not saying that Amazon is, but if you're able to inject script into one of those review boxes, then that'll get stored into the database and potentially reused later on. So an example here is, the attacker identifies a vulnerable website. Let's say it's some product review website that allows for reviews to be submitted. And the attacker knows that site is susceptible to cross-site scripting. So they go there, they leave a review with script. The script then gets stored, processed by the web server. The script then gets stored into the database server. And then any user, so this is more of a shotgun approach as opposed to a more targeted approach. Any user that goes and views that review, depending on how that script is created and what its plans are, any user that goes to that and browses to see that review will then have that script execute. So again, it's more of a scattershot type of attack. Depending on what you're trying to get there, maybe you're trying to get credentials for the user, or maybe you're trying to get not credentials but session information about the user. Maybe you're able to leverage that to do more devastating attacks down the road. So again, think of the persistent as less targeted, more scattershot, but it means a wider audience, so more opportunity there. So with that, I hope you enjoyed this lesson, and I look forward to talking to you again. Thank you. Hey everyone, welcome back, and in this lesson we're going to go over using known vulnerable components. So when we talk about components, we're also thinking about things like dependencies. So what is a dependency? In broad software engineering terms, it's used to refer to when a piece of software relies on another one. So for those that program in any higher level language, you're typically pulling in libraries from other locations. They're not all the code's not written by you. You're pulling in libraries and components from other areas for things like math functionality or security components, other different things that you use to build your overall software, but it's not developed by you. So that's a dependency. So there's two different types of dependencies. There's a direct dependency and there's a transient dependency. So a direct dependency is one that your library, or that's called explicitly by your code. So that could be a library or an API or any software component that's referenced directly by your application. A transitive dependency is one that's dependent upon, or it's actually pulled in from a dependency. So you can think of it as more of a chain. So it's a functional dependency which holds by virtue of transitivity among various software components. So basically it's something that's not necessarily called directly by your application, but maybe it's called indirectly by the components that you're pulling into your application, or it's something that's pulled at runtime even. So you can think of transitive as being something that's not directly called by your program. So the term components in this category refers to application frameworks, libraries, other software modules, again, like APIs, other things that you call to create the overall application that you end up delivering. And so this category references using these components when they may have malicious code or security weaknesses within them, in other words, a vulnerability. So when we're talking about components with known vulnerabilities, we're talking about when you make those direct calls to other libraries or components. Those other libraries or components may have vulnerabilities in them. So that's what using known vulnerable components refers to. So here's an example of calling a component here in Java and C Sharp. Again, if you're familiar with any higher level programming, object-oriented, you're going to see something similar to this where you may be referencing a DLL, or you may be just calling in a library in the top of your C# file or C++, whatever higher level language that you're writing in. So when we're talking about defenses, we're going to talk a little bit more about some other types of defenses in a bit. But when we're talking about defenses here, most applications include some type of way of getting vulnerability information about their products. So for instance, if Oracle, Google, IBM, Microsoft, any of the big players, or even some of the smaller players in this space that develop software that gets used by other products, they're going to make sure that they have a means of patching that software when something goes wrong. So we're all familiar with Microsoft's Patch Tuesday. That's Microsoft pushing out security patches or feature patches to their products. So that's one way of thinking about how you get security patches for any of the libraries that you may be pulling into your application. Things like, again, Java, Oracle, Microsoft, IBM, or any of the other software that you may be packaging in with your product. Chances are there's going to be patches that are going to be pushed out occasionally. You need to have the means to be able to upgrade, because that's what's going to really entail, is upgrading that library to the latest level that doesn't have the security vulnerability in it. So a lot of these different companies that produce these third-party components do have the ability to notify you either through direct contact or through some kind of feed. So whether it's could also just be through email. But typically there's a way to reach out to the user base to let them know, hey, there's a vulnerability in this product. You need to upgrade to version XYZ in order to mitigate this vulnerability. So for OSS, open source software, there's different types of products out there that do scans. So one we'll take a look here in a little bit is called Dependency Check, and it's a OWASP product. There's Bundler Audit. There's GitHub offers some options for scanning libraries. There's a lot of different products out there that do open source software scans. And a lot of them, the kind of commonality between all of them is that they typically will go out and look at the NVD, the National Vulnerability Database. And there is where you'll be able to find information related to any of the CVEs that come out, and that list is constantly updated. So what happens is if somebody says, like Microsoft for instance says there's a vulnerability in one of our libraries, they will go get a CVE, and we've talked about CVEs in the past. Those CVEs will be posted to the National Vulnerability Database, the NVD. And then a lot of these open source products will go out and look at the MDD for that version of software that you're packaging in your program, and determine whether there's been a known vulnerability in that package. If it has, it's going to tell you, hey, I found something that you need to be aware of. So that's how a lot of these typically work. Some of them are smarter than others. Dependency check is free, and it's a pretty simple scan of your build, and then a lookup in MVD. So it's pretty straightforward. So some of the general defenses, other than signing up for notifications and using something like dependency check, some of the other general defenses around open source or components, using bundling components in your application is, make sure you're not giving extreme trust to those third parties for a number of reasons. It may not necessarily be security, but you may also be having privacy concerns as well. Always verify the size and the checksum. So when you get a library from a third party, you want to make sure that it hasn't been tampered with. And to do that, you use something like checksums, integrity check, and also make sure that the size, hasn't changed. And you want to do that in an automated way. You want to challenge the vendor to provide some evidence of security vulnerability scanning. Some vendors will do that, not all of them, but you do want to make sure that they're at least doing their due diligence from a security perspective. A lot of them will turn over that information when they're asked. Use well-known vendors that are maintained. That's another good practice in terms of security, because you may find a library that fits your needs, but it may not have been updated for the past couple years, and it looks like it might be abandoned. Well, that might not be great, because that means it's not getting security updates. And then, if possible, scan the code yourself, and that's always a possibility. So, depending on the software that you're using, that should be a possibility. So something else that plays into this open source software and using components that may have vulnerabilities is the ability to be able to do patching and notifications. So when we talk about notifications, you want to make sure that you have the means to get notifications. So companies like Microsoft, Oracle, IBM, and so forth, they're going to have the ability to send notifications to those that signed up for those notifications. And more importantly, getting the notification isn't the last step. You want to make sure that you have the ability to do something about it. So once you get that notification, you want to know where you're using that level of software that's potentially vulnerable. You want to have the ability to test that patch before you deliver it to a production system. And then you want to have the means to be able to deliver it once you have the testing completed. So there's more to it than just getting the notification. You want to make sure that you are able to act upon that notification once you get it. And then again, like I mentioned, with in terms of the patching, you want to make sure that you first take that patch in your development lifecycle, make sure that that it works, number one, and that it works with your program or your application that you're writing. And then you want to push it to a pre-prod environment, and then lastly out into production. And with that, I hope you enjoyed this lesson, and look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to install ZAP or Z Attack Proxy, which is managed by OWASP. So you see here, if you go to the URL for OWASP ZAP, you'll find the download and additional information for it. So we're going to go ahead and download the file. And you'll notice here there's a couple different installers for Windows, Linux, Mac. What we're going to do, since I'm running Ubuntu, I'm going to install the Linux or run the Linux installer. It's basically going to download a shell script, so that's the installer. Once that installer is downloaded, I'm going to go ahead and change model on it in order to execute. Oops. And then I'm going to go ahead and run the script. And this will fire up the installer. And of course you have to be running as root, so sudo Try that again. Okay, so the installer is going to go ahead and rip. I'm going to take the defaults on this, and just for some backstory here on Zap is that it's what we consider a dynamic scanner. You can put into a URL and do a security test of it. So it's a nice tool to have to check the security of a online website. Okay, I'm going to go ahead and fire it up. Well, I'm doing that now. As mentioned, you can point this to a website and run it. The one thing you want to make sure that you are not doing is using this against a public website. You could get in trouble for that. So typically you want to use this against your local application to test for security issues, unless you have permission to point this at a public site. But in most cases, you're not. I mean, you're essentially hacking or trying to hack another site. So I'm going to not store my session here. That's typically what I do. And here we are. Zap is loaded. Welcome back, everyone. In this lesson, we are going to show an example of scanning WebGoat using OWASP Zap. So here we are in Zap, and I have WebGoat up and running over here. I'm going to go ahead and log in. And what we should hopefully see here is that Zap has picked up that WebGoat's up and running, and it has. So the first thing we're going to do is actually crawl the site, and what that's going to do is, or spider the site. Some people call it crawling, some people call it spidering. Zap refers to it as spider. So we're going to actually spider the site here, and what that's going to do is grab all the information about the site. So all the different pages and folders that are visible to the site. So you can see there that happens pretty quickly, and you can see it populating more information related to the website. So with that, we're going to go ahead and start. We're going to start creating a context. So first thing I'm going to do is do an include in context with the login page, and the context is really just a way of organizing the site for further attacks. So create a new context here. And you see here it says login. It's included in this context, and there's a default one that gets created that picks up basically background requests that Zap is proxying. So the first thing we're going to do here is go to the authentication. WebGoat uses form-based, so a username, password. We're going to include the login page, the post. Say select there. It's going to automatically populate the information, and make sure that's selected as username. For users, I'm going to add the user ID. Oops. Okay, let's say add. So I have a user added here. Go back to authentication, got all my information here. And I've seen other sites mention doing this, so I'm going to go ahead and add, basically, they recommend adding this title as part of the regex for finding the logout page. So down here at the bottom for regex pattern identified in logout response message. So basically, if it sees this in the response, then it knows it's the login page. So with that, we have our authentication. We added our user. Got the logout response here. I'm gonna say OK. Context should be created up here. And the only thing I didn't do here is actually rename it. So I'm going to go ahead and open that up again. Just give it a name that makes a little bit of sense. Okay, say WebGoat. I'm going to actually add the context root included in context for WebGoat. Okay, so now that's going to be added as well. You see the login page, you see WebGoat. Say OK. All right, we're almost ready to do the attack here. The last thing we want to do is do a forced user mode. Say yes. All right, and now we are ready to perform an attack. So we're going to do an active scan here. And I'm going to be able to choose my user. Okay. And the one thing you'll notice here is, for sake of speed, we'll take take basically the regular options here, and you can feel free, if you do these attacks against WebGoat, to go ahead and pick, go through and figure out what makes the most amount of sense. But what I'm just going to take basically a standard stuff here and just do a scan, again, just for sake of time. This should only take a few moments, but in the meantime, you can see here that it's just, these are the requests that are being made, and you can see the progression here. One thing that's interesting is that if you open up this little heartbeat icon here, it'll actually show you the progress of the scan. You can see the requests that are being made, the type of attack that's being leveraged, and potential alerts that come out of that potential or that attack that's actually occurring at the time. Again, since we took kind of the defaults, I don't expect to see a lot coming out of this, but I guess we'll find out. So for the sake of time, what I'll do is I will go ahead and let this run and pause the video for a little bit. All right, everyone, so we're back. The scan has completed. You can see here it's about 6 minutes long. Not really surprised, didn't find a lot of stuff. Did find 4 issues, so that's good. So what you can do is, once those issues have been identified, is that you can come over here to the alerts. And you'll see here there was 2 SQL injection type of attacks, and then you can sort of dig into them here on the, sorry, I'm trying to expand that. There we go. You can dig in, SQL injection may be possible. It'll give you information about the SQL injection, and more importantly, provide you a solution to how to protect against this. But it does show you the URL, does give you the attack that it attempted there. So this is the SQL injection that we've seen before. Gives you the CWE for common weakness enumeration, and then gives you a confidence of medium, meaning that it's pretty confident, maybe not highly confident, but it's good chance that this is a true positive. And then it also shows the risk, which is high, and we know that SQL injections can be devastating. So, and then you can go through and you can see the rest of the types of issues that were found. They are going to be rated by criticality or risk, but that's pretty much, without the super deluxe settings that you can set on an attack. We got a handful of issues here that we can try to tackle. Now, again, if you want to rerun this scan and crank up the types of attack, so if you go to scope, or I'm sorry, if you go to input vectors, and if you tag these additional items, it says here it could slow down the testing. It does. It could take hours sometimes, depending on your system, depending on the site. You can do that, and you'll get a more robust reading out of the website. But we don't need to do that just to show this example here. So with that, I hope you enjoyed this lesson, and look forward to seeing you in the next one. Thank you. Welcome back, everyone. In this lesson, we're going to go over CSP, or Content Security Policy. So content security policy is an added layer of security that helps protect against cross-site scripting and injection type of attacks. You need to configure this on the server side, and there's no compatibility issues. For instance, if the browser doesn't support it, it's not a problem. If the web server is not sending a content security policy, it's not a big deal. So there's no compatibility issues there. So CSP makes it possible for server administrators to reduce or eliminate the vectors by which cross-site scripting can occur by specifying the domains in that content security policy that are allowed to be executed by the browser. So a CSP compatible browser will then only execute scripts loaded in source files that are specified by that content security policy, or in other words, whitelisted. You can have basically the ultimate protection by disallowing all scripts to be executed. But for those that may have dabbled with plugins that disable scripts across a site or across your browser, you'll realize really quickly that running any kind of web pages without script is pretty much useless. So a policy is described using a series of directives. We're going to show some examples of that here in a moment. And those directives are going to show the certain resource types that are allowed within that policy area. So your policy should include a default source policy directive, which is a fallback for other resources. So if one's not specified, it's going to use the default source as the default. You also need to include a default source or script directive to prevent inline scripts from running, as well as blocking use of eval, so the JavaScript eval function. And then lastly, default source or a style source directive needs to be set in order to restrict inline styles from being applied from a style element or style attribute. So here's some examples of some of the directives that are available in CSP version 1. So you see the connect source, image source, media source, and these are all basically where you can set those elements to only execute from the domains that you specify. Same with script and style, and then your default, of course. And then in CSP2 2.0, there's some additional directives that have been included. So form actions, frame ancestors, base URI, child source. So again, all of these enable you to tell the browser where and how for those particular elements that they're allowed to access. So here's a sample of a content security policy. This policy allows image scripts, AJAX, and CSS from the same origin and does not allow any other resource to load. So you see here the content security policy, the default is none. Script source is self, connect source is self, image source is self, and style is self. So in other words, don't load from anywhere else except for this domain. And then the default says none. Basically, I'm not setting anything there. Take what's, in other words, don't load anything except outside of the ones I specified there in the script, connect, image, and style. So here's additionally, you're able to generate a report that can be sent to a URI that you specify. So it'll tell you if something has happened, a violation to your CSP. And here's an example of what's in that report. So you see down towards the bottom there, it blocked a URI that wasn't part of the CSP policy. And it says the violated directive was style. So it looks like it was trying to load a style sheet from cdn.example.com. And apparently that wasn't part of the policy. So therefore it's presenting this report saying this policy was violated, here's how it was violated, and here's what it was trying to do. So it's very helpful if you're trying to understand because maybe you need to tune your policy to allow certain domains. Maybe this domain does make sense and you want to allow it. So this report will allow you to make those adjustments. And with that, I appreciate your time and look forward to speaking to you next time. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over a demo of Content Security Policy, or CSP. And if you recall, Content Security Policy is a way for a web application to be more secure by limiting where the web application is allowed to load things like script, style sheets, and other URLs that it's allowed to access. So the first thing I'm going to do here is enable Fiddler. I'm going to show you two different ways of doing this. The first way is the hard way. The second way is the easy way. So I'm going to go ahead and turn Fiddler on. I'm going to bounce over to my browser here, and let's go browse to facebook.com. And so let's go back over to Fiddler here. And we've been capturing, and so if you recall with Fiddler, it's a proxy tool, so it's capturing data between a client and a server, and it's really capturing that request and response. So up here you see this is the actual request, and down below is the response that came back from the server. So what we really want to look here at is this content security policy that was returned by the server. So let's open it up in a browser so it's a little bit easier to see here. And I'll just create some separation just to kind of allow us to take a look. So here you see the content security policy. You can read through it here with the default source, script source, and so forth. And if you recall, these are different parameters that are available for content security policy. Again, this is the harder way of looking at it. So let's make a little bit easier way to take a look at this. I'm going to shut down Fiddler here. And if I go over to CSP Evaluator, so CSP-evaluator with google.com. And what I've done is I've already browsed over to Facebook, and just so you see that there's nothing up my sleeve, we'll do that again. Check CSP, and you'll see it's in a much nicer format. Gives you some good indication of where things may be need a little bit more security, where perhaps the security is pretty strong, and so forth. So looking at the actual content security policy came down here. So if you see default source, data and blob is isolated to itself. Data is just basically the data that can be loaded. Blob is a form of data. Could be an array, could be an object, could be multiple different things. You see here script source allows from star.facebook.com, star.facebookcdn.net, and so forth. And you can see all the different URLs or domains that are allowed to load scripts for Facebook. Style source, you see here, data blob, unsafe inline, which was interesting. So I bounced over here to look at what unsafe inline means. And it says here, allows the use of inline resources such as inline script elements, JavaScript URLs, inline event handlers, and inline style elements. The single quotes are required. So we're going to come over here to the CSP Evaluator, CSP-evaluator with google.com. And make it easier, we're just going to punch in facebook.com and do a check CSP. And what you're going to see here is a much cleaner format to the CSP, and it's also going to give you some additional information down below about maybe some issues that are considered high severity or some medium and so forth. So you see the default source has some concerns there. Default source should not allow asterisk as source. Data URI and default source allows for the execution of unsafe scripts, so it's a little bit concerning. And then additionally, here's some information around the script source where the policy may be maybe not as strong as it could be. And as you may recall, the different items that we have available within this content security policy here: default source, script source, style source, connect source. And you can see here that default source allows for loading of self, and that's your default posture that you want for data and blobs. And data is could be files, blobs could be an array or other types of objects. Script source, no surprise here, is allowing from Facebook, the CDN, other iterations of Facebook. And then style source here, you see some additional parameters here. This unsafe inline, I wasn't sure about, so I went actually and checked here. It says allows the use of inline resources such as inline script elements, JavaScript URLs, inline event handlers, and inline style elements. A little surprised that was there like that, and I'm surprised it didn't get called out as a potential issue there, but I guess it's okay. And then here you can see the different connections that Facebook's allowed to make, and again, no big surprise about where some of those are. So this is pretty good in terms of being able to evaluate the security posture of content security policy. You can punch in any website that you want. And additionally, if you want to follow up some more information around what the different components of a CSP are, you can always go over here to Mozilla, where there's information related to the content security policy. And you can find all the different options there to make sense of it. So with that, I hope you enjoyed this lesson, and I look forward to speaking to you in the next one. Thank you. Hey folks, welcome back. And in this lesson, we're going to talk about security models. So a security model is really what we use to develop or enforce security principles. And security principles are what we've been talking about throughout this class, really protecting confidentiality, integrity, availability of data. So there's three different types of elements that are part of security models, and that's people, process, and technology. And not just in security, but you'll see that elsewhere in technology and business is using people, process, and technology to achieve some ends. So addressing a single element, as usual, like we've been talking about with defense in depth, is not going to be able to accomplish the goals that you're looking for. So for instance, if you're just going to focus on people and not process and technology, you're not going to ultimately get to a good secure posture. You're going to have some gaps. So again, similar to defense in depth, you want to make sure that you include not just people and process, but also technology, and make sure that you're using all three of those elements when you're developing a security model. So you see here in the diagram going to build an operating system, or this could be true for an application that you're building as well, but there's going to be some kind of framework that you're trying to tie back to. In this case, it might be NIST or ISO or FIPS, and you're going to use a security model to implement that framework. You're going to use a programming language, the technology part here, to develop that end product. And your end product here, in this case, could be an operating system, could be an application or an API or a microservice. It doesn't matter. But there's a clear line from the framework that you started from all the way to the end product, in this case, an operating system. And an access-based access control. It's also known as policy-based access control, and this is really a way for access rights being granted to users through use of policy, which combine attributes together. So basically, it's going to look to see maybe your system, maybe the fingerprint of your system, some of the software it's installed, where it's located, maybe some geolocation, the time of day when it's trying to access something. So this is basically very similar to something like an attribute-based access, where it's the system is making decisions on whether you can have access or not based on some level of understanding of the system and the context that it's running in. So let's talk a little bit about integrity models. So in the BIBA integrity model, this is where subjects may not corrupt data in a level ranked higher than the subject or be corrupted by data from a lower level. So the example that they give here is the example of a monk. So let's say the monk has a congregation. That monk can write a prayer book that can be read by the congregation, but it can't be read by the high priest. And the purpose there is so that you don't corrupt the line of thinking or the order above you. Likewise, the high priest can write something that can be read by the monk, but the monk cannot read something that's been written by somebody within this congregation. So it's a way of securing integrity from corruption upwards and making sure that data integrity is kept in place. So the Clark-Wilson model, this is instead of defining a formal state machine, the model defines each data item and allows modification through only a small set of programs. And basically this means that data can only be modified through a sanctioned method. So typically this is through a workflow or an application or a program. So this makes sure that, for instance, that you can't change data in a database out of band. Like you can't go in and modify the database natively. So that's kind of the Clark-Wilson model. So information flow models, we've talked about the data flow diagram and use case models, but the Brewer-Nash model, so this is Chinese wall, otherwise known as Chinese wall. This is technology can be employed to prevent access to data by conflicting groups. And basically the whole point is that you want to make sure that if you're working on a project, your group is working on a project. You don't want that project being influenced by maybe another team or another project. So you build technical controls around that to make sure that, for instance, code can't be added to your project from a different team within the same company, or maybe even outside of the company. So it's basically ensuring that that access to the data that's within your purview is not being modified outside of your group. And again, we talked about data flow diagrams in the past, especially when we were talking about threat models. So this is designed to document the storage, movement, and processing of data in the system. Use case models we talked about, and this is basically requirements from the behavioral perspective, provide a description of how the system utilizes data. So this is where you want to set up maybe some use cases that say, as a user, I want to be able to access XYZ function within the application. And then assurance models This is basically a level of confidence that software is free from vulnerabilities, either intentionally designed into the software or accidentally inserted at time during its life cycle. So in this case, we talk about vulnerabilities, but assurance is, when we talk about QA, we're talking about quality assurance. Quality assurance does have flavors of security in it, but primarily we're making sure from a QA perspective that the system behaves in a way that we intend it to behave in. So that's quality assurance. So think of assurance as making sure that the system is functioning the way it should be and that it's free from vulnerabilities. And with that, I hope you enjoyed this lesson, and I look forward to speaking to you in the next one. Thank you. Welcome back, everyone. In this lesson, we're going to go over OWASP dependency check and GitHub. So dependency check, as I mentioned in previous lesson, is a way of checking open source software and checking for vulnerable components being used in your application. So during build time, as I mentioned before, your program may be pulling in different direct dependencies or transitive dependencies, and dependency check is able to at least check those direct dependencies to make sure that none of them have vulnerabilities in them. So it's .NET and Java compatible. Actually, I believe they've added more languages recently. And it's used to scan libraries during that build process. So you would actually plug this in during your build process. So the dependencies, they're matched against the National Vulnerability Database, or the NVD. And basically it looks at the version of the software that you have bundled in your application, and it goes out to the NVD to check to see whether that version of software has any known vulnerabilities in it. If it does, it'll be reported, and this report can be generated and used to identify any of the dependencies, and also provide some level of mitigation for what you can do. Typically, it's a matter of just upgrading to the latest version of software to get rid of that security vulnerability. So the National Vulnerability Database, or the NVD, you can find the link here. It's nvd.nist.gov. It's a government repository of basically vulnerability information that's in SCAP format, which allows for automated lookups within the NVD. And so the NVD is going to include information around vulnerabilities that have been identified in the industry for lookups to make sure that any of the specifically for software that you may be bundling with your application, the NVD would contain that library with version information, vulnerable version information, and how to remediate that issue. And that's really what dependency check is doing, is going out there to the NVD, pulling that information and displaying it for you. So here, as a developer, you're going to be developing your software. You put it into a build technology like Jenkins or something like that. And if you're using Jenkins, it's going to go out and pull all the dependencies that you may have. Maybe it's open source dependencies. And dependency check, when it's plugged into this pipeline, is going to go out, look at the software that you're pulling in, and go out to the NVD and make a match and determine is the software that you're pulling into your build, are there any known vulnerabilities for that? And if so, it's going to provide a report for you back to the development team to say, here's what I found, and here's where the issues that are known, and here's how to remediate them. And in most cases, the remediation is to upload or upgrade to the latest version. So here's a sample report of dependency check, and you'll notice here there's a CPE, and that's basically, it's a structured naming scheme for the dependency. So it's a good way of normalizing that dependency name so that it's for faster lookup. But if you look at the dependency check report here, it's going to give you the dependency name, the CPE designation for that, and then severity information and so forth. And basically, this will allow you to take a quick look and say, this is a high severity, I need to fix this. What's my path forward? It's to upgrade to the latest version. So GitHub actually has security alerts as well. And I know they've kind of morphed this over time, but basically this works within GitHub. So it works with both private and public repos. Private repos need to request the access. You also must be using dependency graph within GitHub in order to enable this. It supports JavaScript, Ruby, Java, .NET, Python, and they're adding languages as they go. Each security alert includes a severity level and a link to the affected file in your project. So very similar to what we saw here with dependency check. So very similar to dependency check, GitHub will track these public vulnerabilities that have been broadcast out. They're going to scan on top of that. They're going to scan the public repos and do some combination of machine learning and human intervention to actually look to see whether there's things that haven't actually been reported. So it's a little bit more comprehensive than what dependency check does. And then when GitHub discovers or is notified of a new vulnerability, they identify the public repository and then they notify the affected they notify the owners of that repository of the affected vulnerability. So here's a quick example of what it looks like in dependency graph. As I mentioned before, in GitHub, you have to have dependency graph enabled. But it's basically going very similar to what you've seen in dependency check. And again, a lot of these tools operate the same way, where it's going to show you the in your build or in your repo, in this case, what file is affected, what the issue is, the criticality of that, and how to remediate it. So with that, I hope you enjoyed this lesson, and I look forward to speaking to you next time. Thank you. Hey everyone, welcome back. In this lesson, we're going to talk about the ASVS, or the Application Security Verification Standard. So the reason that the ASVS came about is that there's a lot of different interpretations with what the client is actually expecting for their end product. And a lot of times that's due to miscommunications. It's not really conveyed appropriately to all the different stakeholders. So this comic here is kind of a lighthearted look at the way that everyone interprets what the client is looking for, including the client. So there's a lot of, again, miscommunication around what is actually expected. The other reason that the ASVS came around is that testing can be difficult. So there's a lot of different ways of testing code, unit tests, system tests, integration tests, and so forth. And writing those test plans for those types of tests can be difficult. Without clear goals and guidance, the test plan can become very useless. And for those that have either written or have run test plans that have been written, unless it's very clear, it can be a difficult task. So the ASVS has a couple different levels. There's 3 levels, and the first level is reserved for applications that are considered not critical, doesn't have sensitive data, so therefore it's kind of lower in the risk category. Level 2 is more for applications that have some sensitive data, and it's mostly reserved for basically every application that doesn't fall into level 1 or level 3. For you to go to a level 1 application, you really have to kind of prove that there's no risk at all running that application. So most applications would fall underneath the level 2. And then level 3 is for mission critical applications with a lot of sensitive data. You can think of the level 3 application as one that, if it went down or it was corrupted, could result in fatal consequences, or even for a company maybe going out of business or something like that. So think of level 3 as it's the highest risk application, therefore it has to have the most amount of protection. So there's 14 different domains within the ASVS, and you can see them listed here: architecture, session management, access control, authentication controls, cryptography, malicious code verification. So there's a lot of different areas that the ASVS covers, and these are all considered the domains. And so within each of the domains, as you'll see here, the first one is 1.1.1. So this is the very first statement that's within the ASVS, and it falls under the architecture category. So the description there, it says, verify the use of secure software development lifecycle that addresses security in all stages of development. And what you'll see there on the right is that the levels for 1, 2, and 3, meaning that this particular statement applies to level 2 and level 3, but does not apply to level 1. So again, if it's a level 2 or level 3 risk application, you would check for this statement that's in the ASVS. And then you can also see the other ones here. Some of them are all 3 levels, meaning that that applies even if you're a level 1 application. So for instance, the middle one there, the 2.1.5, it says verify users can change their password. So it's a pretty simple statement there, and that should apply to pretty much any application. So you can kind of see how this works in terms of the domains and the different levels. So how do we apply the ASVS? Well, you can apply it in penetration testing. So one way to do that is that the statements can be used to guide a penetration tester as they are trying to look for weaknesses within the application. The other thing is that it can be used for as a set of guidelines on what will be tested to help define the scope. And then lastly, it can be used to generate that report where like the penetration tester can create that output report based on their testing findings and put it in the context of the ASVS. So you can also apply it as a security SDLC, meaning you can use these statements as security requirements and put them in as requirements, same as you would put in for functional requirements. So an example here is on the left, the statement that's in the ASVS says, verify that input validation routines are enforced on the server side. You can create a requirement that could be pushed onto a development team that says software will validate input on the server side. So it's just basically using the statements to create security requirements. So again, different phases that the ASVS can play in. At the design phase, it can be used to create those security requirements. During the development phase, you can use it to ensure that the code that you're writing adheres to proper security standards based on the ASVS. Under peer review, you can use it as a way to do a code review. So that you can look at code and depending on the area of the code that you're working with, you can look at that domain within ASVS and see the statements that are there and make sure that the code is actually adhering to those statements. And then as I mentioned with the penetration testing for the secure test, the last phase here, it can be used to define test plans during automated testing or through penetration testing. So the ASVS is a good way of getting a lot of good security best practices and requirements and standards that's already created for you by OWASP that you can leverage. So with that, I hope you enjoyed this lesson. Look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about the Security Knowledge Framework, or the SKF. So OWASP developed the Security Knowledge Framework, and it's intended to be a tool that's used for guiding, building, and verifying security within software, within an application. So they built this based on the fact that education should be the first step when developing secure code. And I'm a firm believer in that as well, that if you educate people around secure principles and secure design, then you have less reliance on tools further down the road to solve your problems. So that's why hopefully you're enjoying this course. That's why I wanted to create this course. So I'll take this straight off of the OWASP website here, but it says OWASP Security Knowledge Framework is an expert system web application that uses the OWASP ASVS, which we talked about, and other resources that can be used to support developers in pre-development, security by design, as well as after code is released. All right, so it's basically a web application that allows you to, and we're going to show some of this, but it's a web application that allows you to put in some information about the application that you're building or the feature you're building, and it'll guide you through what you need to do from a secure design perspective. So why was the SKF developed? So again, as I mentioned, it allows security by design, or being able to bring security further left in the development lifecycle. The other thing is that information can be difficult to find as far as security goes. So one of the goals of the SKF was to make all the security information related to developing secure code available in one location. Examples lack security details. So again, that's something that they try to address with this, is that they want to make sure that any code examples that are provided provide the appropriate security details. The other thing is, again, security is difficult. That's why we're having this course. That's why you're here, to learn about these principles and understand about security. So that's another example of what they were trying to tackle with the SKF. Being able to work in a collaborative group. So again, OWASP is open source. You can use it and extend the SKF and also give back to the OWASP community. So that allows for many different contributors to be able to provide their input into what secure design is. SKF provides a defensive coding approach, which is, again, kind of playing off the security by design. And then SKF is the first step in the secure SDLC, or at least that's what we would hope for, is that you're able to leverage something like the SKF in that first step when you're first developing or designing the application that you're trying to ultimately build. So how can the SKF be used? Security requirements for development and for third-party vendor applications. So similar to what we talked about with the ASVS, the SKF can be used to gather those security requirements that are specific to the functionality that you're building. So security knowledge reference, it can be used to be able to get information on security issues right there within the web application, so you're not searching all over Google or Stack Overflow or Security Exchange or wherever you're going to get your security information. And then security is part of design with the pre-development functionality in the SKF, and also post-development verification, and we'll talk more about that here in a second. So within the pre-development stage, here's where you're able to understand the requirements that are appropriate for the application that you're building. It provides developers with secure development patterns that they can build into the product up front and first. And then within the post-development stage, you can use the SKF, similar to what we talked about with the ASVS, and that's the beauty of the SKF, is that it's really extending and building a web application on top of what the ASVS provides from a security requirements or standards perspective. So what we talked about with the ASVS in terms of being able to use it as a testing guidance or around penetration testing or writing test plans, you're able to do that same thing with the SKF as the web application to do post-development verification. So with that, I hope you enjoyed this lesson and look forward to seeing the next one. Thank you. Hey everyone, I wanted to go over what the security knowledge framework looks like. You can install this as a Docker container or as a full install, I believe, on Linux. It's pretty easy to get up and running. But here, just for simplicity, I'm going to show the actual OWASP demo site that they set up here. So it's demo.securityknowledgeframework.org. And the login. So for the login credentials, it's admin, and then the password is test, T-E-S-T, SKF. I'm sorry, it's test dash SKF. So here is the security knowledge framework and some of the options that you have, and we're going to kind of go through that here in a second. But before we do that, I just wanted to kind of show here some of the options on the left here. We'll go over these around projects. You can manage users. Because this is a demo site, it's cleaned out pretty frequently, so you're not anything you put on here is not going to be persistent. Just keep that in mind. If you want to keep persistent information around projects and users, you're going to have to install your own version. So the two big things here to notice that are pretty easy to navigate on your first pass of the SKF here is the code examples and the knowledge base. So take a look at here at the knowledge base. You're going to see it's pretty consistently through the site. You're going to have an option to look at web applications or mobile applications. We're going to stick with web applications for right now. So I'm going to go ahead and open up the web applications. And for the knowledge base, it's going to provide you examples around things that vulnerabilities that impact web applications. So if you look here at SSI injections, LDAP injection, include X cross-site script or cross-site scripting, and it'll give you some information related to basically it's an encyclopedia around these vulnerabilities that impact web applications. So it's going to give you a description of the issue, some of the solutions that are provided for it. Again, you can update and delete, but again, none of this is going to be persistent because this is a demo site that's being managed. So if you want to update or delete any of this information, you'd have to run your own version of it. But again, you can kind of see there's a long laundry list of issues here that you can look through for proper security. We're not going to go through all of these, but you can see here it's a rather long list. CA certificates, it's interesting. So if you go up to here, you can also do search for specific vulnerabilities. So maybe we're looking for SQL type of vulnerabilities, SQL injection, and it'll give you, again, the description, the solution here. So now the other thing that they provide here is code examples. So again, we'll stick with web applications. You can filter this by language. So maybe we want to look at Java issues, and then again, you can search by vulnerability if you want to. But this is going to give you coding, secure coding related to that specific issue that you're looking at here. So for instance, we're looking at hashing, and here it's going to be the Java code related to doing a secure hash. So you can copy and paste this. You can modify it if you want to. If you're working in an enterprise, this is where the update delete options come into play. But if you're working in an enterprise and perhaps you manage the application security for your enterprise, you may want to add perhaps a different coding style, or maybe your enterprise has specific code, coding style that it wants to implement. You can do that by adding that information in here and doing an update. So, but again, as you can see, there's a good amount of information here, coding examples that you can freely take, use, modify the way you want to. So, okay, with that, just wanted to provide those two quick hit things here, the knowledge base and the code example. They're easy to kind of take a look at and get yourself familiar with some good coding practices. And what we're going to do here is create a test project. So I'm going to go ahead and create this project called test, and today is we're going to say test April. Okay. Project version is going to be project 1 or version 1. Description, my April project. Okay. I'm going to go ahead and say store project. And I believe my session may have been maintained here because this information, I believe, was me. So, oh no, actually, maybe not. This might have been somebody else. So, I'm going to go ahead and say ask for requirements once I go into the project. So here it's going to say, it's going to kind of walk you through a sort of questionnaire to determine what your requirements are for this project. So, what type of application is it? We're going to stick with web application, say select. Maturity level, this is what we talked about before with the ASVS, where level 1 is an application that doesn't have too much, or doesn't have any kind of sensitive information. Level 2 has some sensitive information, and level 3 is the mission critical type of application. We're going to stick with just stick in the middle here and just say level 2. And what we want to focus on, maybe we have a lot of APIs, so let's focus in on the API security here. And it's going to ask questions around that specific category that we picked here. So generic web service security verification requirements. Yes, I do want those. Yes, I want RESTful web service requirements. I don't need SOAP verification requirements. GraphQL. Let's say, no, we're not using GraphQL. And here you can, select the sprint if you have one. Again, if you have a persistent copy of this, you're going to have perhaps sprints already listed here, but we're just going to create a new one and say this is our April sprint, and April sprint. Okay. Finish, say save, and it should populate here. So now I'm going to go ahead and view it. It says there's 11 total items that were created, so I'm going to go ahead and view it. And these are going to be the requirements that are required for the given project that we're working on here. So I can look here and see, again, this is based on the ASVS, which we talked about. So this comes from category or from domain 13. It's requirement 1.1 out of 13 here. So it says verify that all application components use the same encoding and parsers to avoid parsing attacks that exploit different URI or file parsing behavior that could be used in SSRF and RFI attacks. So here it'll give you common weakness and enumeration reference to that as well. And here you can provide information as to how it was resolved. If it was indeed resolved, you can do an update. So these are the listing of all the different, all the different requirements that would be put on the development team when creating this development module that we chosen. Now, additionally, you could take this and use it as a testing once the development has been completed. So now, the other thing you can do here is you can export this to a CSV file. So you need to import it into something else. That's an option here. I do also want to look here at the checklist option. So what we can do here is do web application again. Look at, for instance, maybe we're concerned with data protection. So let's go ahead and take a look at that. And it's going to be similar to what we saw there with the actual project that we were creating, but in this case, this is just generic, not specific to the project we're working on here. But let's say we wanted to do a code review, and we want to do a code review that pertains to the error handling and logging of a set of code or a module. So we could take this and perhaps look at these as reference for how do we do that code review of the code that we're looking at here. So we would ask questions, related to verifying that the application protects sensitive data from being cached in the server components, such as load balancers and application caches. So if we're doing a code review, we may ask questions around how is that sensitive data, if it's being cached, where is it being cached, how is it being protected, is it being flushed, are we not caching sensitive information? And again, there's going to be a CWE reference available as well, so that you can take a look at. Okay. Now with that, there is a lab section here. We're not going to do this right now. What we will do is do that in a separate demo, but this is also available in the SKF. So look for that demo soon. And I appreciate your time, and I hope you enjoyed this. Thank you. Hey everyone. Welcome back, and today I'm going to show a little bit of the labs that are available in the Security Knowledge Framework. So here you can see I just went to the public site here, the demo.securityknowledgeframework.org, and if you look under labs here, you'll see a listing of all the different labs that you can take advantage of. Just for this example, we're going to do an easy one. We're going to do the cross-site scripting. So I'm going to go ahead off here to the lab, and in order to do this, I'm sorry, let me, I had something else running there. In order to do this lab, you need to have a Docker, we're going to run this as a Docker image here. So go ahead and you need to have Docker installed. I'm not going to go over that here. I'll allow you to do that exercise on your own. So I'm going to go ahead and run the Docker image here, and we are up and running. I specified here 127.0.0.1 port 5000. So I'm going to go ahead to 1.7.0.0.1 port 5000. You can see here that the request is being processed. Now the other thing I have running here is Burp Suite. We talked about proxies in the past, and Burp Suite's basically a proxy, but it's proxy on steroids. It allows you to do a lot of additional functionality above and beyond something like Fiddler that we talked about in the past. The intercept is turned off, so what I'm going to do here is run a test, make sure that this works. It comes up, it shows test. So I'm going to go ahead and turn the intercept on, and let's do test, let's do test 2. All right, now it's paused here, intercept picked it up, and if you look at history here, you can see here string, picked up our string of test 2. I'm going to go ahead and send this to the repeater. Again, you can kind of see string 2 is being sent here. And all this is showing that we're able to capture the information. So I'm going to go ahead and let the proxy run. Test 2. Okay. So This shows that we have a proxy running. If you look at step one of this lab, it's saying here that it's got an input field. We want to test cross-site scripting, so we want to make sure we're getting a successful intercept. We showed this the string being shown there. It gives you a little bit of insight here into the application code, and it's saying that in that post that there's no auto escape that's being there's no auto escape attribute here being used, so we should be able to try some injection attacks. So the first step we want to do here, I am going to leave intercept on so we can just show this, but I'm going to go ahead and put in their suggestion. Go ahead and submit. Proxy intercept. And so you can see here that it encoded it. It's in 3p here, so we can see a little bit better here. We can do a send. And I believe it's, yep, so you can see here. All right, so as you can see, the application did not encode or blacklist any of the dangerous HTML characters, which, in this case, it's possible we can inject possible strings or script. So, because we found out that it's not doing anything there, it's actually rendering that as is. Let's go ahead and try a little bit more. And for this, I'm actually going to turn intercept off so we can actually see it happen. Okay, and there you go. So that's a reflected cross-site scripting. We injected the script tag. It was an alert, just so you can see that again. We're saying, run this script here. It's an alert, which is going to be a pop-up. In the pop-up, we want to have 1, 2, 3, and here you go. So we know that this site is susceptible to reflected cross-site scripting. All right, and here's the output that they received as well. So it does specify here that in Chrome it doesn't work because cross-site scripting auditor is enforced. So there's some nuance there and difference between the browsers, but we're using Firefox, and again you can see that it actually worked. Okay, so that's just a quick overview of the labs that are available here in the Security Knowledge Framework, and I highly recommend if you have the ability to install Docker and run this. It's fairly easy to get running. This is an alternative to using something like, say, WebGoat, but highly recommend that you give it a try. And thank you for your time today, and I look forward to talking to you again later. Hey everyone, welcome back, and in this lesson we're going to start talking about secure code reviews. So similar to a threat model, you want to make sure you have the right audience when you're looking to do a secure code review. You want to make sure you have the developer that's responsible for the code and any other developers that may be responsible for ancillary code around that code that's been developed and under review. You also want to make sure that you have architects that are familiar with the overall system so that they have the proper context to be able to address questions around the code. And obviously you want to have security SMEs, maybe it's within the team, or maybe it's a security individual from the actual security team outside of the development team. And then depending on the portion of the application, you may need to include SME for that topic. So for instance, authentication, database, system integration, user experience, APIs, so forth. You may have to have people that are better versed in those specific areas. So when we're talking about scope, you want to make sure the code reviews should take into consideration the threat model and high-risk transactions in the application. Again, your threat model should already be completed, and that should be one of the inputs that you do for this code review. A completed threat model will highlight the areas of concern. As we mentioned before in the threat modeling, it should highlight certain hotspots within the system that you need to pay closer attention to, and that should rise up when you're doing your code review. Anytime code is added or updated in those high-risk areas, a code review should be triggered for that event or for that code that's being injected. When changes are required to the threat model due to findings during that code review, then the threat model needs to be updated. So it's a really kind of a cyclical type of activity where your threat model should inform your code review, and your code review should inform your threat model. So then when we're looking at the code that's under review, you want to make sure that you understand the risk that that particular workflow may have to the overall system. Is it a high value type of workflow? Is there impacts to other parts of the system or to clients or to interactions? So these are things that you want to understand prior to going into the code review. Is what's the risk level for that particular code that's under review? The higher the risk, the more thorough the code review should be, and probably the more people that you need to include, especially from the security space, to that threat to that code review. So some of the things that we talked about when we did risk rating is that to understand what the risk is of the code review is, you understand what's the ease of exposure to a vulnerability. Is it something that can be easily discovered? What's the value or the impact of the vulnerability? If there was a vulnerability in the code, what's the impact of that? And then are we under any kind of regulatory controls in order to inform the way that we do the code review and the way that we have risks associated with it? So things you want to understand before going into the code review, you want to understand the application features and the business logic. So what's the code trying to do from a feature perspective? What's a different business logic that's impacted by this? You want to understand the context and the sensitive data that may be either part of the transaction or the workflow that's under consideration. You also want to know, obviously, the code. If you're coming from outside the team, you want to have a good understanding of the code. If it's written in C#, obviously you want to have a security person that knows C#. Java, Ruby, same thing. You want to understand the user roles and the access rights. Does somebody need to be authenticated to the application in order to run this workflow or the code that's under consideration, or is there anonymous access? Because that changes the way that you look at it. And then what's the application type? Is it a desktop app? Is it a web application? Is it a mobile application? Any kind of the design or architecture diagrams or documentation that you can gather will obviously be good input into this as well. And then what are your company standards, guidelines, and requirements that may apply to the code that you're about to review? So the reviewer is going to need certain details about the code, and that could be the design documentation, the business requirements, the functional specification, test results, and so forth. So that's going to be hard documentation that the reviewers should be familiar with before going into the code review. And if the reviewer, specifically around security, if the security reviewer is not part of the development team, they need to talk with the developer and the lead architect for the application to get a better understanding of what the application is from a high level. What does it do? What's its purpose? What are the different interactions that it has with perhaps other parts of your own system or other parts of external systems? So some information gathering tips. You want to see, and I work this way as well, I want to see the application running. I want to be able to experience it from the client viewpoint, because that helps me understand a little bit more about the application. You want to have a brief overview of the structure of the code and any libraries, so you don't need to dive deep, but maybe at least from the project level, what are the different components of the application and the structure that are important that you may need to know about. Knowing the architecture of the application goes a long way. So again, those diagrams and the documentation, the technology stack, the way it's deployed, how it runs in operations, all that information is only going to enhance your ability to do a proper security code review. All the required information of the proposed design, including flowcharts, sequence diagrams, class diagrams, and requirements and documents, should again all be gathered so that you have that information, at least if not readily available to you for reference, at least have it ahead of time so that you can review it. So talking about a couple different ways to go through the code review, or at least different areas of concern that you want to look at. So for instance, the design. What could be a vulnerability that could impact the design? Well, is there a presence of backdoors or placement of checks, insecure data binding, things like that? So some of the questions you may want to ask if you're in one of these code reviews are, are there any backdoors? Flat out ask, are there backdoors? Is there proper mapping of user privileges and methods, actions are allowed to them? Are security checks placed before processing input? So these are kind of the code flow type of questions that you may want to ask during a code review. From an authentication and access control perspective, the vulnerabilities could be insecure authentication, insecure session management, weak password handling. Again, we talked about these throughout this course. So you want to ask questions about does the design handle sessions securely? So what's your session management process, and how are you securing sessions? Are passwords stored in encrypted formats? Are they salted and hashed? Does authentication authorization fail secure? Those are the types of questions you're going to want to ask around the authentication and authorization. So what about data access? So presence of sensitive data and configuration code or support for insecure data sources, those are potential vulnerabilities there. So you want to ask questions around database credentials. Are they secure? Are they secured using encryption? And does the design support weak data stores like flat files? So those are kind of, again, the data access type of questions you want to ask. So what about centralized validation? Is there any weakness in existing security controls? So it's kind of broad here, but are there any special kind of requests skipped from validation? Does the design maintain an exclusion list for parameters or features from being validated? So this really comes down to how do you scrub and sanitize your inputs when they come in? Is that being done in a decentralized or a centralized way? And if it's done in a centralized way, are there any workflows that perhaps bypass that centralized check? So what about the overall architecture? So is there insecure data handling, transmission? Is there elevated privileges when running? Is the data, so some of the questions you want to ask is the data sent on encrypted channels, HTTPS? Is there, we talked about data at rest, data in transit, and so forth. Does the design involve session sharing between components and modules? Does the design use an elevated OS system privilege for external communications or commands? Because that you want to be concerned about, because anytime a vulnerability takes advantage of something in a system, it's running under the context of the current user. And if that's an elevated user, that could be a problem. So what about configuration? So known flaws in third parties, common security controls. And the questions you may want to ask are, is there any third-party libraries that you're using that are perhaps vulnerable? Are there security settings enabled in the design so it's secure by default? And with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about session management. So one thing to remember about HTTP is that it's a stateless protocol, meaning that every time your browser makes a request to a server, the server's seeing it for the first time. It's a stateless protocol. So in order to maintain some user configuration and maintain some state about the user as it comes back to a web server, say for instance, if you go onto Amazon, we had to introduce something and that will maintain that session. So what's typically done, or what has been done up until most recently, is the use of cookies. Now you're seeing a lot more different technology that's out there, token type of ways of maintaining session, but primarily the way it has been done is through cookies. So the way cookies work is that on the first request to a server, the server is going to say, hey, you're new, let me set this cookie. And then every time that your browser goes back to that same address, it's going to append that cookie to that request so that the server says, oh, here's, it's you again. Here's the cookie information that I gave you on our initial contact, and so now I know it's you. So some obvious ways that this can be broken. If there's somebody in the middle, a man in the middle, a person in the middle, that is able to intercept that traffic and grab that cookie, there's potential there for them to be able to replay that cookie. So there's another type of attack called session fixation. And basically, this is where an attacker is able to go to a web server. They'll log into that site with their credentials. They'll get a session and get a cookie. And through phishing or social engineering, they will generate a URL that they'll pass to the victim with that session ID that they've been authenticated with. and the user goes, and maybe it's an email or something like that that says, hey, go to your bank account or go to your bank website because there's an issue. Click this link and go there. And so the victim will go, they'll use the session ID that the attacker used to get to the site. And the victim will then put in their username and password. And because that session is now considered shared between the victim and the attacker is basically, with that session, being able to be authenticated as that other user. So some examples of poor session lifecycle management: guessable session IDs, meaning that you can guess what the next session is going to be, which will allow you to create possibly a session that could be active. Not destroying sessions when the session is over. So if I log out, if my session still persists, that's a problem. Reusing sessions. So maybe a great example of this, but maybe every week you start over again and start reusing sessions that you started using on Monday, whatever that case is. Reusing those sessions can be bad because if they could be potentially used to be replayed. And then exposing sessions. Maybe it's you're exposing it in the URL through logs or other examples. So some of the defenses with session identifiers: you want to make sure you're generating unique session IDs. That way they're not guessable. You want to use something like a GUID. A lot of frameworks will generate these for you. You want to generate them random and in an unguessable order. So in other words, like I mentioned before, you don't want to have it your first one be 1 and your second one being 2, or things like incorporating the date or something like that. Makes it more guessable. So the recommended way to do it is use GUIDs, which are typically in the programming frameworks. Do not reuse session IDs, as I mentioned. Once that session ID has been terminated, then get rid of it, never use it again. And again, GUIDs are going to help you in that space. You want to be able to distinguish between session identifiers generated before and after authentication. So you can go, for instance, to Amazon and start putting stuff in your cart without being logged in. As soon as you log in, that the stuff that you added to that temporary cart is merged into your regular cart. And that's the difference between having a session prior to login and a session after login. But they should be two different sessions. So in other words, as soon as you log in, that initial session should be terminated and you get a brand new session started. And then don't expose session IDs in application URLs because, again, that URL could be shared, it could be bookmarked and then shared or something like that. You don't want that session ID being possibly replayed. So some of the best practices around the lifecycle management: you want to end or expire sessions after a period of user inactivity, and we're all pretty much familiar with this, that after a certain period of time, your session is no longer active, you have to re-log in. Do not allow infinitely lived sessions, even with user session activity. So in other words, if a user moves their mouse every 30 seconds or 30 minutes or whatever your timeout is, you want to still terminate that session after perhaps a week or maybe 3 days or a month or whatever the policy for your organization states. You always want to offer a logout option. This is very important that you want to have it clearly defined on the page where a user can log out so that they have the ability to terminate their session. And then tie audit events to user sessions. So you want to make sure that there's an audit trail and a session alias. So you don't want to store necessarily a session ID in that audit or in the logs, but you want to be able to tie it back to a specific user in case something happens that you need to actually determine whether there's an issue or not. So some points about cookies. So here's some of the typical settings that you can have in cookies: max age, expiration, domain, path, secure, and HTTP only. The ones from a security point of view that we're concerned about is the secure, HTTP only, max age, and expiration. So when we're talking about setting secure, that just basically means that the browser cannot send it over HTTP, it can only send it over HTTPS. When we set session cookies as HTTP only, that means that only HTTP is able to access that cookie, not script. So that's important to keep in mind when we're thinking about things like cross-site scripting. And then you want to avoid setting values for max age and expiration. And the reason for that is that this will actually remove that cookie when the browser is shut down. So that way that cookie doesn't persist afterwards. And so just some basic finishing thoughts here. So from OWASP, it says authentication, authorization, and session management are hard. We talked about that before. So rolling your own is usually a perilous endeavor. So instead, you want to use standard authentication protocols that are out there. You want to use hardened web frameworks, identity federation. And again, we're going to talk about some of this stuff that later on in the course. But point being, don't create your own authentication, session management, authorization, because a lot of these have already been created. They're done well, and there's plenty of opportunity for you to leverage those tools as opposed to creating your own. And with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to start talking about session management. So what is session management? Well, it comes down to, as we mentioned before, HTTP is a stateless protocol, so therefore there's no way for the protocol itself to be able to understand that the same person or system that made a request 30 seconds ago is the same one that's making a request now. So there's no concept of understanding state or session. So there's a couple different ways to manage sessions. And one is through user authentication. This is everyone's pretty much familiar with this. This is using your username and password on a log-on page. You can also maintain session within like an HTML hidden field where the session identifier is actually stored in a hidden field. You can also do that in a URL rewrite where you actually put the session in the URL. And then the last one that we're probably all fairly familiar with is the use of cookies, where the session is actually stored inside of a cookie and stored in the browser. So again, because HTTP and web servers are stateless, the only way to maintain session is when some unique information about the session is passed between server and client in every request and response. So here's a kind of a sample of a session management using cookies, and it says Java, but this is really kind of generically how cookies are managed with sessions. So, in step one, you go to the web, you request information from a website. When the website server replies, it sends back a cookie, which your computer puts on your hard drive, so it stores it locally on your device. When you get online to return to the website, you pull that cookie and you send it back to the server. So that's the way that the server recognizes that it's you. It's similar to a cookie you can think of similar to something like an ID badge or something to that effect, where every time you go to the server, you present this cookie and the server says, oh, I remember you because I gave you that cookie to begin with. So here's an example of using Java session management with HTTP session. And serverlet API provides session management through HTTP session interface. And you can see the two methods below in order to get that, one with a Boolean flag and the other one without. So the one without, this method always returns an HTTP session object. It returns the session object attached with the request. If the request has no session attached, then it creates a new session and returns it. For the one with the Boolean flag, this method returns HTTP session object if request has session, else it returns null. So it's important to remember that when using the get session does not return an active session, then it creates a new HTTP session object and adds a cookie to the response with the JSession ID and value as session ID. So this cookie is used to identify the HTTP session object and further requests from the client. So it's just basically a way of getting session from the servlet API. It gets put into the JSet, or the JSession ID is put into a cookie, which is then returned to the server every time the client wants to make a request to that server. So there's an alternative way of managing sessions with Java, and that's with the URL rewrite. So there's obvious security concerns with this, and you'll kind of understand as we talk through this, but there are many times when the browser has cookies disabled, which means you have to pass the session ID in some manner. And the application may choose to pass this information in the URL. So it's going to encode it using the encode URL method, and this will put the session ID in the URL And again, as we know with what we've learned in this course, any type of sensitive information in the parameters within a URL could be potential for that to escape. Could be logged, could be sent over email if somebody's sending a link, things like that. So it's not really the securest method of managing sessions, but it is available if cookies are disabled. So let's talk a little bit about .NET sessions. So with .NET, there's a couple different ways of managing sessions. There's the in-proc, state server, SQL server, and then custom. We're going to talk about each one of those here in a moment. So with session management in .NET, again, there's several different storage options. Each option is identified by a value in the session state mode enumeration within the web config. And modes other than in-proc or off require additional parameters. So again, we're going to step through each one of these individually, but just remember that it's in web config. You can set whichever session management that suits your needs. Just remember that when you're setting modes other than in-proc or off, that you're going to need additional parameters such as connection strings. So in-proc mode, which stores session state in memory on the web server, this is the default. State server mode is somewhat slower service, and we're going to talk about that here in a minute. SQL Server and state servers are very similar in terms of concept, where it's basically stored away from the web server. Custom allows you to build your own, or at least point to your own session management scheme, and then off means that there's no session being stored at all. So the in-process mode is the default session state mode, and it's stored on the web server in the memory. So it's actually running in memory. That's what in-process means. One thing to remember about this is that if the web server goes down or reboots, you lose all the sessions because those sessions were in memory. So the other thing to remember here is with in-process, that it's the only mode that supports session on end, which means that when the session is abandoned or timed out, the session actually ends. So with state server mode, this stores the session in a process referred to as the ASP.NET state service. That is separate from the ASP.NET worker process or the IIS application pool. So this is stored off of the web server. And so that means that you have some improved security, you have some improved reliability in the sense that if the web server restarts, the session state is still available because it's not being served on or stored on the web server. And then again, it's similar with the SQL server, similar concept in the sense that the SQL server is stored off of the web server, meaning that it can survive a restart of the web server. And it also allows you a little bit more security and flexibility with the fact that you're storing session within a SQL database. So then with custom mode, you're allowed to customize what type of store you want to use. When you configure your .NET application with a custom mode, you need to specify the session state store provider using the provider sub-elements of the session state configuration element. You specify the provider type using an add sub-element and include both a type attribute that specifies the provider's type name and a name attribute that specifies the provider instance name. And below you can see an ODBC type of connection to some other type of session state session state store that's not a SQL database or a state server. So with that, I hope you enjoyed this lesson and look forward to speaking to you later. Thank you. Hey everyone, welcome back, and in this lesson we're going to start diving into session management. So as we spoke about before, HTTP is a stateless protocol, meaning that every time you make a request to a server, the server's seeing you for the first time, even if you have gone to that server multiple times. And the only way for that server to really know that it's you is by retaining something about your session, and that's usually done through some kind of a session identifier that's stored into something like a cookie or some other way. And we're going to get into more of that later. But so modern and complex web applications require the retaining of information about each user for the duration of multiple requests. And that information could be specific to you, your shopping cart, your search history, and things about, you think about Amazon. If you go there, like there's a lot of configuration that goes into your account on Amazon. All that is maintained through retaining that session information. So session provides the ability to establish variables such as access right and localization settings, which will apply to each and every interaction a user has with the web application. So every time you go back to that server, as long as you have a session created with that server, all that information about you is going to be retained when that web server serves up that page. So web applications can create sessions to keep track of anonymous users after the very first request. And as an example, as I mentioned, there's preferences like user language or colors or the information in your card. All that stuff is stored in the session. And additionally, web applications will make use of sessions once a user has authenticated. So there is this concept of a pre and post authentication. So keeping with Amazon as the example here, if you go to Amazon and start adding stuff to your cart, but you're not logged in, once you log in, that stuff that you had in your cart prior to that session, prior to you logging in, actually gets merged with your cart. So there is this concept of pre and post authentication. Once an authenticated session has been established, the session ID or token is temporarily equivalent to the strongest authentication method used by the application. That's a very important part to remember, is that, and this is why it's important to protect those session IDs, is that once you log into a website, for instance, again, sticking with Amazon, once you log into Amazon, every time you browse somewhere or add something to your cart, it's not asking you for your login. It's using that session ID for each one of those requests to act as your login credential. So that session ID is equivalent to your authentication. So HTTP, stateless protocol, we stated that already. Session management links both authentication and authorization modules commonly available in web applications. So this basically makes decisions about your session ID. Once the server has your session ID, it knows that you're either a user or an admin, and it retains that information, within the server. But it knows based on your session ID what your actual role is. So it acts as both your authentication and your authorization. So let's talk a little bit about federation and federated identity. So when we talk about federated identity, it's basically the means of linking your identity across multiple different identity management systems. You can think of it similar to something like single sign-on or SSO, where basically a good example of a federated identity, and maybe this isn't the greatest example here, but it's pretty clear, is that when you log into Google, there's multiple different applications that you can access. You can access your calendar, you can access your email, you can access the search engine, and all the other different YouTube and so forth. All of that works as a federated identity. You're only logging in to one location. You're only logging into your Google account. You're not logging into each one of those individual services separately. So it's not a great example of federated because it's all underneath the Google umbrella, but it's an example of single sign-on and using an identity across multiple different management systems. So the federation of identity describes the technology standards and use cases which serve to enable the portability of identity information across otherwise autonomous security domains. So there's a couple different types of technology within federated identity. We're going to talk about these here coming up. But so you can think of SAML, which is a security assertion markup language, OAuth, OpenID, security tokens like JOTS or JSON Web Tokens, SAML assertions, web service specification, and Windows Identity Foundation. We're going to talk a lot about OAuth and OpenID and security tokens coming up in the upcoming lessons. So here's just an example of the different parties that play in the federated identity space. And there's a user there in the middle. And the user wants to access some type of service that is being hosted by the service provider on the left. And the identity provider is the one that actually vouches for that user in that service for that service provider. There's a relationship between the service provider and the identity provider. And the user has, when they want to authenticate and access that service that's being hosted by the service provider, they're actually authenticating with the identity provider, and the identity provider then creates some kind of a token or some type of identifying information. And it really depends on the use case and the technology, but the identity provider is going to provide some type of information that vouches for that user, and the user then sends that to the service provider to say, I've been authenticated by the identity provider. Here's what they gave me to authenticate me. Let me in. So from a high level, those are the players. You have a user, you have a service provider, you have an identity provider. And that's basically for a lot of the different types of technology that's out there, this is basically the way it works. But you'll see there's going to be some nuance in some of the technologies. So with that, I hope you enjoyed this lesson. Look forward to seeing you next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about JSON Web Tokens, otherwise known as JOTs. So JSON Web Token, it's an open standard RFC 7519 that defines a compact and self-contained way for securely transmitting information between parties in a JSON object form. So this information can be verified and trusted because not only can it be encrypted, but through the use of digital signatures, a signed token can verify the integrity. And we know this from what we've talked about in previous lessons regarding encryption and digital signatures, that a signed token can verify the integrity, and then also using a public-private key pair means that you can verify who it came from. So there's a couple use cases for authorization. This is the most common scenario for using a JOT. Once the user is logged in, each subsequent request will include the JOT. So remember what we talked about with cookies. Very similar JOTs are used for the request and response, where for each request, the JOT is going to be appended to that request, similar to the way that a cookie is. And then for information exchange, JSON Web Tokens are a good way for securely transmitting information about users between two parties. And because you can sign it and hash it, you can make sure that the information hasn't been tampered and that it came from who you expect it to come from. So in authentication, when the user successfully logs in, like I mentioned, it's similar to using a cookie. So it basically replaces a cookie in the sense where in that request, they're going to send the JOT in the HTTP header, and that's going to provide session information about the user and so forth. And then whenever the user wants to access a protected route, it should send the JOT typically in the authorization header using the bearer schema. We're going to talk a little bit about that here in a minute. So this is a stateless authentication mechanism, similar to what we talked about with cookies. So again, think of JSON Web Tokens as basically a replacement for cookies. As JOTs are self-contained, all the necessary information is in there, reducing the need to going back and forth to the database. So here's basically a simple workflow. So your browser will post with a login with the username and password. The server is going to create a JOT with a secret. Send that back to the browser, and then the browser sends the JOT on the authorization header for each subsequent request. The server is going to check the JOT signature and then get the information out of the JOT and send response back to the client. So again, it's very similar workflow to what we've seen with cookies. So the structure for a JSON Web Token has a couple different parts, and it has a header, a payload, and a signature. And if you look down there at the bottom, it's going to be basically the header followed by a dot or a period, and then the payload followed by a dot or a period, and then the signature. And so the header is going to have two parts, and the first part is going to be like what type it is. It's a JSON Web Token, and then the hash algorithm that's going to be used for hashing and creating the signature. And then in the payload, there's going to be the information about the entity, about the user, and these are going to have the claims in there. And the claims are statements about the entity, about the user in this case. And then the signature is going to be basically a hash of the JSON Web Token and then signed by a private key. So we remember from talking about digital signatures that basically this JSON Web Token is going to be put together from the header, the payload, put together, hashed, and then signed. And then that digital signature is the signature that's used here at the end for the JSON Web Token. So here's just a sample header. And as I mentioned, for the type, it's going to be a JSON Web Token. The algorithm that's used here is SHA-256. So there's just a sample of what the header looks like. And then for the payload, the claims, you have a couple different types of claims that you can use here. You can have registered claims, and these are the set of predefined claims, which are not mandatory but recommended to provide a set of useful interoperability claims. Some of them are, some of the examples here are issuer, the expiration time, subject, and audience. The public claims, these can be defined at will by those using JSON Web Token, but to avoid collision, they should be defined in the IANA JSON Web Token Registry. So it's basically a way to make those claims public so that everyone's aware of them and they don't have any collisions. And then they could be defined as a URI that contains a collision-resistant namespace. So in other words, it has to be unique. And then there's private claims, and basically these claims are ones that are agreed upon between the two parties that are exchanging the JSON Web Token. So here's an example of a payload. So you have the subject, you have a name, you have an admin. This is a very simple payload. A lot of the payloads are obviously more complex than this. So the payload is then base64 encoded. And then that, along with the header, is going to be eventually hashed and made into the signature, which we'll talk about next. So for the signature here, you take the hashing algorithm that was set up in the header, and so for instance, we had a SHA-256 algorithm. So it's going to hash this using SHA-256. It's going to take the header, the payload, and then a secret, which is going to be the key. Combine that, hash the payload, the header, and then use the secret key to actually sign it. And again, the signature is going to provide the ability to show who it came from. It's because only you have, or the sender should only have access to the private key. Nobody else should. And then the hash is going to provide that integrity check. With that, I hope you enjoyed this lesson, and I look forward to seeing you next one. Thank you. Hey everyone, and welcome back. And just wanted to kind of show an example here of a JSON Web Token, just some samples here to get you familiar. The other thing I wanted to show here real quick is that on the OWASP cheat sheet series, there is some information on JSON Web Tokens, and it'll provide you some of the information that we've gone through in the lessons. But additionally, it'll give you some other security considerations around using JOTs. So it'll tell you like what the symptom is here, how to prevent it, give you some implementation examples, and then it'll go into the next vulnerability or security issue and follow that pattern. So it is a good resource for not just for JSON Web Tokens, but as you can see here, there's a lot of different cheat sheets available that you can take a look at. So what I wanted to show here is that here this is jwt.io, and in here you have the ability to create or decode or encode JOTs. So the first thing I want to show here is that if I just change this payload here, let's say we're going to change the name. I just want to show you that in real time it's going to re-encode it. So if I put in here, let's say it's changed it to Jane Doe, you could see here that the encoded values have changed. You can also additionally add a secret here to sign it. So if I want to sign it with hopefully a stronger secret, but this is now signed with our quote-unquote secret here. You then have the ability to share this. You can copy and paste this and send it to somebody. So I do want to show you a quick little example here of the other way around here. If I take a JSON Web Token and pop it into that site to actually get the information out of it. So put it in, comes back as shows the payload data here. Now, if you go back and look at this site, he states that the signature is actually just a SHA-256 hash of the encoded content. The encoded content is just the header and the payload together. So basically there is no secret. So you'll see here it's an invalid signature because right now we have your 256-bit secret in here, and that's not the actual secret that's being used by. So if I get rid of that, you'll see here that it says signature verified, and we're good. So this is just an example of showing how you can get a JSON Web Token. You can get the information out of it. So this is the reverse of what I showed earlier. Just one word of security here is that this is a public website, so you want to be careful what you do put in here. If this information, then your payload is potentially secret or sensitive, you want to make sure that you're not putting it into this public website where it could potentially get logged into somewhere where you might have some concern. So, and with that, I hope you enjoyed this, and I look forward to speaking to you again. Thank you. Hey everyone, welcome back, and in this lesson we're going to talk about OAuth. Now the important thing to think about here with this particular lesson is that there's a lot to learn about OAuth, and we're only going to scratch the surface on this, but I wanted to give you a little bit of insight into what OAuth is so that you can go off and do additional research on it and understand a little bit more about it. But the important thing to remember about OAuth is that it's access delegation, meaning that you're enabling a third party to gain access to a service that you are the resource owner for. So for instance, maybe you want to provide a third party access to information that you have on Facebook, but you don't want to give them obviously your username and password in order to log in as you in Facebook. And as crazy as that sounds, that's actually how it used to happen, and that's why OAuth came about, was that in order for you to provide access to a third party, the third party would request your username and password and then log in as you and either scrape information or post as you or something like that. So that's where OAuth came along, where the whole point was to be able to delegate access to a third party. And the important part here is that you didn't have to give up your username and password in order to do that. So this mechanism is used by companies such as Amazon, Google, Facebook, Microsoft, and Twitter, and it permits users to share information about their accounts with third-party applications or websites, and again, without providing information about their, specifically their username and password. So you may be familiar with seeing a screen like this where, there's an event here. It says Bike to Work Day, and it wants to get access to your public profile and your email address and maybe some additional information. And you would allow this with your Facebook account. The Bike to Work Day would then gain access to some of your profile information within Facebook. So we all may be familiar with seeing this type of a screen, and this is essentially powered by OAuth. So OAuth decouples authentication from authorization. So again, it's a way of delegating access, and access means authorization, not authentication. So it supports multiple use cases addressing different device capabilities. It works with browsers, mobile native apps, and even with televisions and such. So you may be familiar with those use cases as well. OAuth is a delegated authorization framework for REST and APIs. It enables apps to obtain limited access, which is scopes, which we're going to talk about here in a minute, to users' data without giving away the user's password. Designated specifically to work with HTTP, OAuth essentially allows access tokens to be issued to third-party clients by an authorization server with the approval of the resource owner. The resource owner is going to be you. The authorization server is a separate entity that's part of the OAuth workflow. The third party then uses the access token to access the protected resources hosted by the resource server. So you may be the resource owner. So in the case of, like, let's say Facebook, you're the owner, quote unquote, the owner of the content that's on Facebook. The resource server in that case is Facebook. So, as I mentioned, here's some of the actors that are part of OAuth. So the resource owner, that's the person that owns the data in the resource server. So think again of Facebook. You are the resource owner of the data that's being served or being stored on Facebook's end. And resource server, this is the API which stores data the application wants to access. The client is the application that wants to access your data, so that's kind of the third party that we've been talking about here. And then the authorization server, that's the main engine of OAuth. That's the one that provides the tokens for the third party or for the client to be able to access the resource owner's data on the resource server. So as I mentioned, there's the concept of scopes, and scopes are what you actually are allowing that third party to have access to. And a lot of times this may be already designated by the third party and says, I need to have access to your email address, but you may be, as the resource owner, be able to kind of tweak what information is actually shared with that third party by configuring and unchecking certain boxes. But so scopes are what is, as the name states, what's in scope for that third party to have access to. So there's a couple different types of tokens. The access token are the token that the client uses to access the resource server. They're meant to be short-lived. Think of them in hours and minutes, not days and months. So the access token is what is actually used to present to the resource server to be able to get information from that resource server. So because these tokens are short-lived and scale out, they can't be revoked. You just have to wait for them to time out. Now, on the other hand, there's the refresh token, which we're going to talk about here. This is much longer lived, days, months, maybe even years. And this is used to get access tokens. So you use the access token to gain access to that resource server and to get the information that you want from that resource server. When that access token expires, you take your refresh token, you go back and you get another access token. So the access token is used for gaining access to the actual data that you're trying to get to from the resource server perspective. And then the refresh token is used to get new access tokens. And the OAuth spec doesn't define what a token is. So you can use JSON web tokens, you can use other technology, but for the most part, JSON web tokens or JOTs are the primary tokens that are used for OAuth. So tokens are retrieved from endpoints on the authorization server. The authorization endpoint is where you go to get consent and authorization from the user. And then the token endpoint is where the tokens, the refresh and the access tokens are issued. You can use the access token to get access to the APIs. Once it expires, you'll go back with the refresh token to get a new access token, as I stated before. So here's just a sample of a request, and I'll show the response here in a minute, but here's just a sample of a request to a Google API. And the scope here is just Gmail API. The redirect URI is the URL of the client application that the authorization grant should return to. The response type indicates that your server expects to receive an authorization code. The client ID is from the registration process. The state is a random string generated by your application, which you'll verify later. So the state is kind of a security bit of a nonce or a bit of information for to maintain that security, and we'll see here in a second with the response. So here in the response, you'll see the code is returned. The code returned is the authorization grant, and state is to ensure it's not forged and it's from the same request. So again, we're only scratching the surface on OAuth. There's a lot more to learn about this, but I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back, and in this lesson we're going to talk about OpenID. So what is OpenID 1.0 and 2.0? So OpenID is an open standard and decentralized authentication protocol. So the important thing to remember here when we talk about this is that it's a decentralized authentication protocol. And we talked about OAuth, which is an authorization. We're going to get to that here in a minute, but remember there's a difference between authorization and authentication. Authentication is that you're providing information that vouches for who you are. And authorization means what you have access to, right? So OpenID is on the authentication side of that equation. So it's promoted by the nonprofit OpenID Foundation, and it allows users to be authenticated by cooperating sites known as relying parties, or RP, using a third-party service, eliminating the need for webmasters to provide their own ad hoc log-on system. So that's another key concept here, is that one of the big drives for OpenID and the big desire around having OpenID is that for websites that don't want to manage user credentials, this opened up the door to allow them to offload that login functionality to a third party. So OpenID standard provides a framework for the communication that must take place between the identity provider and the OpenID acceptor, in this case the relying party. Neither service nor the OpenID standard should mandate or needs to mandate or will mandate the type of authentication that should be done. So it can be done through passwords or biometrics or key cards. So there's no requirement that it needs to be done through something like a password. So OpenID allows you to use an existing account. And this is probably going to start sounding familiar here in a minute, but many of you have probably seen websites where it says log in with your Facebook or Google or LinkedIn or some other type of account. And that's what OpenID basically is. It allows you to use another third party to be able to log into a website so that they don't keep that third party website that you're logging into doesn't need to create authentication mechanisms, store your password, which is obviously more secure. Now, obviously, you're using your credentials are being stored somewhere. So if you're using Facebook or Google or something like that, they have your username and password. But this allows you to not have to register a login at a different party. So you may choose to associate information with your OpenID that can be shared with the website you visit, such as name or email address. And that's similar to what we talked about with scopes and OAuth. And with OpenID, your password is only given to your identity provider. So in that case, Facebook or LinkedIn or Google or something like that. And then, last point there again is that other than the provider, no website will have access to see your password, the one that you use. For instance, if you're logging in with Google, that third-party website that you're logging into doesn't have access to your Google password there. So the end user interacts with the relying party, such as a website that provides an option to specify an OpenID for the purpose of authentication. Again, that's where it's going to prompt you and say, log in with Facebook, Google, LinkedIn, so forth. The relying party and the OpenID provider establish a shared secret, and that's done beforehand, which the relying party then stores. The relying party redirects the end user agent to the OpenID provider so that the end user can authenticate directly with the OpenID provider. So in that case, again, if you're logging in with Google, you'll get redirected to the Google login page. That's the OpenID provider. You'll put in your Google credentials there, and then behind the scenes, you're authenticated in that third party. We're going to talk about that here in a minute. If the end user accepts the OpenID provider's request to trust the relying party, then the user agent is redirected back to the relying party or the initial service that you're trying to access. So, as I mentioned, we're all kind of familiar with seeing a page similar to what is there at the top where you can sign in with Facebook or sign in with Google. And just, a pictorial version here is basically you wanting to have access to that application. The application says, who are you? You say, don't worry, I'm going to go to Google. I'm going to get my information from them, and they're going to vouch for me. Again, we talked a lot about that with OAuth and other types of authentication authorization. But so Google's going to send back some type of token that you're going to be able to then present to the app and say, here, Google, said I'm good to go. Please allow me access. So there is another form, that's OpenID. OpenID Connect is something different. We're going to talk about that here in a second. And really, OpenID Connect is the combination of OpenID and OAuth. So it really marries that authentication and authorization together into one standard called OpenID Connect. So OAuth is directly related to OpenID Connect since OpenID is an authentication layer built on top of OAuth 2.0. And it's distinct from XACML, which is basically a authorization policy language. But OAuth can be used in conjunction with XACML, where OAuth is used for ownership consent and access delegation, whereas XACML is used to define the actual authorization policies. So OpenID Connect, as I mentioned, is a combination of OpenID and OAuth 2.0. And it allows clients to verify the identity of the end user based on authentication performed by the authorization server, as well as to obtain basic profile information about the end user in an interoperable REST-like manner. So OpenID Connect allows clients of all types, including web-based, mobile, JavaScript clients, to get information about authenticated sessions and end users. So the specification is extensible, allowing participants to use optional features like encryption, identity, data discovery, and session management when it makes sense. So what does this look like a real workflow here? So the user, in this case, the resource owner, we talked about this before in the OAuth lesson. So the resource owner, in this case, the user is going to request access to an application. And that could be, again, an application, a third party that participates in the OpenID Connect workflow. And that client is then going to redirect through the resource owner and ask them to authenticate to that OpenID provider. So it could be Facebook, could be Google, LinkedIn, something like that. So the user will authenticate there, and then the OpenID Connect provider is going to then send an authorization code over to the client application, redirected through the user. And then the OAuth client and the OpenID Connect provider are going to exchange that authorization code for an access token. And that's a term probably sounds familiar because we talked about that with OAuth. So the request, the user then will be able to use that access token to be able to get the requested information. And that access token, again, is used at the resource server to actually gain access to that those resources at that resource server. So with that, I hope you enjoyed this lesson. Look forward to talking to you again. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over risk rating. So what is risk rating? When you boil it down to its simplest parts, risk rating is basically likelihood multiplied by the impact. We're going to talk about each of those here coming up. So a couple different steps we're going to go through here. So first one is identifying the risk. And again, we're going to go through each one of these steps in detail, but first thing you want to do is identify the risk. Next, you want to establish the estimated likelihood. You then want to think about the impacts, determine the severity of the risk, which is basically the calculation that we showed, impact, impact and likelihood equaling risk. And then the last part is deciding how to fix it, or if you're going to fix the issue. So in step one, identifying the risk, the first thing is to identify the specific risk that's potentially been identified. Now that can come from a lot of different sources. Could be from a penetration tester, could be from a vulnerability scan, could be from an external party. So there's a lot of different ways that a vulnerability or a risk could be potentially raised to your team. So the important part is first identify where that risk exists and whether it's real. The next thing you want to think about is estimating the likelihood. So this really means how likely, hence the name likelihood, how likely is this risk going to actually happen? There's a couple different ways that you're going to try to figure this out. And one is you want to look at the threat agent factors, and the other one is the vulnerability factors. So the threat agent factor, this really comes down to the group of threat agents that could actually take advantage of this risk. You want to use the worst case scenario for a threat actor because that's going to give you your highest level of risk. From the vulnerability, here you're going to try to establish the likelihood based on the vulnerability being discovered. So this could be not just discovered, but also exploited. And then you want to also take into account the threat agent or the threat actor that you've chosen in the previous step. You want to make sure that threat agent is actually going to perpetrate that vulnerability that's been found. So threat agent factors, a couple different concepts around the threat agent that you want to take into consideration. So what's the skill level of that threat agent? And we've talked before about the differences between script kiddies, hacktivists, advanced persistent threats, and so forth. What is their motive? And that's going to play into the threat agent. So again, we talked different motives that each one of those threat agents have. So for instance, a script kiddie might be motivated by revenge. Advanced persistent threat might be motivated by national security interests. What's the opportunity? So what resources are needed for a threat agent to actually take advantage of that vulnerability? And then last, what size is that group? So again, if it's script kiddies, that could be a very large group of people that have potential access to exploit the vulnerability. So around the vulnerability factors, what's the ease of discovery? So how easy is it to discover this potential vulnerability? Are there automated tools, or does it take a little bit more research? The ease of exploit, is there something that's already, are there exploit kits already available that somebody can take advantage of? Or are they going to have to write their own exploit and, again, take a lot of effort and time to do that? And awareness, how well known is that vulnerability? Is it something that has been publicly announced, or is it something that still is very not very likely to be well known? And then probably one of the more important factors around vulnerabilities is, do you have mitigation or the potential to actually detect that vulnerability is being exploited? And again, that all gets into how impactful that vulnerability is. So when you're considering the impact, you want to think about the technical impact and you want to think about the business impact. And then obviously there are two different things, and we're going to talk here in a moment about why they're different. But from a technical perspective, you're thinking more about the application and data that's part of that. From a business point of view, you want to look at what's the impact of the business. More importantly, what's the impact of the business's bottom line? Are they going to lose money? Are they going to lose clients? That kind of thing. So when we take a look at technical impact, this can be broken down into factors aligned with traditional security areas of concern. So confidentiality, integrity, and availability, CIA, which we've been talking about a lot here. And the goal is to understand the impact on the system itself, so the technical aspect there. And then from the business point of view, it really comes down to having a deep understanding of what is important to the company running the application. So again, as I mentioned, if something happens to that application, is the company going to lose a lot of money? Are there clients going to leave? Are there regulatory or fines that might actually be levied against the company? So all those kind of things come into play with the business impact. So some of the technical impact factors, as we mentioned, talking about confidentiality, integrity, and availability and accountability. So is there loss of confidentiality? Is there loss of integrity? Is there loss of availability? So in other words, did data get leaked? Did data become corrupt? Or is data unavailable? So that's really when we're talking about technical impact. And then loss of accountability. Are we able to trace this back to somebody who actually perpetrated the attack? So with the business impact factors, we're looking at things like financial damage. So how much money is the company going to lose? Reputation damage. Is the company going to be in the front page news, and are a lot of people going to be upset about this? And are they going to leave? That's one of the biggest points is if there's a lot of competition in the space that you're in, and you have a breach and something happens, there's potential there for you to lose clients based on this. Non-compliance. So again, if you have legal or regulatory demands on your application, non-compliance could also mean fines and things like that. And then privacy violation, how much personally identifiable information was disclosed. So again, about the overall business impact. If you lose a lot of your data, that's going to be a problem. So determining the severity, there's two different ways of doing this. There's an informal way, and then there's a repeatable way. So the informal is basically sitting down with a group of people, reviewing the factors and just capturing the answers and basically capturing the way you got to the answer that you came to. The repeatable is more of a process. So it's where you have a formal process of rating. You may even have some automation around it. That's a more repeatable way of doing that. And it really depends on the scale and the frequency in which you're rating these risks, depending on the way that you want to approach this. So we talked about all the different factors that are available here. So with vulnerability factors, what you basically do is you take a look and you, from a scale of 1 to 10, you pick 0 to 9. You pick which dial you want to place this in. So for ease of discovery in this case, we said maybe it's not that easy to discover, so we're going to say it's a 3. But maybe there's some automated tools available, so the exploit could be it's a little bit easier, so maybe that's a 6. And everybody knows this, so it's a 9 for awareness. And we don't have much in the way of detecting this, we have a lot of intrusion detection capability, so maybe that's a 2. So you can kind of see how there at the bottom where it says low, medium, high and gives the number scale associated with each one of those, you can see that ease of discovery is a low, ease of exploit is medium, awareness is a high, and intrusion detection is a low. So, and it follows this throughout the rest of the ones we're going to look at here. So with the threat agent factors, you do the same thing. You basically take all those numbers, all those scores, and you then average them out, and in this case, based on the factors that we have here, we came out to a score of 4.3 or 4.4. You can round up. So then, looking at the technical impact, what you actually want to do is split out the technical impact and the business impact. You can do them together. Some companies will do them together. Some companies will just take the technical impact or the business impact alone. So in this case, we're saying the technical impact is high. So we have a lot of loss of confidentiality. or the loss of confidentiality is very high, loss of integrity is very high, loss of availability is low. Maybe we're not going to lose access to the system or access to the data, but it's going to be exposed and corrupted, and then we have no way of tracing that. So that's pretty significant. From an overall technical impact here, you see it's a 7.2, which is high. And then from the business impact, maybe we say, yeah, but we're not concerned about that data. We're not going to take a big hit on that from a financial aspect. It's low. Reputation damage, we're not worried about that. We're the only player in the space, and nobody's really going to flee if we don't, or if this gets disclosed. We don't have any kind of compliance concerns there. And yes, it's a privacy violation because data was exposed, but we can manage that. So here you see kind of the technical impact is high, but the business impact is low. And the reason for this is that it allows you to say what's more important. Are we more concerned from the technical point of view that we have this issue that needs to be resolved, or are we more concerned about from the business perspective? In this case, the business is saying we're not too concerned about this. So you take these, and again, you have the likelihood, which is going to tell you how likely is this going to happen. And then you could add, again, we're going to do the averages here, but you could add the likelihood to the business impact and get a score out of that by averages, or you can take all three of them together and get an overall score that will provide you what your overall risk severity is. So deciding what to fix. So this is obviously the big concern here, and you want to make sure that you keep it in perspective. If, for instance, your privacy violations, your compliance violations, or maybe some legal issues, or you have to buy some kind of credit monitoring for people that had their data stolen. You take all that and you add it up, and maybe it comes out to $1 million, but to actually fix the issue is going to cost you $10 million. Well, that's not something that you're probably going to want to spend your effort on, and you may want to figure out a different way of resolving this risk. So that's a good way of kind of figuring out, what is our number one, what's the impact from a dollar amount, what's the impact of this actual risk, and then from there, what do we need to do in terms of mitigating it, or the other option is just to sunset possibly the feature or the application in favor of actually putting a fix in place. So there's a couple different ways of handling the risk. You can accept it, and this basically, you document the risk, you acknowledge that it exists, and you assign ownership to it, and you say, "Yep, it's a risk. We know it. Here's the team or the group or the executive that owns this." You can avoid the risk by putting other mitigating controls in place, other security controls in place that basically will reduce or eliminate that risk. You can mitigate it by just fixing the issue. That'll mitigate or remediate. That'll actually remove the risk completely. Or you can transfer the risk. And this is a concept that maybe people are familiar with in terms of insurance. Many companies purchase cyber insurance to be able to use in the event that something happens. The same thing with car insurance or health insurance. You pay premiums, and then when something happens, you call it in and you pay your deductible, and they'll cover you for the cost of whatever you've negotiated with the insurance company. So which one to use? Well, it really comes down to in terms of accepting or mitigating or using your insurance, transferring risk. It really comes down to, again, the amount of money that you have to spend to fix it, and the amount of money that you're trying to not lose. So if the risk level is very high, but the cost is very low, well, then obviously that's something that you want to fix. You want to fix immediately. If the risk is high and the cost to fix it is low. If the risk is low, but the cost of fixing is very high, like I said, that's something that you probably don't want to pursue because it's just not worth it. And you want to at least address the issue. You accept the risk, and you talk about, again, as I mentioned, maybe it's a way. Maybe you want to look at sunsetting that application or that feature because maybe nobody needs it, or you look at other paths to migrate clients to something different. But the bottom line is that there are cases where the amount of effort to protect something is greater than what you're trying to protect. And in those cases, you want to try to avoid that. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to do a walkthrough of a risk rating. Now, this is a lot more fun in person and in a group, but I just want to give you a sense of what risk rating entails, what it looks like, some of the things you want to think about. So let's start and talk about the actual application that we want to do that's part of this risk rating that we're going to perform here. So I threw in here a little bit of a background on an application that we're going to use for this risk rating. It's called My Health Records. It's a software as a service application, so it's deployed to, let's say, the cloud, and it provides the ability for a user to view their medical records from multiple sources. So for instance, maybe your doctor's office, your dentist, your insurance company, they're all able to send data to this My Health Records, and you're able to go there and look at the information that they've put out there. So just some functional descriptions here. Users must authenticate with a username and password. We're not going to assume any kind of SSO or OAuth or nothing complex in that sense. It's just multi-factor authentication. It's just straight up username and password. The application only allows view rights, not updating of medical information. So you can go to My Health Records, you can see the information that's there, but you're not allowed to modify it or anything like that, or delete anything like that. It's just pure view. User can then access the application from multiple devices as long as it has a browser. So there is not a mobile app, but you're able to view obviously on your mobile device if you open up a browser and view it from there. You can do it from a desktop, a laptop, anything that has a browser. The document viewer allows for search of medical records using a date range, keywords, and encounter location. So basically there's different ways of being able to narrow down your search to be able to see the medical records that you're interested in. And then you can print documents. So that very slimmed down function here, it's not very robust. It's just basically viewing medical records, simple interface. So what we're going to do is we're going to go through a bit of a risk rating here, and we're going to use this securitynet.biz files OWASP riskcalc.html. It's an online version of OWASP's risk rating calculator, and you can find the risk calculator, which is you can get it in an Excel format. You can also, they'll give you the formulas so you can do it on your own. But this one's an online version. It makes it a little bit easier to do it in this type of setting. So here we are in the risk rating calculator. And like I said, the application we're going to model, it's pretty bare bones, simple. You can view medical records. You can browse, do some searching and browsing, print out your medical record and so forth. So there is the ability to enter in a search bar. So let's go ahead and assume that that search bar has SQL injection in it. So again, very simple, basic UI and very basic concepts around the application. So we could think of something like maybe there's an issue with the login. Maybe there's a way to do some parameter tampering and view other records. If you were an attacker and you were trying to compromise My Health Records, the SaaS application that we're talking about here, those are the things you might want to try to break. Maybe you want to see if there's proper authorization in place and you want to elevate your rights to admin, or you want to be able to view medical records from other patients or something. So there's a lot of different things that we could think of from a risk perspective. So let's just keep it simple and say it's a SQL injection, because I really just want to focus in on the risk rating aspects of this, not necessarily on the vulnerability part. So let's assume that it's a SQL injection that can be entered into the search bar within the My Health Record application. So if we're saying that it's a SQL injection, and we know based on SQL injection that there's a lot of different opportunity there, to do a lot of things, and it really depends on what it is that the attacker is trying to perpetrate. So we could say that the attacker is trying to modify a record. Maybe they want to change some values in one of the medical records. Perhaps they want to erase some of the medical record information that's in there. Maybe they want to view other medical records that are available. Maybe they want to try to see if they can get different credentials. So there's a lot of different things that we could think of here. But let's say it's a SQL injection, and the attacker is we have a lot of other controls in place. Again, we're sticking hypothetical here, but we have a lot of other controls in place to block things. And maybe our remaining risk that we have here is that we're concerned. The risk is that an attacker can use SQL injection to tamper or modify the record of themselves. All right, let's just keep it scoped to that. And that's one of the important parts of this is that, there may be other risks that are of concern, but we want to keep it scoped appropriately. So we're going to say that an attacker would be able to inject SQL injection to modify their own medical record. So when you go through this risk rating, you want to start with, as we talked about before, with the threat agents and the vulnerability factors. This is all part of that likelihood. And if we remember, risk is likelihood multiplied by impact. That comes out to risk, right? So there's the threat agent factor. So what's the actual skills and motivation of the threat actor? There's the vulnerability factors of this around, discoverability and exploit. And then we have the technical factors that we're concerned about from an impact perspective, and then also the business impact that we're concerned about. So we're going to go through each one of these, and just again to keep it in your mind here that we're talking about a attacker injecting SQL injection to modify their own medical record. So let's say what are the skills that would be needed for this? Well, we may say that some technical skills, at very least, some technical skills, maybe even advanced computer skills. And so you can see as we start going through this that it can become very subjective. So it depends on who you have in the room, and that's why it's important to make sure that you have people from a lot of different areas, whether it's the security folks, you want to have the product people that are responsible for the product. You want to have engineering that's familiar with the product as well. So let's say in this case, the skills required, we're going to keep it scoped to, let's say it's an advanced computer user, because doing some SQL injection does take a little bit of skill. The motive, maybe they want to change it. Let's say maybe the information shows a failed drug test, and they want to go in there and change that. So it's not really a reward in this sense, but being able to change something like that may get them into a job that they really want to get into, and maybe that's a high reward for them. The opportunity, special access or resources required, some access or resources required, no access. So we should assume here that the user would have to actually be logged in to be able to view their medical record. So let's say you need to at least have special access or resources required. Let's say you need some. You need to be logged in. You need to be authenticated. And what's the population size? Well, this is probably scoped to a small. You would need to be authenticated, right? So it's a small subset there. So when you look at, is it anonymous users? No, they need to be logged in. But it's not partners. It's not limited to just the partners of the application. All right, so we have our threat agent completed here. What about the vulnerability factors? What are the ease of discoverability? Well, if you're skilled enough, you could probably uncover that. And there are automated tools. We know that tools like OWASP Zap exist to do that. So let's say it's easy, because maybe the automated tools might trigger some alerts. Ease of exploit. Wouldn't say it's difficult, so I would say it's either easy or automated, because again, there are fuzzing tools and things like that exist that would be able to uncover this and maybe help you out a little bit. But let's say it's not necessarily automated. Let's say it's easy. The awareness, it's not obvious, it's not publicly known, because maybe it hasn't been publicly known yet. So let's say it's at least hidden. Intrusion detection, and this gets down to what we talked about before about the logging and actually reviewing those logs. A SQL injection, a change to the database would most likely be logged, but let's say logged maybe without review. All right. So again, you can see here where it's important to have the right people in when you're doing these risk assessments, because you may want to ask those questions about, is this logged, and more importantly, do you have processes in place to be able to review those logs? Because if it's not being reviewed, then that's going to obviously change your answer to that. So we're now going to go over to the technical impacts. And so when we look at technical impacts, loss of confidentiality, well, we're not going to lose data, right? Because this particular risk is only exposing the medical record of the individual attacker, so minimal non-sensitive data disclosed. Loss of integrity, yes. Somebody is trying to corrupt data, but maybe they're only it's only, again, we only scoped it to their own record here, so minimal slightly corrupt data. I think that's probably right. Actually, minimal serious, most likely. Loss of availability, it shouldn't have an impact to availability. The system should be available. So we'll say it's minimal. Loss of accountability, attack fully traceable to an individual, possibly. If you're able to tie it back, you would possibly be able to trace it back to that individual. But again, it really depends on your logging. So if we said here that it's logged without review, then maybe the traceability is a little bit less likely. So business impact factors, we'll talk about financial damage. It's probably not going to cost the company much because it's a security issue, but they didn't lose a lot of data. It's one incident. They can probably handle that. So we'll say damage cost is less than the fixed issue. It's minor effect. Let's keep it low. Reputation damage, probably again minimal damage. This probably wouldn't trigger any kind of, there wouldn't be a wide announcement of this. Chances are it's not going to have a huge impact on client base. So probably say it's minimal damage. Non-compliance could be a violation depending on the laws there around, specifically around HIPAA, but with no data being exposed, probably not a huge impact there from compliance. So we'll probably say it's a minor violation. Again, privacy violation, nobody's really been impacted except for the attacker here. So we'll just say one individual. So you can see here, when we go ahead and calculate, so we got, from a likelihood perspective, we got a 6.2, which is high. From a technical impact, we got a medium. And from a business impact, we got a low. All right, so we can take those two together as well and come up with an overall, the overall score here is low. The business impact was 1.7, the technical impact's 3.25. So you can see here that we rated this as not really from an impact perspective being that impactful. Maybe from a technical point of view, we're concerned about the integrity of the data, at least for that one user. But from a business perspective, it's not really going to cost us a lot of money with this particular issue. Now that could change depending on, depending on what you're looking for and what you're trying to find in terms of, especially around compliance, and especially if there's other legal issues that come into play there, your business impact might go higher if you have to pay a lot of fines or other things like that. So, but based on the way that we rated this right now, if I was looking at this, I would say the overall impact is so low that it may not be something that we're terribly concerned about. But because of the likelihood, it's something that we should consider. So maybe you would overall rate this as potentially a medium, something that you would want to fix, but it's not a critical or high issue. And again, that's just balancing that business versus the likelihood, or the overall vulnerability and impact. So with that, I hope that was interesting. Again, it's a little bit more fun when there's a group of people and we all sit down and go through these, because you really get to see where other people's minds are at when they're trying to understand these risks. And you also have to make sure that the scope is properly positioned at the beginning, because you want to make sure that that you're within that scope, so that you're not going down those Hollywood scenarios like I mentioned before. So again, I hope you enjoyed this lesson, and I will talk to you again. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about threat modeling. So threat modeling is a structured approach to identify, quantify, and address the security threats and risks associated with an application. And this is an investigative approach to identifying those risks and threats. And typically it's done in a group with multiple people, different SMEs, subject matter experts from both from security, also those that know something about the product. So we're going to talk about some definitions. Some of these you probably were already familiar with that we've already covered in this course. But an abuser is someone who would misuse intentionally or unintentionally an element of the system under consideration in the threat model. So this can include hacktivists, cyber criminals, advanced persistent threats, also script kiddies, and all the other different types of threat actors that we've talked about in the past. An asset, like we spoke about before, anything that we deem to have value. So that could hold value, provide access to value, or produce value. And so some examples, the money, precious metals, house, car, data, social security numbers, PIN numbers, all of these are considered assets. So when we talk about threats, it's a means by which an abuser might compromise an asset that has potential for success. And we want to make sure that we remember that threats aren't just actors. When we think of actors, we think of people, but threats can also come from places like earthquakes, natural disasters, floods, tornadoes, wars, political unrest, and so forth. So threats can take many different forms, and it's not always an individual or a group of individuals that are trying to perpetrate attack against your system. So when you think about companies as they determine where they're going to put their data centers, they typically put their data centers in places that are not prone to natural disasters, are in politically stable locations, and the purpose of that is because they're mitigating those potential threats. And the other thing to keep in mind is that intention is not necessarily a factor here when it comes to threats. So something like a hard drive failure or some other type of hardware failure is just the likelihood of that happening is pretty high. So that threat should be considered just as equally as somebody or a group of people trying to attack your systems. So let's talk a little bit about hazards versus threats. So a hazard is a potential source of harm or danger. So it's a potential. It's a harmless state with potential to change into a threat. A threat is a specific type of hazard involving an abuser potentially harming an asset. And that means that it's actually in a harmful state, not in a potential, not potentially a threat. So tree hazards are a great example of this. I live around a lot of trees. My house is around a lot of trees. And the trees themselves aren't necessarily dangerous. They're not a threat, but they're a hazard because dead limbs or something like a storm or high winds can turn it into a threat where a tree could fall over. In fact, I had a tree at the end of my driveway that always had me worried because my cars were, both my cars were parked there. My house is right next to it. If the tree came down, it could take out, both my cars and potentially a house. That's a huge, threat to my personal safety, to my assets. So that's a prime example of the difference between a hazard and a threat. So what about a risk? So a risk, that's the potential for loss, damage, or destruction. So really, it is a threat actor acting on a vulnerability to create to reduce the value of an asset. All of that is the risk. The potential there is the risk. So based on previous example, the mechanical failure of a hard drive is more likely than, say, an advanced persistent threat gaining access to your overall system. However, because it's more likely. However, it's not the impact there is going to be low because you're going to have redundant systems. You're going to be able to replace that hardware failure pretty quickly. So therefore, you may not even notice any operational issues from a hardware failure. However, an advanced persistent threat, even though it's less likely, the advanced persistent threat still has the opportunity to create a much broader damage to your system overall. So that's risk, where it's really the potential, like what's going to happen here if what's going to happen to our business operationally, to the systems, what's going to happen here if this does occur. And again, the risk is low from the perspective of a hardware failure, because you have a lot of redundancy built into the system. Therefore, you're not too concerned about the risk. So let's talk about identifying, quantifying, and addressing the different risks and threats. So one thing to keep in mind when you're, especially when threat modeling and understanding risk and threats, is that we don't always want to take our knee-jerk reaction, our first instincts and our gut, basically is that humans naturally are fearful of things visual. Like very quickly, they can come to a conclusion that it's a threat, or that they're at risk, without really thinking it through and understanding whether that's really accurate or not. The other thing to keep in mind is, keep out of, try to steer clear of the Hollywood type of scenarios. And we call them Hollywood scenarios because, if you're trying to figure out the different risks to your data center, somebody helicoptering in and rappelling inches from the floor and cutting cables and, replacing network cards. Yes, somebody could do that. That's really, really, really unlikely. It's not something that you want to necessarily just throw out. Maybe there's something there that you do want to kind of consider. Something along the lines of, yes, maybe physical access to the data center by somebody that's not supposed to be there. That's concerning. But think about the way that person would get in there. It's not going to be from a helicopter rappelling into your data center. So that's what we talk about. Trying to steer clear of those Hollywood type scenarios. So, as I mentioned, humans are kind of very susceptible to having a knee-jerk reaction to something that they deem a risk. So in this case here, if we look at these two pictures, there's a grizzly bear on the one side, and the other side there's a flight of stairs. And so commonly humans, and myself included, if I was faced with a grizzly bear, I would probably freak out. But if I was faced by a flight of steps, I would probably be just fine. The truth of the matter is that bears kill about one person per year, whereas stairs kill about 1,500 people per year. So stairs are far more dangerous than bears. However, we all know this. If you're faced with a bear, you're probably gonna be a little bit concerned and consider that a bigger risk. But that's just an example of where mentally, as humans, we tend to go to things that are flashy and say that's the bigger risk, when in reality it could be something a little bit more benign. So some of the things we also want to try to take out of our vocabulary when we're talking about risks and threats is that we don't want to go down the path of saying, well, the attacker would need to be on the internal network and things need to be in such a way in order for this to be a true risk. It's fine to kind of, again, think about those things and understand what are we really trying to capture there. But at the same time, those types of phrases, what happens is it tends to make people check out. So they say, oh, well, there needs to be a special circumstance for this to happen. So therefore it's not really very likely. The reality is, an intruder on the inside of your network is not that uncommon. So you don't want to take that and say, they'd have to be on the inside of the network. So that's not a big deal. It can be, it does happen. It is a big deal. And if the other thing to keep in mind is that if you don't have all the answers to the questions that are being asked, that's okay. Write them down and make sure you do the follow-up to get those answers later on. Document any assumptions you make and follow up. Same with the questions. So a couple other things. Don't assume that you have a secure environment, because chances are you don't. There's a lot of different compensating controls that can be inside of a data center or a network. You don't always want to assume that those are there and available and working. You shouldn't assume that your hardware is reliable either, because again, as I mentioned before, hardware failures are frequent. It may not be a big risk, but it does frequently happen. So don't always assume that your hardware is going to be available. And the other thing is, when threat modeling and doing risk assessments, is that you shouldn't assume that your environment is correctly configured. So similar to making sure that you don't assume that your environment's secure, You also don't want to make sure, or you also don't want to assume that it's correctly configured, because a lot of times it's not. So we talked about the defense in depth principle in previous lessons here. Just to reiterate, the defense in depth principle is that you have a lot of other controls in place. And we gave the example of a castle. So you have a castle with some walls, you have gates, you have a moat, you have archers on the wall. And so the idea there is that you have a lot of other controls in place to help protect your assets. This is very similar to from a data perspective, what we're trying to protect. And in theory, you don't make trade-offs between security or defense and performance. The reality is that, yes, of course, every day we make decisions in terms of, is this security control we're putting in place, is that going to cause an undue burden to the performance of the application? And the answer is almost always yes. So, there is trade-offs. What's the risk, and what's the risk to the business in terms of not being able to perform it the best way that it can? So some of the benefits of threat modeling is a better understanding of your architecture, and really that what happens is when we build out a threat model, we're building out the architecture of the system and understanding all the different interactions and interoperability points, and that allows us to have a good view of what the architecture looks like. It allows us also to create reusable architecture that maybe there's parts of the threat model that you look at and say, this is pretty strongly secure, so this is something that we can leverage in other products that we're developing. And the other thing is that you can use threat models as input into other types of security tools, such as penetration testing or scanning tools during code reviews or risk management. So the idea that you're creating this artifact that can be reused to help guide your other security practices. And with that, I hope you found this insightful, and I look forward to seeing you in the next lesson. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about the different types of threat models. So first, there's two different high-level types. There's a manual method, and then there's the using the tool method. So from a manual perspective, this is more favorable in terms of the quality of threat model that you're going to get and the ability to customize the threat model. Because basically you need a whiteboard and you need subject matter experts from product, from engineering, and from security to basically get together in a room and talk about the architecture, the system, and the product, and determine the different threats that might be an issue or might be posed against the system. The biggest problem with that is that it's not scalable. So obviously getting a lot of people into a room in front of a whiteboard is not something that you can do in a short period of time, and it's not something that you can do multiples in like a day, or a given week. You have to do that multiple times in a very large amount of time. So that's why there's a lot of tools out there to help to do these threat models. So it's a little bit more scalable when you're using a tool. The problem is that there's not always consensus on which tool to use. There are engineering teams that will use wikis, PowerPoints, Visio diagrams, or other types of drawing diagrams, or look at a threat modeling tool itself. So this can kind of lead to a check-the-box mentality as well. That's part of the issues with the tool, is that you may come to the conclusion that, hey, I created my threat model, everything's great, I don't need to do anything else. But that's not always the case. So the manual one is more preferable, but much more difficult to scale. So there's a couple different types of threat models out there. In fact, there's a lot, but these are probably the three more popular ones. So there's Octave, Operational Critical Threat, Asset, and Vulnerability Evaluation. This focuses on non-technical risks that result from breach data. And assets are identified and classified, and that's how you determine what it is that you're trying to protect and the threats to those assets. The problem is that with this particular type is that as those assets grow, you need to bring them into the threat model, which means that you need to revisit and expand your threat model each time you bring in new assets. PASTA, which is a process for attack simulation and threat analysis, is an attacker's view of threat modeling. And so this allows you to develop the actual threats, enumerate them, and score those different threats. So this gives you a bit of a higher level view of the threats that are incoming. This allows you to go to the senior management and executives and say, here's the threats that we're most concerned about, and they can prioritize which ones that they want to focus in on. So it doesn't really get down to the requirements aspect, like developing the requirements. However, Stride does. And this is used in Microsoft's threat modeling tool, as well as in Microsoft's secure development lifecycle. And the way to think about this is that you draw a diagram, a data flow diagram, or an architecture. And this allows you to define boundaries and data flows, and then identify the threats that are part of that data flow. And STRIDE stands for spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. And we're going to go through each one of those here next. So spoofing is basically masquerading as somebody else. And a lot of times this can occur through stealing of username and password, or otherwise credentials. So an example here is a threat action aimed to illegally access and use another user's credentials, such as username and password. And the security control for something like this is proper authentication or strong authentication. Obviously, if somebody's able to steal a username and password, one of the ways of protecting against this is using multi-factor authentication, where you need more than just the username and password to be able to access functionality. So with tampering, we've talked about before in the confidentiality, integrity, and availability, the CIA. So for tampering, that's a breach of a break of integrity. So this is the intentional modification of products in a way that would make them harmful to the consumer. And the example here is threat action aimed to maliciously change, modify persistent data, such as persistent data in a database, and the alteration of data in transit between two computers over an open network such as the internet. So I think when we talked before with integrity, it's if I send something from point A, when it goes to point B, it should be identical from what I sent in point A. If it's not, then it's been tampered with. So there's some security controls we can put in place there in terms of hashing algorithms, checksums, digital signatures, and such. So with repudiation, this just basically means that I can't deny that I sent something. The definition is a little weighty here. So an example here is a threat action aimed to perform illegal operations in a system that lacks the ability to trace the prohibited operations. So think about your laptop that if you're using it in a corporate environment, the laptop may have been issued by the company that you work for, and the company wants to be able to ensure that anything that's been done with your laptop, if it's a violation of policy, that they have the ability to trace it back to your laptop and to you personally. So that's an example of repudiation. There's other things to think about where if I send a message, there should be a means to go back and know that I sent that actual message, or at least that the device sent that actual message. So that's a repudiation. So using things like encryption, digital signatures, and notarization is our proper security controls for that. And then for information disclosure, this is the C in CIA for confidentiality. So this is the intentional or unintentional release of secure or private confidential information to an untrusted environment. And basically, we know what this means. It means that data or documents or some other type of information or asset was exposed to somebody that shouldn't have had access to it. And no big surprise there, the security control for information disclosure and confidentiality is encrypting. So you want to make sure that you're encrypting things in transit using HTTPS, or if you're transmitting files, maybe secure FTP. And then encrypting your databases and encrypting files at rest that have information that should be kept secret. So denial of service, this is when something is made unavailable. So again, leaning back to the CIA, this is the A, or availability in CIA. And denial of service just basically means taking something offline or making it unavailable for legitimate use. So an example here is a threat aimed to deny access to valid users, such as by making a web server temporarily unavailable or unusable. So this would be if you try to go to google.com and it didn't load. That's an availability issue. There's a lot of different ways of trying to protect against this. Most of the time, just based on the way that networks have expanded so large, and things like botnets where somebody's able to procure thousands of machines to be able to point at a service or a web server or a network and be able to flood it with requests, there's not really a good way of trying to stop that, because a lot of that traffic looks legitimate. So what tends to happen is that a lot of companies will go out and buy services that will just scale to at a potential attack and be able to just basically absorb it. And that's more or less a lot of the protection now. It is getting more intelligent and being able to understand when an attack's occurring and be able to shut down traffic if it does look like a certain pattern. And the last one is elevation of privileges. So this is an example of being able to access functionality or log in as somebody with higher privilege than what I'm supposed to have. So this is the act of exploiting a bug, design flaw, or configuration oversight in the operating system or software application to gain elevated access to resources that are normally protected from an application or user. So you can think of, if I go to Amazon.com and there's an admin portion of Amazon.com, me as a non-Amazon employee and just as a shopper on Amazon, I shouldn't be able to have access to admin functionality. And there's ways of trying to protect against that, but bottom line, it comes down to making sure that you're doing authorization checks on every single web request that your application sees, so that you can ensure that that person or that user or that it could be a system trying to access an API. You want to make sure that that has the appropriate rights to have access to what it's actually requesting. So with that, I hope you enjoyed this lesson, and I appreciate your time, and I'll talk to you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to go over the manual process for threat modeling. So a couple things that you need to keep in mind when we're doing a manual threat model is that you need to keep an open mind. You need to have a whiteboard in order to draw out your architecture and keep track of the different issues that are going to come up around threats and risks. And you need time. As I spoke about earlier, the manual process for threat modeling takes time, takes people, takes resources. But so from the bottom line, you need an open mind, a whiteboard, and some time and resources. So best done in groups, meaning that it's best to have the SMEs or subject matter experts for the particular project or system that you're trying to do a threat model for. You want to make sure that you have solution designers as part of that, the development team, product owners, architects. You want to have security people there as well. But you don't want to have a large group. So you want to keep it small, somewhere around the 6 to 8 range. Again, that's not a hard number, but you want to make sure that it's small so that it's not... you'll find that in a lot of these types of exercises that the more people that are there, the more likely you're going to get a lot of wide-ranging opinions and comments. And sometimes that's helpful, a lot of times it's not. So it's good to keep the size manageable so that you can deal with all the questions and comments that come in a manageable way. So who's the audience? Well, you want to have your team. So if you're the person that's owns the development or owns the product, you want to make sure that the threat model becomes a reference for understanding the security of your solution. So as I mentioned before, it's a good opportunity for you to create architecture that can be reused, something that is an artifact that's developed for your specific solution. So your team is obviously the prime audience member here. You probably want to have some pen testers as far as enabling them access to this threat model so that they have the ability to understand where the different weaknesses are in your system. We talked about that before as well, is that threat models can be inputs into a lot of different types of activity, penetration testing being one of them. And then, for instance, other teams, you want them to be the audience for a threat model too. And this is once the threat model is complete. You don't necessarily need them there for the activity in and of itself. But you want to make sure that other teams are at least aware of your threat model so that if there's any reusable components or components that are shared amongst your team and other teams, that if you identify threats in those components, you want to alert other teams that issue is there. And then your clients, they may want to have access to your threat model as well. That's not consistent across the board. You may not see that all the time, but it's not unlikely that a client may ask for a threat model. So some of the things you want to keep in mind as you're building your threat model is you want to understand the scope. What is it that you're building, the system, the technology? You want to have all that in mind, or at least have the subject matter experts there that can answer that question. You want to talk about what can go wrong, because that's the purpose of the threat model, is what are the risks, what are the threats that are associated with this. And as we spoke about before, threats aren't necessarily a malicious actor attacking your system. It could be something like natural disasters or failures. So what should you do about those things that can go wrong? What are the mitigations or remediation plans to address those threats that are identified? And then, did you do a decent job of analysis? So you want to make sure that once the threat model is complete, that you do actually validate the threat model. Number one, were the threats that you found true threats? Were some of the assumptions that you made around the mitigations that are possibly there, are they actually there? Are they working as intended? So these are the things you want to keep in mind as you're thinking about building your threat model. And then always keep in mind that threat models are never complete. So they're a living artifact. It's similar to an architecture diagram or an architecture or system diagram or system documentation. We all know that for those that work in development, that those types of documents go stale very quickly. So for instance, if you're developing software, you may have a release in, let's just say for sake of argument, in January. Well, by February, you probably have had at least one more release, maybe multiples, or at least working on a new release. That means that your system architecture has changed. Same thing with the threat model. You want to make sure that the threat model is being updated to take into consideration the changes that are being made within the system. So when we're doing a manual threat model, what we want to do, and this is why I mentioned a whiteboard early on, is that we want to first draw out the architecture. And I threw a little simple architecture here on the board with a browser, a web application, and a database. And what you want to do is draw a grid that says who, what, why, how, impact, and countermeasure. And what might also be helpful is having stride, which we talked about before. Now, again, if you're choosing a different type of threat modeling, whether it's PASTA or Octave, you may want to put that there as a reference as well. But in this case, we're using stride. So we're going to write the stride acronym on the right. So spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. And then below the grid, you want to throw a little bucket down there for Hollywood scenarios. So again, these are the ones where perhaps they're not something that you necessarily want to disregard, but you do want to put it in a separate container so that you can revisit it at a later time. So again, what you want to draw out here is the who, the what, the why, the how, the impact, and the countermeasure. And this is the process of that manual threat model. You're going to create a grid with multiple rows below that, and in each one of those, you're going to start identifying things like the who. So who, if we're a financial institution, we have a lot of money that is potentially a good target for somebody like in the cyber criminal space, and we talked about threat actors. So, if we're a financial industry business, then chances are cyber criminals are looking to create fraud scenarios or just flat out steal money. So for us, we're going to say, hey, the Russian mob is what we're concerned about in this case. And what is it that the Russian mob is after? Well, they're after the credit card information that maybe we store in our databases. Why are they doing it? Well, they're trying to get financial. It's for financial gain. The purpose is to steal money. How are they going to do it? Well, they're going to try to do maybe a phishing campaign in order to try to steal credentials or gain elevated access to something. So what's the impact? It's limited to targets. So whoever may be the target of that phishing campaign, it's limited to them. And what's the countermeasure that we would put in place to protect against this? Here we're just going to say it's two-factor authentication. So that's a simple example of a line item in a threat model that we would try to address. Now you may go on with that and say, continue with perhaps it's the Russian mob that we're still worried about. Maybe there's a different type of attack that they're going to try to leverage, and perhaps that's to gain access to our load balancers or something to that effect, right? So you see how you can continue down that path until you identify all the different threats that you feel are warranted against your system. And that's the process of a manual threat model. So this is a good example of a high-level example of a simple web application with the basics. But remember, the important parts here is that you want to have an architecture diagram. You want to have a grid that has the who, what, why, how, impact, and countermeasure. You want to have a block for Hollywood scenarios. For instance, if we want to say that the Russian mob's going to drive a T-30 tank into our data center and run over our guards and run off with the hard drives. Sure, that could happen. It's extremely unlikely. So we'll put that down in the Hollywood scenario. Maybe you work off of that and say it's not that the Russian mob is gonna ram a tank through our data center, but maybe there's a possibility that somebody may try to breach the gates with a truck or something like that. So you may want to think about that and say we need to have more robust physical security around our data center. So again, you want to have the grid with the who, what, why, how, impact, countermeasure, the Hollywood scenarios, and then keep, just as a reference, you want to keep the threat modeling technique that you're using. Again, in this case, we're using Stride. You want to keep that there as a reference so you can remember what it is that you're trying to put that threat in the context of. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to actually walk through a manual threat model. So for this threat model, let's think of a retail store, and think about your favorite retail store that you may frequent, a place that sells clothing, food, other supplies, things like that. So in a store like that, there's going to be a back office management of the store. That's where the manager sits and processes payroll and works on a schedule and things like that. There's also an inventory management that's probably done out of that management office. So there needs to be the ability to be able to view and modify the inventory, and also to be able to create staff schedules on the system that's plugged into the network. And then also you want to consider the payment system, point of sale system. So that's going to be what processes the credit cards at the register, and also some way of collecting that information, probably in the back office, again on that system that's in the back office. So customers need to be able to pay with a phone, card, or cash. Staff need to be able to check out a customer as well. So that's all part of that payment system. Also think that there's probably going to be a kiosk within the store. This is where a customer can go check prices on an item that they might be interested in buying. And then there's going to be remote management of lighting, heating, cooling, and water systems. So think of the HVAC system and the other components that keep the lights going and the temperature within the building within a reasonable level. So there's going to be an HVAC company that has remote management of this HVAC system. The store management needs to be able to access this system as well remotely. So both the company that manages the HVAC as well as the store manager, both are going to want to manage that HVAC system. And then also there's going to be CCTV, or closed circuit television. So it's a surveillance system. There's going to be cameras around the building, cameras within the building. And store manager needs to be able to remotely view this feed. That's one of the requirements. And then the loss prevention team within the store, not just the manager, but the loss prevention team also need to be able to remotely and in store be able to view this. So with all that in consideration, here's a kind of a loose architecture of what that retail store should look like. So you're going to have your boundaries for internet access, for the HVAC system, for the managers, and the loss prevention to be able to access the different the closed circuit television, as well as the management of the heating and ventilation and all that. And then within the store, you have your application, your kiosk, all that other stuff. So this is basically a loose diagram of what that architecture should look like. Again, you may draw it differently, but this is just to help us kind of understand the different components of the system and where they lie. So speaking of the components of the system, we want to consider all the different devices that are part of this overall system. So not just the store's devices, but also the customer devices. So as I mentioned before, clients need to be able, or customers need to be able to pay with their phone. So that's a device that they can bring into the store. There might, we don't include this here in this threat model, but There might be options down the road for maybe the store to push notifications to people's phones as they're in the store. So the customer's device is part of this when you're considering, especially when you're considering threats. The customer device is one of those things that should be in consideration there. You also want to think about who interacts. So it's not just the store employees and the manager, and actually not even just the customers, but it could be your rivals, rival stores. It could be somebody doing some investigation within your store. So there's a lot of different people that you want to, actors that you want to consider when you're thinking about your threat model. What are the external entities? So your inventory system, your third-party ordering systems where you're ordering more inventory and managing your inventory. So those are going to be external entities that you interact with. And then who has access? Again, thinking about the actors. So you have your HVAC, your repair people, security, your loss prevention people, cleaning people, and then of course your employees, your managers, and then customers as well. All right. So as I mentioned before, when we were talking about creating threat models, you want to think about the five components of this: the who, the why, the what, the how, and the impact and countermeasure. So the who should cover not just the threat actors, but the users of the system and as a whole. So again, as I mentioned, you want to make sure that you consider your customers as well. The why should cover the motivation that is identified by who. So why would somebody want to potentially harm your system? That plays into the who as well. And then the what are they trying to do? What are they trying to steal, break, or misuse? How are they going to do that? You want to think about the practical examples. Again, stay away from the Hollywood type examples. And then what's the impact of that being successful? And then what are we going to do about it in terms of guarding against it? So with that in mind, let's kind of talk through two scenarios here. So for the who, let's say there's cyber criminals, because that's kind of the easy one to think about here. What are they trying to steal? They're trying to steal credit card numbers. And why would they do that? Well, because they want to make money. So there's a profit motive there. How are they going to do it? Well, they're going to try to install skimmers on the credit card machines themselves. And for those that may not be familiar with them, these are just little devices that slip over top of a credit card machine and actually steal data from that credit card machine as the credit card is put in. And then what's the impact there? Well, it's loss of reputation and possible loss of revenue, because the store may have to pay maybe some credit monitoring, maybe some loss revenue, or pay back clients or customers. So there's a lot of in terms of loss of profit or loss of revenue there. So what's the countermeasure? Well, maybe this is more of a process and people resolution here or countermeasure, but we probably want to have people, go around and check the credit card machines. Maybe it's every couple hours, maybe it's every day, depending on how you view this risk. Is it going to be frequent, or what's our tolerance there in terms of risk? You may want to have it every few hours that somebody goes around and checks the machines to make sure they weren't tampered with, or every day or every week or whatever your process or policy may cover in terms of covering your risk. So what about another example here? So maybe there's a rival store. So maybe there's a store down the street that is your strongest competitor. So what are they trying to do? Well, maybe again they may hire somebody to try to create an outage for your website. And then what's that going to do? Well, they want to try to reduce your customer base and maybe drive customers to their website or their store. How are they going to do that? They're going to use DDoS. They're going to hire somebody to DDoS your site. So what's the impact there? Well, you can have loss of customers and again, loss of revenue. So kind of similar to the one above, in the sense that when your website's down, you're losing revenue. You're not making money at that point. Also, customers that can't access your site may go to your competitor to get something that they wanted to buy that day. And then what's our countermeasure? Well, we're going to use a third party to something like Cloudflare or something to be able to withstand a DDoS attack. Now, that last one, the rival store, we could probably say maybe that's Hollywood scenario. because it's not that it's far-fetched, but it's unlikely. If you think about some of the big, at least here in the United States, if you think about some of the big box retailers like Walmart and Target, it's unlikely that Walmart's going to hire somebody to DDoS Target, but I guess you never know. And again, it's good to think about this thing because maybe it's not a rival store, but maybe you might be held for ransom, by a cyber criminal who wants to DDoS your site on Black Friday or an important shopping day. So with that, I hope you enjoyed this, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to start preparing to use Microsoft Threat Model, the Microsoft Threat Modeling tool, in order to generate a threat model. Now, as I mentioned before, there are other tools in the space of threat modeling. We're using Microsoft's tool because, number one, it's free, and it allows us to create threat models using Stride. It's an easy tool to get up and running to create a simple threat model. Again, because it's free, it's accessible to a lot of different people. So with that in mind, before we start creating the model, we want to identify the documentation that's required. So architecture and system documentation, diagrams, things like that are going to help us build that system model. And then once we have that system model built in the Microsoft tool, we're going to then identify the threats, and Microsoft does that. The Microsoft tool does that for us, and then we're going to address the threats. So we might mark them as not applicable or put a mitigation in place. And then the most important step is to validate the model. Make sure that, number one, that the assumptions that we have are accurate, the mitigations that we have are accurate, and that the threats are actually accurate. So using Microsoft Threat Model, the architecture is drawn out. In other words, in the tool itself, we're going to create an architecture diagram within the tool. The diagram should be as in-depth as possible, but should not be so much that it's distracting. So in other words, and we're going to talk about this here in a minute, but don't create an eye chart. So you don't want to create something that's so difficult to read that it just becomes unwieldy and the threats are just not relevant. So the scope of the diagram should be identified as well. Some things that I usually try to keep in mind when creating a Microsoft Threat Model is that, I want to keep in mind the things that I actually have control over to change. So in other words, if I integrate with a third party and perhaps they're calling an API of mine, well, my ownership of that API means that I'm responsible for the changes there, but the ownership of whatever service or system that is calling my API is not anything I have control over. Now I can tell the vendor, hey, these are things that we're concerned about, but it's not something I have control over to change. So therefore, something like that is not necessarily in scope. So the first thing you want to do, step one, is decompose the application. So you want to think about the scope, as I just mentioned. Think about the things in your system that are things that you can change, that you have the ability to modify. So all the system components, whether that's your web servers, your app servers, your database, your configuration files, load balancers, network appliances, you want to keep all that stuff in mind when you're creating that threat model. The backups, the monitoring and logging, again, those things are key, crucial components of that threat model as you're building it. And then think about the actors and the abusers. So the people, actors in the sense of who's using the system and how are they using it. And then the abusers, who are the potential attackers of the system or where things can go wrong. The process and data flows are going to be pretty evident when we create the Microsoft threat model, because it's basically it's an architecture or system diagram, but it relies heavily on that data flow, and it wants to see where all that data is going within the system. So something about scoping, it's a combination of workflow diagram and an architecture diagram. So as I mentioned, you want to understand the use cases that the actors are using your system for. So it's not just about the architecture, but also how the data is flowing through the system. The purpose of scoping small is to concentrate on a small part of the system so you can get to the end of the threat modeling process. So you don't want to keep on building out that scope and pulling in a lot of different components. You want to try to scope it to something that's manageable and something that you can achieve in a short period of time. Boil down the workflow to something as small as you can. Again, kind of going along those ideas of you want to make sure that you're not trying to encompass everything that's part of your system. But really, what is the biggest threat that you're trying to address with this threat model? Or what's the most concerning part of your system that you're trying to address with the threat model? You may have to build multiple threat models to cover all your system as well. So keep that in mind. For a reasonable complex system, you would otherwise never reach the end. So again, if you have a significantly large system that you're trying to threat model, you don't want to put all that into one model. You want to perhaps break it up into multiples. So first, or second step, once you have all the ideas around the system and the actors and the different abusers, and you have your scope appropriately identified, next thing you want to do is get your hands dirty and actually create the diagram. So the diagram must help you understand and discuss the system's security considerations. The diagram should contain the items determined in step 1. So as we mentioned, identify the scope, the systems, the actors, the abusers. It is okay if you miss things. You can always go back and add it. That's the nice thing about having especially something like a threat modeling tool, where you can it's a file that you can revision and update as needed. So the diagram should show components, data stores, data flows, and trust boundaries. And we're going to get into this as we as we show a demo of using the Microsoft tool. We're going to talk about the different components that you can use within that threat model. But the important part is to understand the different boundaries, the trust boundaries. So where is your on-prem devices? Maybe there's cloud devices. Those are behind different trust boundaries, right? You have a different trust level with the data that's coming from cloud and data that's on your in your on-premise servers. And also you have different trust boundaries for perhaps users that are accessing it. Let's say you have a web application. You may have anonymous users that are accessing that web application. Well, that's going to be a different trust boundary as well. And as I mentioned before, don't create an eye chart. So you want to make sure that it's manageable, something that makes sense, and something that you can look at and understand quickly. Not something that is so complex that it's difficult to really get a grasp on what the system is doing and where the data is going. Now, again, you may have to build multiple threat models, but you certainly don't want to have a threat model that's so difficult to read that it's unusable. So here's an example of a simple web application. So you have a web application in the middle there. You have a database that it's calling. You have a file system that it's calling. And then you have a browser client that's accessing that web application, because that's the purpose of the web application. And you can see here in the diagram the different interactions of data. So you see there's an HTTPS call from the browser to the web server. There's SQL calls back to the database and so forth. And this is a very simple web application. So obviously more complex systems that are calling out to like cloud resources or other systems and interoperability and things like that, the threat model becomes a little bit more complex. But this is your basic run-of-the-mill web application threat model. So you want to understand things like where are the accounts and the different network interfaces that are applied here. What are the different physical computers? So the web application, the database, the file system. Are there any virtual machines that you need to consider here? What are also the organizational boundaries? So maybe there's some pass-throughs between your web application and perhaps even other servers or web applications within your own organization. Maybe they need to be included as well. And then almost anywhere you can argue for different privileges. So that's really what it comes down to when you're talking about the boundaries. When you're trying to define those boundaries, is where do you require different privileges or a different account? That would signify a change in boundary. So last step is that you want to identify and analyze the threats. And the nice thing about Microsoft Threat Model is that it'll do that for you. So once you have the diagram completed in the Microsoft tool, it's going to generate a report that will show all the different threats that are impacting your system. So now that you have a diagram, you can really start looking at what could possibly go wrong with this security. And Microsoft Threat Model does use Stride, so it's going to put all the threats that it finds in the context of spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privileges. And it's going to identify the threats and again, label it as one of those Stride components. So if you're not sure where to start with the external entities that are calling your web application or your system. So in the simple web application example, You may want to just start with the browser that's calling your web application. You start with the browser, start with the web application, and then you start building your system out from there. So wherever you choose to begin, you want to aspire to some level of organization. You want to make sure that everything's properly put in its right place, so that you have all your boundaries set up. And again, keep in mind that the boundaries are any time that you potentially change user context. And then when you address the threats, you can go in order of stride, or you can just go down the list. And we'll show that again in the demo in terms of how you actually want to address those threats. Without some organization, it's hard to tell when you're done. So that's one key component, is that if you're not organizing your threats and your diagram in an appropriate manner, it's going to be hard to understand really when the diagram is actually done. So let's get into a demo here in a minute, and I hope you enjoyed this lesson. I look forward to speaking to you in the next one. Thank you. Hey everyone, welcome back, and in this lesson we're going to go over Microsoft Threat Modeling Tool. I'm going to show you just how to get started here and some of the basics. Obviously, to get more information, read up on the documentation that's out there and other information that may be available, but I'm just going to get you started here and show you a quick little bit of the tool itself. So something that they added recently with the newer versions of Microsoft Threat Modeling Tool is these templates. And you can start with an Azure template, SDL threat model, or medical device model. And this kind of gives you, I'll show you here in a minute, but this gives you stencils that you can work with that will be specific to that template. So let's go ahead and start with an SDL threat model and say create model. And so from here, what you'll see is you have basically a blank canvas. And over here on the right, you're going to see some stencils. And there's a lot of different options here for stencils. But the primary ones that you want to be focused in on are the processes, the data store, the data flow, and then trust boundaries. So for processes, when we're thinking of a simple web application, what we may want to do here is start dropping in some stencils for things that are part of that architecture. So for instance, for a web application, you're obviously going to have a browser client, and additionally you're going to have a web server, and you're going to have a web application. So let's just and actually additionally we're going to want to throw down a database. So we can go here to the generic data store. Let's say we have a SQL database, and then I guess we can leave it at that, or we can say there's a configuration file as well. Okay. And then from there, what you probably want to do is draw out the boundary. And so you can say there's an Internet Explorer boundary. It doesn't have to be Internet Explorer, but we're just going to, just for completeness, we'll do Internet Explorer. And you can also have not just the box ones, but you can have these lined ones. So how about an internet boundary? Because we know that this traffic is going to be going over the internet. So once we have these lines or these stencils that are down and we have a boundary that's defined, let's start drawing the interactions between these different groups. So you have the generic data flow, and we're going to say that it's obviously HTTPS between the browser client and the web server. And just to make it a little bit easier to see here, we'll drag it around. And let's say from the web server to the web application, let's use binary. And if you mouse over, it should give you some information, but it's going to be pretty standard. And you can be more specific about naming these connections if you're positive of the type of connection that's there. Maybe name pipe is probably a little bit more appropriate for this. But this is just a sample here. When you're doing your actual threat model, you may want to be a little more precise about what it is that you're drawing these data lines for. So just again, for simplicity's sake, we're going to keep these as binary. Now, the other thing I want to draw your attention to here is that for each one of these stencils and for the data flows, You also notice here that there's a element property. And so this allows you to configure the way that this interaction works. So for the browser client, you can see here running as, well, it's not kernel or system. It's probably running as a standard user without elevation. And the reason you want to set these is this is going to change the threats that are identified by by the threat model tool. So you can go down through here and select some of these properties. Let's bring this out so it's a little easier to read here. Accepts input from, well, the browser will be taking input from, let's say, how about, well, we could say it's any remote user, right? Because it's getting responses back from the web server. So we'll leave it at that. Sanitizes input. We're going to leave that blank for right now. And then additionally, you can add new custom attributes to add other elements for this property. So for the web server, let's go ahead and set it as sanitize input, yes. Sanitize output, yes. Implements use of communication protocol, yes. Authorization, yes. Authentication, yes. Accepts inputs from any remote user. Isolation, we're going to say it's a local service. And so the whole purpose of that is that when you're going through these different properties, you'll be able to set these elements. And that's going to, again, that's going to enhance the way that your threat model report comes out. So once this is a very simplistic drawing here that we have here. So once you have this done, you want to go up here to View Analysis View. And what that's going to do is actually show you the threats that are associated. And you can also kind of tweak this. I have a tendency to look at it this way. It's a little bit easier. You can set this up any way you want, but for me this seems to be a little bit easier to read. So what this is going to show here is that it identified 19 threats with this particular model that you drew. And what it's going to show here is going to give you the title of the threat. It'll also highlight it here on the window. So you notice here that this is highlighted, and it's going to give you a title, category, and again, Microsoft Threat Modeling uses Stride. So the S in Stride is for spoofing. Going to give you a description, and within that description, it should also provide a little bit of information about how to resolve it as well. So here it says consider using a standard authentication mechanism to identify source processes. So what you can do, it also marks this as a high priority, and what you would want to do with this threat model here is look at this issue. You can say, yeah, maybe that needs some investigation. No, it's not applicable because for some reason this doesn't apply, or we have something in place to mitigate this, so we're not concerned about it. And let's just say we need more information. I'm going to go ahead and say it needs investigating. But we're not sure this is high, so we're going to say it's a medium priority because we don't think it's really a high priority issue. And you'll notice here up in this window that it shows here that it was changed. It's been modified to needs investigation, and it gives you the information that was already viewed here. And also, sorry, it shows that the priority was changed. So you would go through each one of these threats and do a similar review of that threat and provide input there. It also does a changed by. So if you're keeping the threat model in something like a source control where other users are able to interact with this, it should at least give you some information on who interacted with it. And the last thing I want to show you here is that you can create a report. So you may want to just create this into like a PDF or HTML. In this case, it saves off as an HTML. And I'm going to say, and then go ahead and open it in Chrome. And here it's going to show you the summary report. It's going to say 18 of these weren't reviewed. One was set for need investigation. It's going to give you the diagram and walk through each one of these issues with a zoomed in of the threat model of what the issue was. So it's a little bit easier to read this way, especially if you've gone through and done some triage of the threats and provided some insight into whether it's a true issue or not. And it's a good way to kind of view the threat model in a different type of format. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back, and in this lesson we're going to talk about encryption. So there's two types of encryption. There's symmetric encryption and there's asymmetric encryption. So with symmetric encryption, this allows for encryption and decryption. The big thing to keep in mind here is that with symmetric encryption, the same key is used to do encryption as is to do decryption. So an example here is that you're storing sensitive data in a database. You would use one key to encrypt the database or encrypt the data that's going into the database, and then use that same key to decrypt it later on. So asymmetric encryption, the big distinction again is that there's two keys instead of one. It's used for encryption, decryption, and for repudiation, and we're going to talk about that a little bit as we get into digital signatures. So again, the big point here is that there's one key that's used to encrypt and one key that's used to decrypt. So this, you have to decide which key is going to do which. Doesn't matter, but as long as once you decide which key is going to do the encrypting, then the opposite key is the one that's going to do the decrypting. So that's the power of asymmetric encryption. So an example here is that verify that a message came from an individual user using their private key. And basically what that means is that if you have a key pair, which is what we talk about when we're talking about asymmetric encryption, we're talking about key pairs. If one key is used to sign a message, then it's been signed by that user's private key. Only the other key, the public key in this case, would be able to verify that that was actually sent by that user. And again, we're going to get more into that stuff as we talk about digital signatures later on. So, symmetric encryption. So when we talk about symmetric encryption, one of the older methods of this type of encryption is something like a Caesar cipher. And Caesar cipher is also considered an offset cipher. And for those that are familiar with the American movie The Christmas Story, there's a scene in that movie where the boy, the main character in the story, the boy receives a little key or a little decoder ring in the mail, and basically the narrator on the radio station that he listens to tells him which direction to move the key to unlock the message that's being super secret message that's been stored. So, but basically what this means is that it's an offset cipher, and the reason why they call it an offset cipher is because you put the dial. Maybe you're saying, like in this case, you see B and B and C and C and D, and you see that the letters are shifted off a little bit. So in this case, you may say that you're offset by 3, meaning that B is now E and C is now F, and so forth. So that's a very primitive way of scrambling a message, because if you didn't know that B was equal to E, then when you got the word, or if you got the message, it would look like total gibberish. So in a way it was encryption, but it was a very crude method of encryption. So there's a couple different types of symmetric encryption. Probably the most widely known and widely used symmetric encryption that exists is AES, and it was established in 1977, so it's old. However, it is like the gold standard for symmetric encryption. Now there are other ones out there, Blowfish and Triple DES or 3DES. And Triple DES is basically 3 times DES, which is an older algorithm. As you see there at the bottom, DES and RC4 are both considered insecure algorithms and shouldn't be used anymore. Triple DES is questionable, but AES, when it comes to asymmetric or when it comes to symmetric encryption, AES is the kind of the gold standard for symmetric encryption. So what about asymmetric? So again, asymmetric encryption is 2 different keys. So keys are generated together. There are not just because they're called because it's asymmetric encryption. You have 2 keys. They're typically called private and public. So the public key is freely available to anybody that wants to see it. There's no secret to it. Private keys, on the other hand, are ones that should never be handed out. That's why it's called private. And again, it doesn't matter which one you choose, just as long as when you decide that one is going to be private, that one stays private and never gets out. So when we talk about asymmetric encryption, the most dominant version of asymmetric encryption that's out there is RSA. It's the most widely used, and it's again kind of the gold standard, similar to what AES is for symmetric. So both the public and private keys can encrypt a message. The opposite key for the one used to encrypt a message is used to decrypt it. So like we've been talking about, there's a private and public pair. One can encrypt, one can decrypt, and vice versa. You can decrypt or you can encrypt with the one and decrypt with the other. It doesn't matter who the sender or receiver is. It's just that as long as both the opposite one is used to decrypt. So it's also important to recognize that not only does this give us confidentiality, but if you're paying close attention here, it gives us integrity and authenticity, because if you're signing something or if you're encrypting something with your private key, only you have that private key. So if somebody can decrypt that message with your public key, well, then they know that came from you. So it's a way of providing authenticity and non-repudiation. So what we talked about, obviously the big difference is that there's one key versus 2 keys, but there's other types of things to keep in mind in terms of use cases when to use symmetric and asymmetric. So the primary advantage of symmetric key encryption is that it's fast. So symmetric key algorithms are generally significantly faster than asymmetric key algorithms, and the keys are shorter in length. So since asymmetric requires fewer keys overall and symmetric cryptography is significantly faster, a hybrid approach is usually used. So what you may see is that asymmetric encryption is used to encrypt the symmetric key. So you could encrypt a message with a symmetric key because it's faster, the key lengths are much shorter, and then actually use asymmetric encryption to encrypt that key, send that along so that the receiver can decrypt it with their private key, and then they have the symmetric key and they can decrypt the message. So it's basically a hybrid approach that provides some speed and additional security. And with that, I hope you enjoyed this lesson, and I look forward to speaking to you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about different use cases for encryption. So the first one we're going to talk about is HTTPS, and you may be familiar with this because when you go to a website, it's typically prefaced with HTTPS. Most websites today are using HTTPS. Not that long ago, a lot of sites were not using HTTPS, but today that's changed drastically. So this is basically a way to encrypt the connection between your browser and the server. In this case, maybe you're going to Amazon or Facebook or Google. So your browser will be able to encrypt that traffic that's going to that server. So one of the primary components of this HTTPS is certificates. And we haven't talked about certificates yet, but we are going to. But certificates are a way for a third party to vouch for the owner of a private key. And basically that means that a server, like we talked about with private and public key pairs with asymmetric encryption, a server will get a private and public key pair, and they'll go out to a third party. In this case, the third party is Entrust data card. And so the server will go out to a third party, or the owner of the server will go out to a third party and get a certificate. And that certificate is signed, and therefore that vouches for the server's ownership of that private key. And so that certificate is then used to pass out publicly, and within that certificate is the public key, so it's the other half of that asymmetric key. So that certificate is then used by the browser when it goes to, let's say it's Amazon. The browser will have the Entrust data card certificate in its Rolodex of certificates, and therefore it knows that it will trust the server, and therefore will know that it can trust that the server owns the private key. So what happens here is that your client, or in this case your browser, will have the Entrust root certificate, so it's been signed by Entrust. The server has the private key that's associated with the public key that's embedded in that public certificate. And this is the way for the browser to trust the server connection, the one that it's connecting to. So, as I mentioned, the public key is within that certificate, and the private key, which is supposed to, stay private, is on the server. And as we talked about with asymmetric encryption, this allows for the client, or the browser in this case, to encrypt any of the traffic going to the server, and the server is the only one that can decrypt it because it's the only one that has the private key. So this is how many different browsers can connect to, let's say, Amazon, and all of them have access to that public key. All of them can encrypt the message or the traffic that it's sending to Amazon, but Amazon's the only one that has the private key, and therefore the only one able to decrypt the messages coming in from all the different clients. So in a nutshell, that's how HTTPS works. It's asymmetric encryption. It's backed by third-party certificate authorities. The public key is used that is embedded in that public certificate. The public key is in there. The clients use that to encrypt any of the traffic that gets sent to the server. The server, because it owns the private key, is allowed to, or is able to, decrypt the messages coming in. So let's talk about digital signing. And I know I mentioned digital signing a few times in the past, but let's talk through a use case here. So you may have a document, it could be a medical record, and like we talked about before, you're going to hash that document, so it's just going to become gibberish basically. It's not the same document. It's going to be a fingerprint or a checksum, or basically it's a fixed size of gibberish. So again, it doesn't look anything like the document, but it is representative of the document. So you have that gibberish, it's the fingerprint of the document. You use your private key in this case to sign that output from the hash. So you're going to use that private key to sign the fingerprint. And this produces a digital signature of the document. So because you used your private key to sign, you're the only one that has ownership of that private key, and therefore you're the only one that could have signed that document to create that digital signature. So you append this to the document, And this provides a digital signature to that document. So if you want to verify that document, first you would take the public key and you would decrypt. So down the bottom there, you would take that public key, decrypt it. So that means that using that public key to decrypt means that only the private key could have encrypted it. And therefore, when you use the public key, you know that you are therefore assured that it came from the owner of the private key. So what you would do is take the original document, hash it, and you'll get that output of that hash. And when you decrypt the digital signature with the public key, you're going to get the hash that was generated by the person or the system that signed the document in the first place. And if those two hashes match, then that means that the document has not been modified. And you're also able, again, because you used the public key, to verify that it came from the sender who sent it. So it provides you both integrity and repudiation in this case. So let's talk about a larger overall scope for encryption. And this is really, if you understand this walkthrough here, this use case, you're going to understand almost every single use case within encryption. So let's say we're going to start with a document, and we're going to use Alice and Bob in this case. So Alice is the one that created the document and is going to send it over to Bob. So Alice has this document, and Alice is going to hash that document and create that fingerprint that we talked about. And with her private key, she is going to sign that fingerprint and create a digital signature. So that provides authentication. Again, this is Alice signed it with her private key. Only Alice has possession of that private key, so therefore we know that it came from Alice. So she's going to take a symmetric key and actually encrypt the document, okay? And she's going to take Bob's public key to encrypt that symmetric key. And this provides security because you have a document that's been encrypted, and you now encrypted that symmetric key, so you're able to pass that then to Bob. So you take that. Because you sign it with Bob's public key, you can then send both the encrypted document and the encrypted symmetric key over to Bob. And Bob, with his private key, because you encrypted it with the public key, Bob is able to take his private key and decrypt that symmetric key. Once he has that symmetric key decrypted, he can then decrypt the document that you encrypted. And then with Alice's public key, Bob is able to verify that he takes Alice's public key to decrypt that digital signature. He hashes that document that he decrypted with a symmetric key, and if the two of those match, then he knows that the document has not been tampered with. And this provides integrity. And if Alice wants to get verification, she will ask that Bob will sign what he hashed with his private key, send that over to Alice. Alice uses Bob's public key to decrypt that digital signature and gets the fingerprint of the document that Bob actually hashed. And if that matches to her original, then we know that there's verification that Bob received it. So there's a lot to unpack there, but this includes a lot of different workflows within the encryption space. And so if you're able to understand this use case, you're going to be able to understand a lot of the different use cases within encryption. So one of the important things to remember about encryption is that the management of the keys is one of the more difficult parts of this, because obviously if you lose control of one of your keys, that's going to be a very bad day for you and your company. So the algorithm that encrypts the data are all the same. So there's nothing special about the algorithms. They're open. Everyone can read them, understand them. That's not the what makes encryption secure. What makes encryption secure is the keys. So as organizations use more encryption, they also end up with more keys and more varieties of keys. In some companies, you might have millions of keys. And this really gets down to the different use cases that you need in terms of using encryption. You want to make sure that you keep in mind that those keys you can have key sprawl, where you have a lot of different keys that encrypt a lot of different use cases. That's very difficult to manage and maintain. There are tools out there that will help you for instance, hardware security modules or key management solutions, they will help you manage your keys, provide secure access to them, actually do some rotation and automation as well. So there are solutions that exist out there, but there's a balance between making sure that you are doing encryption properly in the sense of making sure that you're using the right techniques, the right encryption levels. But the key management of encryption is one of the more difficult components to really get under control. So one of the important components is that the more use cases that you want to have unique keys for each one of those use cases. You don't want to reuse keys. And again, that's where those key management solutions will come into play. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about hashing. So what is a hash? A hash is a one-way function, which means that it's impossible to reverse. And when we're looking at good hashing algorithms, or ones that are considered secure, we're looking for a hashing algorithm that is what we call collision resistant. And basically that just means that two different values put into the same hash function should not have, there should be no possibility for those to hash to the same value. So in other words, if I have the word or the letters ABC and the letters DEF, and I put them through a hashing algorithm, the output should be completely different, therefore there's no collision. If you put in two different values and they hash to the same output, the output of that hash is identical, then that's a collision, and that's what we're trying to avoid with hashes. So what are some of the uses for hashing? We're going to talk about many of these throughout the rest of this course, but one is digital signatures. And so digital signatures are basically taking a form or a document and putting it through a hash function and then signing it with a private key. Passwords, you want to make sure that any passwords that you get from an end user, say for a login, that password is stored in the database in a hashed format. You can also use hashing techniques for verifying the integrity of files, and that's typically called something like a checksum or an integrity check or a fingerprint. And you may see that when you download files or go to a site that has a file for download, it may have some type of an integrity check like a checksum or a hash of that file, so that you can verify that it hasn't been tampered with. And again, we're going to talk about these things further. And then in blockchain, so for instance, with cryptocurrency, when you're mining cryptocurrency, you are solving for a specific hash. You're trying to look for a specific hash output, and that's how you mine Bitcoin. So hashing is used a lot in security. It's a good way of proving that something hasn't been tampered with, and it's also obviously for passwords. That's the way you want to store your passwords. So there's a lot of good uses for hashing within the security space. So when we talk about hashing, we also want to talk about the concept of salt. And salt is essentially a unique value that's added to an input value before it's hashed. So think of the example of a password. If my password is password, let's just say it's all lowercase PASSWORD. If I put that in as my password and that gets stored in the database, odds are, and we know this just based on when we see databases that have been breached, that a lot of people have the same passwords. So if my password is the word password, odds are there's other people that have that same password. So what you're going to see is if you breach that database and you have that list of passwords, you're going to find that there's going to be a lot of similar hashes in that database because everyone or many people are using that using password as their password. So what Assault does is actually create some uniqueness before that password gets hashed. So that way, say for sake of argument here, let's say the salt that's used is maybe the timestamp that the password was created. So assuming that there's 10 people that have the same password and they're all using password as their password, if all of them signed up for an account at different times, well, if the timestamp is used as a salt, then that means that everyone, because they signed up at different times, will have a unique password stored in the database because it's the salt has been added to the word password. In this case, it's a timestamp, so it could be the date and down to the second, so the hour, the minute, and second. That data is added to the password to make it unique. So even if somebody else had signed up for that account a second later or a minute later, their password is going to be their password when stored in the database is going to be completely different. So that's an example of how salt adds uniqueness to a password before it's hashed. So it's basically, and remember, it's pre-hash. So if I have the word password, the salt's going to be added to the word password, and then it's going to go through the hash function, and then that hash output is going to be stored into the database. So there's several different hashing functions out there. MD5 is probably one of the older ones. Not probably, it is one of the older ones that's out there. So it produces a 128-bit hash. MD5 is widely used, however, not very secure hashing algorithm. Now, you may still see MD5 being used for things like checksums or integrity checks on files, but it's not really appropriate to use MD5 for security type of situations like digital signatures. SHA-1 produces a 168-bit hash, which is longer, obviously, than the MD5, which produces 128. So it's been considered insecure. A couple years ago, it started becoming. There's been more academic style attacks, and when we say academic style attacks, meaning that in theory there's collisions that could be possible with SHA-1, enough to get people worried about not using it anymore. So therefore, SHA-1 is being recommended not to be used anymore, and so it's been deemed to be as insecure as MD5. So you can think of SHA-1, MD5 in kind of that same category of the insecure hash functions. SHA-2, which is newer, it's actually a family of hash values. So there's the 224-bit, 256-bit, 384-bit, and 512-bit. So when you talk about SHA-2, we're really talking about the family of SHA-2 that's available. And this is the more secure, more appropriate hash function to be used today. SHA-3 is the latest one that's out, and it's similar to SHA-2. It's a family of bit sizes. So you have the same 224, 256, 384, and 512, and it is available today as well. But right now, SHA-2 is considered robust enough and able to withstand any types of theoretical attacks that are out there. SHA-3 obviously is, because it's newer, there's a lot of functionality in it that the way that hashing is done that makes it more secure, but today SHA-2 is sufficient. So we're going to talk a little bit about some of the different types of attacks that can be perpetrated against hashes. So mentioned early on that hashes from a security point of view are considered secure when they are collision resistant. So a collision attack, like I mentioned, is when two values put into the same hash function will produce the same hash output. So again, if I put in ABC into a hash function and then put DEF into a hash function and they come out with the same hash output, that's a collision, that's a problem. That means that the hash function is not secure. So there's also another type of attack called a birthday attack, where this is looking to find collisions. Again, you can't reverse a hash, so the way that you try to uncover a hash, we'll say, is to find that collision. So birthday attack takes advantage of what we would call when you're not trying to target a specific type of hash output, but instead you're just trying to find two matches. So one of the good ways to think about this is that in a classroom setting, if you have 30 students in the classroom, and if the teacher says, I'm looking for anybody that has the birthday of June 5th. And there may be nobody in that class that's going to have that. Maybe there's one. Maybe there's a couple. It's all probability here. But the likelihood that if you pick, in this example here, it says October 10th. So if we say October 10th is the date that we're trying to find, does anybody have that birthday in this classroom? The likelihood of that happening is just shy of 8%. There's an 8% chance that one person would have that. However, if you just took the classroom, the 30 students in the classroom, and said, just went through the months of the year to try to find out who might have the same birthday in the class, that's an example of the birthday attack. So maybe you start with January and you have all the students stand up and say, okay, whoever has a birthday in January, who doesn't have a birthday in January, sit down, or you can go through the process here. But basically what happens is you want to get two students. You're not targeting a specific birthday, but you're trying to find two students that have the same birthday in that classroom. And actually, that probability is up to 70%, which means that you're more likely to find two students in a classroom of 30 that have the same birthday, instead of trying to locate a specific date like October 10th. So why is that important from a finding a collision perspective or from breaking hash? So what happens with digital signatures, and basically you can think of an attacker who is trying to get somebody to sign a forged contract, or a malicious contract, or get them to sign a contract that's not beneficial to them. So what happens is the attacker would produce a document that they're trying to get this other person to sign. And they're going to make small modifications to the document. So it's a contract, and maybe it's favorable to the person that is supposed to sign it. But the attacker can go in there and make some minor cosmetic changes that maybe the signer may not notice. So adding a comma, or adding an extra space, or adding 2 spaces after a paragraph, or something like that. And basically, the attacker is going to go through and create a bunch of different iterations of that document. And what that's going to do is create a large pot of these contracts with very minor changes in each one of them. And the contract, when you look at it, looks exactly the same. There's no real, other than these cosmetic changes, there's no real issues. So the attacker is going to go through, create all those different contracts, and then create hashes for each one of them. And then the attacker is going to create maybe a less favorable contract for the victim to sign. And maybe that contract says things, that again is not favorable to the victim. And the attacker is going to do the same thing. They're going to create, a contract that has language in it that's not favorable to the signee, and then the attackers are going to go through and make some minor modifications, add a comma here, add some white space, carriage returns, things like that, which again, if somebody looked at it, they're not going to notice the difference. And once that attacker creates all those different variations of that malicious contract, they're going to go through and create hash values for each one of those. And then, now that you have a pot of good contracts that are favorable to the signee, and you've hashed all of them, and maybe you have 100 of those, and then you've went and created this malicious contract, and you created all variations of those, and you hashed all of them, and again, maybe you have 100 of them. The likelihood, again, like we talked about with the birthday attack, the likelihood of 2 of those being able to match up is very high, which means that you can get somebody to sign digitally sign that contract, and because the value is the same, or because you found a collision there, it would appear as though they signed the malicious contract, and therefore you have the ability to get somebody to sign a contract, digitally sign a contract that's unfavorable to them. And it's difficult for them to prove that it's not that they didn't sign it, because they did sign it. So that's kind of the importance of the birthday attack and collisions, and that'll become a little bit more clear when we talk about digital signatures down the road. But basically a digital signature is hashing a document and then signing it with a private key, as I mentioned earlier. So additionally, as far as the collision and the birthday attacks, there's a couple different types of collision attacks that you can do. There's the brute force, which is basically where you, if you're trying to find a password, and again, let's say it's the word password, you would start hashing the brute force way is by hashing all the values possible. So you might start with A, hash that. Doesn't collide with the hash value of password that you have. So then you go to B, and so forth. And basically you just walk through the alphabet and you start adding characters, and basically you're trying to find that collision. You're trying to find an output from your brute force attempts that match the password, because again, if all you have is the hash value of the word password and you're trying to find out what that hash value means in the plain text, then that's the one way to do it, is by brute forcing and just keep on trying multiple different things until you find that collision. A more sensible way of doing that is with a dictionary attack, which basically uses dictionary words, and they're usually pre-computed, meaning that you'll have a dictionary of hashes, and you can then locate specifically a dictionary word that's been hashed, and for something like password, that's going to show up in a dictionary. It's a much quicker lookup. And then the rainbow tables is basically where the pre-computed table that has both the hash value and the pre-hash value. So you'll see the word password with the hash value in like MD5, and the hash value in SHA-1, and the hash value in SHA, all the different family values of SHA-2. So and basically what that allows you to do is, again, a very quick lookup of the hash value that you may have. And again, if you're trying to understand if you have the password, all you have is the hash value, you would be able to take that hash value, look into that rainbow table, and see that it equals. You would find a match, and then you just look to see what the plain text value of that is in your rainbow table. So with that, I hope you enjoyed this talk on hashing, and look forward to seeing you in the next lesson. Thank you. Okay, everyone. So wanted to show a little bit of a demo here. And what you see here is I'm at onlinemd5.com, and basically this will allow you to generate some hashes out of some string input. So let's do hello world, and you'll see here that the hash value for an MD5 is here. You can change that to a SHA-1, you can change that to a SHA-256, and if I just add one character just to kind of show you how much this changes. If I put, just one character in there, you'll see that it changed drastically. Take it back and it goes back to where it was. Now, if you're kind of following along here, like I mentioned before, the same input's going to have the same output as far as the hash. So make it a little bit easier. Let's go back to the MD5 here, and you can kind of see the pattern here. You don't have to memorize this, obviously, but if I change this, you see a different output. Again, if I go back, you'll see that it's the same exact output. So every time you put your input in, you're going to get the same exact output. Now you can also drag and drop files up here, and on this website you can drag and drop files up here and get the hash of it. And the reason you may want to do that is that, for instance, if you want to verify the hash of a file that you're downloading. So in this case here, I have Linux Mint 19.3, Cinnamon 32-bit, and I downloaded it, and the hash that they present to verify the integrity of the file is this hash right here. Okay, so this is for the Linux Mint 19.3 Cinnamon 32-bit ISO. And what I've done is I've taken the let's see here, PowerShell. So what I've done here is you can drag and drop into that MD5 website that I showed, but it's going to take a long time to do that. So actually what I'm doing here is I'm going to use certutil within PowerShell and actually point it to that Linux ISO and create the hash file, and I'm going to compare it to the hash that they presented here. So it's certutil dash hash file. You send in the hash file that you want to run a hash on, and you're going to specify that I want to do SHA-256. So this may take a few minutes, or not a few minutes, but actually it ran pretty quickly here, obviously. Now you can compare, by eye here. So you can see here F1E, 40469, B2, it's all equal and out for the most part. You can do this again by eye. You can do a find command against the text file for this value. Do basically a search in the text for the value as well to make sure that it comes up and matches. But so basically, this means that the file that I downloaded, this ISO file, matches the hash that Linux that the Mint creators created for that ISO file. So Linux Mint, they created the ISO file, and they ran this similar utility here to generate a hash. They post that hash on their website. So they say, hey, if you download this file, just make sure that the hashes match. If they do, then that means that the file hasn't been tampered with. Okay. And with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about public key infrastructure, or PKI, and certificates. So the term digital certificates, it means that there's proof of ownership of a private key. So it basically is it's a digital certificate that states that a server has ownership of a private key. And we talked about asymmetric encryption and private and public key pairs. And so when those keys get created, the owner of that server or the owner of that private key will go out to sometimes a third party or sometimes an internal certificate authority. And that certificate authority is going to vouch for the ownership of that private key. And that turns into what we call a public certificate or a digital certificate. So it's a digital representation of an identity, and it allows one to confirm with who you are transferring data to and from. So basically, having that certificate authority sign a certificate, and which is proof of ownership, means that somebody has vouched that you are indeed talking to the server that you intended to be talking to. So a certificate binds an entity's unique distinguished name, or DN, and other additional attributes that identify an entity with a public key associated with its corresponding private key. And a lot of times what you'll see in that certificate data is going to be things like the organization name, perhaps the location, and a lot of other bits, and we're going to show some of that here in a minute. So a certificate authority, as I mentioned, is a third-party entity that issues these digital certificates. And there's a bit of a process for that certificate authority to issue a certificate. And usually that's where the owner of that private key has to show that they actually have ownership of that particular server or domain. And the certificate authority may ask them to update a DNS record or do some type of email verification or drop a file in a server location that they own. And that's a way for the certificate authority to say, yeah, if you were able to do that, that means you have ownership of that server. There is more extensive validation that can be done too, and they actually call it extended validation. And that's where the certificate authority may actually call the company and talk to somebody and maybe even do a little bit of an audit to make sure that organization does indeed own that server. So certificate authorities, these are the foundation of public key infrastructure, or PKI. And what the certificates allow is for this offloading of trust to a third party. Similar to and I think I gave this example before, but similar to a state in like the United States, a state will issue a driver's license to an individual. That anybody that you show that license to knows that the state has vouched for you and says, yes, this person, we've done some type of verification on this person, and this is who they say they are, and we've issued them this certificate or license in this case. So it's a very similar setting where the trust of that certificate or the trust of that ownership or the trust of that identity has been offloaded to a third party. So in PKI or public key infrastructure, there are different levels of certificate authorities. And there's what they call a chain of trust, where there's a root certificate or root certificate authority. And then there's some intermediate ones or middle ones that do actual issuing, and they do call them issuing certificate authorities as well. So you have this root certificate or this root certificate authority, and below that there's going to be these other ones that actually do the regular signing of certificates. And what I mean by that is that if you're setting up a server and you created your key pair and you want to go out to Entrust or GoDaddy or some other certificate authority, Amazon, to get a certificate created, the one that will sign the certificate isn't actually the root certificate. It's going to be an intermediate or an issuing certificate authority, which is usually at least one step below the root certificate authority. And the reason for that is that the root certificate, similar to the private and public key pair that you're generating on your server, the root certificate is a private key that's owned by that certificate authority. And that certificate authority, when you send a certificate request, and we're going to show that here in a little bit, when you send a certificate request to them, they're going to sign that certificate request with their private key. And we know that due to the nature of asymmetric encryption, that when they sign that with that private key, that means you can verify that with their public key. So the root certificate authority wants to protect that private key as much as possible. So what they do is they create these issuing certificate authorities or these lower certificate authorities that do those daily or many per day certificate signing requests. The issuing ones will do that, not the root. And the root instead is only used to create more issuing certificate authorities. So it's a way to protect that root certificate, that root private key and that root certificate authority, and instead use those issuing or those middle certificate authorities to do more of the daily grunt work of signing certificates. So as I mentioned, when you're creating that certificate signing request, that CSR, you create your private and public key pair, and on the server that you're, let's say you're setting up a web server for HTTPS, you create that private and public key pair, and you're going to create a certificate signing request, and this is what you send to the certificate authority. And so you create your private and public key pair, and then you create the CSR that has information specific about the host. So distinguished name, the DN, the location, the business name, etc. There's a lot of different information that goes into that. And you're going to sign that with your private key. And as we know, that's going to create a digital signature. And so you send the public key, the CSR, and that signature over to Entrust. Let's say Entrust is the certificate authority that we're using in this use case. But it could be GoDaddy, it could be Amazon, it could be Let's Encrypt. There's a lot of different certificate authorities that are out there. And so this information is validated by Entrust, by the certificate authority. And what they do is they create a certificate and they sign it with their private key. So Entrust or GoDaddy or whoever the certificate authority is takes your data, signs it with their private key, and that's the digital certificate that you then use to pass out to any of the connections that are trying, like any of the clients that are trying to access your server, let's say over HTTPS. You would then serve up that public certificate to say, hey, this is my server, I own the private key, and here's the third party that vouched for me and said that yes, I do indeed own that private key. So you can actually view certificates through your browser. So if you want to browse to a website, and depending on what browser you're using, in this case I use Chrome to look at the certificate, But if you go to the address bar where it says HTTPS and it has the website, there's usually a padlock right next to it. And if you click on that padlock, there should be an option to view certificate. And what you're going to see, and again, it depends on which browser you're using, but in this case, I use Chrome. And if you want to look at the certificate, you click on that padlock, say View Certificate, and you're going to see here the certificate was issued to Amazon. It was issued by DigiCert. So Amazon created their certificate signing request, and they went out to DigiCert and said, "Hey, here's my certificate signing request. Here's my public key, my digital signature. Please create a certificate for me that I can then issue to. That's my public certificate that I'm going to then make public, and anyone can see that DigiCert vouched for my ownership of the private key." You also see here that there's a valid time frame. So in this case, it's about a year. And some certificates may have longer lifespans. Some of them may have shorter lifespans, but in this case, it's a year long. So you can also look at the details where it's going to show a lot of different information about the certificate. In this case, you see that the signature algorithm is SHA-256, which is good. And you see the valid date, you see the subject, which is Amazon.com, and there's going to be some other domains that are listed in there as well. And then the other point, as we were talking about with PKI, there's the root certificate, which is the G2 global root at the top. And then there's a DigiCert Global CA G2. G2, I think, typically means generation 2. And then you see the certificate that was signed. So in this case, the root certificate is the DigiCert Global Root G2 that's at the top of that hierarchy. And then there's an issuing certificate or a signing certificate that's below that. That's the Global CA G2. And then the Amazon certificate is the last one in the chain. So you may have heard the term man in the middle. And what that really means is that, as it states, there's somebody in between you and your end connection or the website that you're trying to go to that's able to basically you're establishing a connection with the man in the middle. The man in the middle is establishing a connection to the server that you're trying to get to. And in that case, the person in the middle or the man in the middle is able to decrypt your traffic and then re-encrypt it when it sends it to the server. So this allows them to read any of the traffic that's going between them. And there are some real world examples of this. And in case you get onto, let's say, an organization's network, if maybe it's a library or your school or your company that you work for, there's a lot of times where they may actually have endpoints that have a certificate, and basically you're trusting the certificate of that endpoint, but that endpoint is actually between you and the server that you're trying to go to. So let's say, for instance, if you go to school at a university, the university may have a certificate on a outbound proxy that will basically, you have a trust relationship between your browser and the proxy, and the proxy is able to, because you have a connection because you have a connection with that proxy, the proxy is able to decrypt that traffic before it sends it off. Let's say you're trying to go to YouTube or you're trying to go to Amazon or something like that. The proxy will basically, you have a relationship with that proxy. The proxy will be able to terminate your connection and then reestablish the connection going out to Amazon. So it's acting as a man in the middle in that case. So there are some legitimate reasons for that. Maybe there's especially on like a university or in a library or in an organization, they want to make sure that the people that are signing onto that network aren't going to servers, websites that could be could pose potential harm to the company or to the organization. So it is in their best interest to ensure that that's being done. So there are use cases where maybe that makes sense to have a man in the middle. And with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about password handling. So some of the best practices around passwords is you want to be able to allow for long passphrases. You want to mask user input field. Now there's some changes in that over the past couple of years where some sites or applications are now allowing a little checkbox or a button that will allow you to see your password that you just entered And the reason for that is that if you have a very long and complex password that you're trying to enter, you want to make sure that it's correct and you're not constantly messing it up when you're putting it in. You always want to make sure you transmit it over a secure encrypted channel. So for like web applications, you want to make sure you're transmitting it over HTTPS. You also want to make sure you're storing it securely. We're going to get into this later around hashing. You don't necessarily want to encrypt a password, and we'll talk about this a little bit, but if you're encrypting a password, that means you have the ability to decrypt it. There are some use cases where you may need to do that, but the vast majority of use cases for passwords, you want to make sure it's hashed. So in other words, you don't have the insight into what that password is, you're only storing it. And again, we're going to talk about this when we get into hashing and encryption. You want to make sure you're submitting it as a post in the body of HTML. So that way, it's not as a parameter in something like a get, because that has the possibility for it to be captured somewhere and viewed. Make sure you never log a password in a log file. And again, these aren't the only things that you should consider when talking about passwords, but this is a pretty good list. So, as I mentioned, you never want to store a password. You definitely do not want to store it in plain text. You want to make sure that it's always hashed. And when we talk about hashing later on, this will become a little bit more clear. But hashing is basically a way of scrambling up some text or input to make it unreadable, and you have no ability. They call it one way because you have no ability to change it back to its original text. So you want to use cryptographically strong hash algorithms, use sufficient salt, and salt is basically a randomized or a way to randomize the hash by adding a unique value to the. So if you have something like your password, maybe it's password, hopefully it's not, but maybe your password is password. A salt would add some kind of a unique value, like maybe it's a number or some kind of long random set of characters to add to password. And then that's put into a hashing algorithm to make a more secure hash or a more secure output from that hash function. So you want to make sure you physically segregate stored hashes from the rest of the application data. So if something should happen where the application is compromised and data is stolen, hopefully the hash passwords are stored away from that data. That's just a good architecture design there. So when we look at this chart down here, just as it comes down to picking cryptographically secure hashes, bcrypt, scrypt are generally the ones that are considered, in most cases, the most or more secure hashing algorithms that you can use. The older ones like MD5, DES are no longer really considered secure. And we don't need to dive into this chart here, but you can see kind of the how things scale once you get to like scrypt at the bottom there, and an 80 character text in relation to how much computing power is needed in order to get down in order to crack that password. And we're going to talk about hashing and cracking and all that later on, but the point to remember here is that scrypt, again, these are just recommendations here. Things change very frequently, and there are other hashing algorithms that are constantly coming out that may be better. But this chart is just to kind of give you a sense for, the hashing algorithms that are considered secure, the length of text that is used in a hashing algorithm, and really the computing power that's required as you go along to be able to create a collision, what we would call a collision, in order to get to crack a password. So as we talk a little bit about passwords, one important thing to think about here is entropy. So entropy, just basically think of entropy as being randomness. Entropy, as entropy increases, you have more disorder, more randomness within a character set. So if you see a character string that's, let's say, just to keep it simple, it's 10 characters long, and in that character string, their 0 shows up 4 times in a row, well, then that's not really good entropy. In a 10 character, you would hopefully not see anything repeat. That's more entropy. So password entropy is based on the character set used as well as the password length. So again, the character set, if you have a large character set including symbols, letters, numbers, spaces, things like that, that's gonna make your character set much larger, and that allows you to have a much larger password length. Which in turn will allow you to have much more entropy. Password entropy predicts how difficult a given password would be able to crack through guessing. So in other words, if we're trying to brute force, as I mentioned before, if you have a 10 character space and the number 0 shows up 4 times in a row, that's not really a high entropy, and that really opens up to brute forcing, or makes it more easy to brute force a password because your guessing becomes a lot more easier. Encryption creates randomness, which cannot be compressed well. So just a note here about compression and encryption. The whole point of encryption is to create randomness in that character set, and that will not compress well. So if you are looking at compression and encryption, you always want to compress first and then encrypt, because compression, the way compression works is that it looks for, again, going back to that example of a 10 character set and 4 zeros showing up in a row, the compression algorithm is going to collapse those 4 zeros down and just mark it as one entry of 4 zeros, as opposed to writing out all 4 zeros. So when you encrypt and then try to compress, you're not going to get the value out of that compression as if you were to do it the other way around. So password strength, again, as I mentioned, it's all about length and randomness. So here's kind of a cartoon here that talks about different ways of creating passwords. So, we've gotten to the point in the security industry where we would create these very random, strange groups of characters and give that password to a user and say, here's your password. Now, we're kind of beyond those days. That was a while ago. Where if you started a new job, the IT person would come down and give you a sticky note that had your password on it, and it was a crazy password that you were never going to remember. So what everybody did, obviously, was put that post-it note maybe under the keyboard, maybe posted it to their monitor so that it was easily viewable to them when they had to enter it. And this was good security in the sense that it was very difficult for somebody to be able to guess what that password is, because it was completely random, completely unrecognizable. However, because of the fact that you couldn't remember it, meant that you had to put it somewhere so that it was easily accessible. And something like that obviously diminishes the security there. So what they recommend here is to create passphrases, and this is kind of new recommendations here. So create passphrases, something that's long and has a lot of random words in it. It's easy for you to remember, but it's very long, which means that brute forcing it or trying to do automated attacks are not going to be as effective. So in this case, it says correct horse battery staple. That's the password. It's 4 random words that maybe you, again, it might be easy for you to remember that. Down the road, it's going to be easy for you to remember that password, but it's much more difficult for someone to try to brute force that. So best practices around password complexity. This changes. In fact, it was recently updated by NIST to make some adjustments there as well. But in general, you want to make sure that it's at least 8 characters. Longer is better. You want to have at least 1 character from one of these 3 groups. So uppercase, lowercase, numbers, special characters. And again, we're all pretty familiar with these recommendations as we create passwords. Shouldn't be a common dictionary word, so you don't want to do something like hello, 1, 2, 3, or something like that. You want to try to make it something that you can remember. Maybe you want to replace some characters with numbers and so forth. should not be a permutation of the username. So you don't want to use your username as your password. So again, those are some basic best practices around passwords. And again, this changes as recommendations come along. So newer recommendations, as kind of mentioned there, these things do change. So some of the newer recommendations around passwords are using multi-word phrases, passphrases, like the horse battery staple, that we talked about. So putting several words together, again, increases the length of the password. Avoid common patterns like reusing like A and numbers and things like that. You want to avoid those kind of patterns because honestly, the way brute forcing works, it's going to look for those kind of patterns. Add a secondary factor, something you have, something you are, something you know. So we didn't really talk about this before, but there's three types of factors when we're talking about multi-factor authentication. Something you have is like a one-time passcode generator. So it could be like a hardware token, could be on your phone, but it's basically something that's constantly generating a token that you use to punch in. For those that have this enabled for either through their work or maybe even your bank supports this. It's basically a code generator that is a second factor. So you put in your password and then you put in the code afterwards. Something you are is biometric. So your eye scan, your fingerprint, your palm print, facial recognition, that's all biometric. So that's something you are. It's something that doesn't change. It's you. It's a way of authenticating you. And again, these are different factors. That one of those factors are your password, and that's something you know. So your password is something you know. Something you are is biometric. Something you have is some kind of a token generator. You also, for the newer recommendations around passwords, implement things like CAPTCHAs, which blocks unlimited guessing. And then, of course, temporary lockouts, which a lot of us are familiar with too. If you've forgotten your password a couple times in a row, your account usually gets locked out. And with that, I appreciate your time today, and I look forward to speaking to you again. Thank you. Hey everyone, welcome back. And in this lesson, we're going to explore Kaspersky's password checker, and you can find it here at password.kaspersky.com. And so we're just going to go ahead and play through some examples here. And the point being that Kaspersky is going to show you how long it would take to crack your password, and whether it's been shown, whether it's been found in a database somewhere. So let's go ahead and use a very simple, easy one here. 1, 2, 3, 4, 5, 6. And a lot of problems with this one. Number one, it's too short. This also appeared in a lot of databases that were leaked online. And it says here it could be brute force with an average home computer in 1 second. So that's probably being pretty generous. So why don't we try the one that we did in our previous lesson here. I believe it was a correct horse battery staple. Pretty long, not too bad. Okay, so the problem here is that it was found 123 times in databases of leaked passwords. So chances are somebody saw that comic or knows that trick there to use this. So that's not good. So why don't we put in something completely random and arbitrary with lots of letters, characters, symbols, and all that other stuff, and see what happens. So I'm just going to go randomly across the keyboard here. Throw in some symbols, some numbers, and so forth. Okay. There you go. Your password is hack resistant. Your password does not appear in any databases of leaked passwords. It would take 10,000 plus centuries for an average home computer to crack that. So that kind of gives you a good indication that number one, this password's pretty strong. And if I reduce this a little bit, I'm sure, like for instance, let's just go with the original characters. Okay, so it says it's good because it's random, it's not a word, and there's no patterns. Doesn't appear, but you could see that this could be brute force in a shorter period of time than the one with the character. So if I had a character to this maybe, or a special character to it, so now you see it's 4 years. So it went up quite significantly just by adding a exclamation point at the end there. And they give you a little bit of neat facts too, just to make it a little bit more exciting. So anyway, Just a little example here of playing around with some passwords. The one thing I would say is if you do go here and use this, and they even recommend this, do not enter in your real password, or any of your passwords. It's recommended not to do that for obvious reasons, because it could get logged somewhere. It could be getting sent. You just don't want to do that. So I'm sure Kaspersky is probably keeping metrics on the stuff that's being entered in here. So just word of wisdom there. So thank you for joining me in this lesson, and I look forward to talking to you again. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about HIPAA and high tech. So HIPAA was signed in 1996 here in the United States, and it stands for the Health Insurance Portability and Accountability Act. And a couple purposes of HIPAA was to modernize the flow of healthcare information, provide protection of PII, address limitations on healthcare insurance coverage. So there's a couple titles that are part of HIPAA. The one that we're going to focus in on here is Title II, which is preventing healthcare fraud and abuse. And within Title II, there's a couple different rules. The two rules that we're most concerned about is the privacy rule and the security rule. So the privacy rule regulates the use and disclosure of protected health information, or PHI, held by covered entities, generally healthcare clearinghouses, employer-sponsored health plans, health insurers, and medical service providers that engage in certain transactions. So that's the privacy rule. The security rule complements the privacy rule. While the privacy rule pertains to all protected health information, including paper and electronic, the security rule deals specifically with electronic protected health information. So we're talking about electronic PHI in this case. So what is PHI? Well, PHI is it basically builds on identifiable information. So identifiable information, no big surprise here: names, phone numbers, email addresses, locations, dates, social security number, account numbers, things like that. Those are all identifiable to you. But from a healthcare perspective, there's other items that we build upon those, things like medical record numbers, maybe some imaging like x-rays or CAT scans, doctor's notes, medical records, things like that are all part of that identifiable information that's specific to healthcare. So when we talk about privacy in HIPAA, with respect to health information, privacy is defined as the right of an individual to keep his or her individual health information from being disclosed. No big surprise here. If you've been paying attention, this falls underneath the category of confidentiality, right? We're trying to protect the privacy of data through maintaining its confidentiality. So privacy encompasses controlling who is authorized to access patient information. Again, no big surprise there, it's confidentiality. When we talk about security, especially in the context of HIPAA, we're talking about the mechanisms in place to protect the privacy of health information. This includes the ability to control access to patient information, as well as to safeguard patient information from unauthorized disclosure, alteration, loss, or destruction. And again, tying this back to confidentiality, integrity, and availability, security is really those mechanisms, the technology, the people, process that we put in place to make sure that we're maintaining the CIA, the confidentiality, integrity, and availability of data, especially specifically to healthcare information in this context. So security is typically accomplished through operational and technical controls within a covered entity. Since so much PHI is now stored and or transmitted by computer systems, the HIPAA security rule was created to specifically address electronic PHI. So there are violations that are associated and fines and penalties that are associated with HIPAA. So if you look at Tier 1 here, it's $100,000 to $50,000 per violation, maximum of $1.5 million US dollars per year. And this is basically, unaware of the HIPAA violation. It's basically you didn't know it was an accident. There wasn't malicious intent. All the way up to Tier 4, which is malicious intent, where the fines can get up to $50,000 per violation. And this is really where there's been negligence in terms of protecting the information. So there, you can see here that the whole purpose of providing these penalties is so that when information has been stolen, that if it's been through negligence or malicious intent, that there are penalties that are actually associated with that. So along with HIPAA, there was another act that came in place in 2009 called the High-Tech Act. And High-Tech stands for Health Information Technology for Economic and Clinical Health Act. So this was, again, as I mentioned, created in 2009 to promote and expand the adoption of electronic health records by healthcare professionals. So it was really, the purpose there was to accelerate that electronic health record advancement. So up until this point, if you had gone to a medical facility or doctor's office, a lot of your records were papers on the shelf behind the administrator's desk. And there was a lot of big push at that time to move all those paper records into electronic system. High-Tech kind of helped accelerate that. So the High-Tech Act contains 4 subtitles, A through D. Subtitle A concerns the promotion of health information technology and is split into 2 parts. Part 1 is concerned with improving healthcare quality, safety, and efficiency. Part 2 is concerned with application and use of health information technology standards and reports. Subtitle D covers privacy and security of electronic health information and is also split into 2 parts. So Part 1 is concerned with improving privacy and security of health IT and PHI. And then Part 2 covers the relationship between High-Tech Act and other laws. So the High-Tech Act built on HIPAA and ensured entities were compliant with HIPAA rules, and that notifications were sent to affected individuals when health information was compromised. There were tougher penalties for HIPAA compliance failures were introduced to incentivize entities to comply with the HIPAA privacy and security rules. It increased electronic health record adoption from 3.2 in 2008 to 14.2% in 2015. So that you could see that there was the purpose of High-Tech was to get faster adoption of electronic health records. It did that pretty substantially. So by 2017, 86% of office-based physicians had adopted an electronic health record, and 96 of non-federal acute care hospitals had implemented certified healthcare IT. So the Act did not make compliance with HIPAA mandatory, as that was already required, but it did make sure that the entities found not to be in compliance could be issued with a substantial fine. So in 2013, High-Tech and HIPAA were brought together under the HIPAA Omnibus Final Rule. Now there were a couple things, again, as I mentioned, High-Tech really added teeth to the HIPAA Act, and there were a couple things that were somewhat new with the High-Tech Act, and the one was that the breach notification, where now within 60 days of the discovery of a breach of unsecure protected information, you had to be notified that your data was, or that your information was breached. Both acts address the security of electronic protected health information, or PHI. However, prior to High-Tech, patients were unable to find out who had their electronic PHI and who it had been disclosed to. So this allowed, the High-Tech Act allowed patients to be able to request access to who had information to their, or who had access to their health information. So with that, I know that was a lot around HIPAA and High-Tech, and I appreciate you sticking with this lesson, and I look forward to speaking to you in the next one. Thank you. Hey everyone, welcome back, and in this lesson we're going to talk about PCI. So PCI stands for Payment Card Industry. Most of the times you'll see PCI used alongside of DSS, which is Data Security Standard. So it's an information security standard. 2 of these put together. It's an information security standard that's mandated by the credit card companies. Any company that processes credit cards needs to adhere to PCI DSS. The standard was created to increase controls around cardholder data to reduce credit card fraud. So there's a couple different roles within PCI. There's the QSA, which is the Qualified Security Assessor. So this assessor is the one that will certify whether a company is in compliance with PCI. Report on compliance is a form that has to be filled out by all level 1 merchants undergoing a PCI DSS audit. So the ROC, or the report on compliance, is used to verify that the company is within compliance of PCI. The self-assessment questionnaire is used for any company that processes a small amount of data. So it's as the name states, it's self-assessment, meaning that there's not an auditor involved. The company in question will take the self-assessment and do that on an annual basis. And it really comes down to how much data they process. If they're a large processor of credit card data, then they would have to have a formal audit. If they don't process that much credit card data, then they can use this self-assessment questionnaire on an annual basis to basically attest to their PCI compliance. So validation of compliance is performed annually, either by that QAS or QSA, the qualified security assessor, or using that self-assessment questionnaire. And again, it really depends on the amount of volume of credit card data that's being processed, or the volume of transactions. Compliance with PCI DSS is not required by the federal government. So again, in the United States. But the laws of some U.S. states either refer to PCI DSS directly or make equivalent provisions. So basically, even though the law does not state that you need to adhere to PCI DSS, many of the requirements and regulations that each state requires do strongly align to PCI. So the standard specifies 12 requirements for compliance. We're going to talk about them here in a minute, organized into 6 logically related groups or control objectives. So the 6 control objectives here are build and maintain a secure network and systems. And basically that comes down to making sure that you have the right network controls in place. So it could be a firewall, IPS, IDS. Protect cardholder data. No surprise there. That's going to mean encryption, making sure that you have the right controls around the data that you're storing, specifically around encryption. Maintain a vulnerability management program. So making sure that you have the ability to not only identify vulnerabilities as they come in, but have the ability to address them so that they get resolved. Number 4, implement strong access control measures. So know who has access to what data. Make sure that you are checking access to that information or that data, and ensuring that you have the ability to know who has had access to especially sensitive information. Regularly monitor and test your networks, so penetration test, and making sure that you have monitoring and logging in place to ensure that you understand what is going on in your network. And then last one is maintain an information security policy. So this is from a high level, ensuring that you have the policies in place in order to maintain a secure environment. And with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about DevOps. So what is DevOps? And I'm sure, especially if you work in the development field, you've heard this term before. And simply put, DevOps is the breakdown of the barrier between development and operations. And what's been typical in the past is development team writes code, they write production ready code, they hand that code off to a operations team, which is responsible for deploying that code and making sure that it runs in the operational capacity. So DevOps is really just a breakdown of that barrier, where you see a lot of different flavors of this, where the development team is responsible for actually deploying the code to operations, or the operations team is integrated more tightly with the development team. There's a lot of different ways of doing it, but basically from a high level, think of DevOps as that breakdown between the barrier where development no longer just throws code over the wall and expects another team to deploy and maintain it. So a couple terms. Continuous integration is a development practice that requires developers to integrate code into a shared repository several times a day. Each check-in is then verified by an automated build, allowing teams to detect problems earlier. So again, if you work in the development space, you're probably very familiar with this. When you write code, you check it into a branch. The branch is then automatically triggers a build in maybe Jenkins or some other build tech that you're using. And that's basically continuous integration where you're writing code, you're checking it in, it's getting built, and you get feedback immediately whether the build failed, whether there's issues with some system tests or integration tests that are part of that build functionality. So that's what continuous integration is. And this is basically from a high level. And again, a lot of companies do it differently, a lot of teams do it differently. But what you see here is a developer writes code, they check in those changes, it goes to a source control server. The build machine will then fetch those changes. There's triggers usually set that detect that source code's been checked in. The build machine will then fetch those changes, build the product, run some tests, and then if it's a fail or succeed, if it's failure, it's going to send a notice. If it succeeds, well, then you have a successful build. And that's really the continuous integration. Again, if there's either way, if it's a success or failure, there's going to be notifications sent out. However, if there's a failure failure in the build, obviously that's going to create a little bit of haste with the development team to go fix that quickly. So with continuous integration, because you're integrating so frequently, there's significantly less backtracking to discover where things went wrong. So in other words, as you're checking in code and that build process kicks off and you get immediate feedback or near immediate feedback on whether the build succeeded or not. And if it failed, you're able to track that back relatively easily because you're not checking in code over a long period of time. It's happening multiple times a day. So it's continuous integration is cheap. Not integrating is expensive. So in other words, if you have code that you haven't checked in weeks, which is unlikely, but if you have code that you've been sitting on for weeks and you check that in and breaks the build, you're going to have a lot of time on your hands to figure out where that build broke, and it's not a pretty sight. So what about continuous delivery and continuous deployment? So continuous deployment is the ability to get changes of all types into production, or into the hands of a user quickly. Continuous delivery is the ability for a team to perform all integration tasks and make a production-ready package ready and available. So there's a difference here, and with continuous delivery, means that you're getting everything up to the point where it's ready to be pushed to production, but it doesn't actually go to production. Continuous deployment is once the build succeeds and everything test pass and everything's good, there's actually a push to production directly. There's no gates, as we would say, or nothing stopping it from going directly to production. So that's a big difference, and it's important to know what the difference is there. So you see here kind of the difference in a pictorial version where source control, you have your code that gets checked into source control. That's automated. The build is automated. And then you have it go to a staging environment. And the difference there, again, with the continuous delivery there you see is that there's an approval that needs to be done in order for that code to get pushed to production. With the continuous deployment, it goes straight to production with no gate or no approval needed. And that sounds like it could be somewhat concerning, but remember that if you are checking in code multiple times a day, that if you immediately get feedback in production that something isn't working the way it was intended, you're able to quickly iterate and get another push of code out very quickly. So there's a bit of a trade-off where you're getting features out quickly, but you're also able to get fixes out quickly. So every development team does things a little bit differently, but this is kind of a general approach to DevOps and the tools that are integrated with the DevOps pipeline. But you look at starting from the left there with code, Eclipse, Jira, Git, Subversion. They're used for code development and code repository. And then you go to your build and your test, and you have Maven and Gradle, Selenium, JUnit. Your release is done by Jenkins and Bamboo, which would push out to environments or get it ready to be pushed to environments. Puppet, Chef, Ansible, SaltStack, they're all used for deployment and orchestration. And then, with your monitoring, you have Splunk, New Relic. Again, those are these are all pretty common applications that are used in this space. But again, it varies where you work and the environment that you're in. And with that, I hope you enjoy this lesson and look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about DevSecOps. So we talked about DevOps and all the different aspects of DevOps and basically just the breakdown of the barrier between development and operations. With DevSecOps, a lot of the same security things that we've been talking about throughout this class still apply. It's no different. Things like threat model, use cases, code review, the tooling that we've talked about, all that still fits in a DevSecOps model. Tools can be slow, so it's a consideration. Something like static analysis tools tend to be a little bit slower with scans, so it is a consideration to make sure when we're looking at the DevSecOps model that we use tools that are going to be able to work better in that faster-paced environment. But it does allow for a faster feedback loop. As I mentioned in the lesson around DevOps, the point is that you're able to get things out to production quickly, but it also means, on the other side of that, means that you can push fixes out quicker. So patching becomes a critical part of the DevSecOps model, and making sure that you get security out to production quicker. So as I mentioned with DevOps, there's a lot of companies and development teams and organizations that do things differently. Not every organization is going to do the same thing. But will kind of give you a high level of where security fits into that dev and operations continuum. So if you look at the starting kind of at that predict and plan and as well as code and test, you look at what are we trying to do? What can go wrong? Let's start building in security into that. So that comes into threat modeling and doing some predictions around security and risks. And then you start layering in your tools like static analysis, integrated security testing, abuse case. You want to include them as well as making sure that you're doing secure code reviews. And then with the build, one of the things you want to incorporate into that is the mentality of break the build. So if for some reason your tooling and your tests come up with a critical finding or a high finding, you probably want to break the build and not allow that code to go out to production. So again, if you're talking about that continuous deployment model where code is going directly out to production, you certainly want to have that circuit breaker in there to make sure that if something is critical or high, it doesn't get pushed out to production. With tests, you want to make sure that you have common abuse cases like we've talked about in this course. And then once it's out in that pre-production environment, you want to do pen testing and fuzz testing. Make sure that it's compliant to the standards that you have built. Once it's out in production, it's a little bit different in terms of we haven't talked a lot about operational security, but there's the SOC or the Security Operations Center that's going to be doing incident root causes and monitoring and validating that that new risks that come out and may expose new attack surfaces, and making sure that gets part of, make sure that that's kind of part of the way that they address security. And then, should an attack happen, you want to be able to stabilize, so restore and maintain service for non-attack usage. Then again, we're getting kind of into the tools that we talked about with RASP, so Runtime Application Security Protection. WAF would be layered in there as well. And the ability to be able to turn off features. That's something that's built into that DevOps model where you may be able to deploy something in production, but maybe you don't want it to be made widespread, so you want to have a toggle on and off. And then from the operational perspective, you have intrusion detection, intrusion prevention tools that are a little bit different than the RASP and the WAF that we've talked about, but they're there to defend against impending attacks or ongoing attacks. And then obviously the monitoring, you want to make sure that you have logging into something like a SIM that's going to be able to organize all those different issues, make sure that you have enough knowledge to understand that there's an incident or an event occurring that you can react to. So again, every different environment's different, development teams are different, but this is just kind of a general high-level way that DevOps works with security in mind, so that DevSecOps model. So what about the tooling? Well, we talked about, with the DevOps, the different tools that are out there for building and monitoring and deployment and all that. So you can see the parallels with DevOps and DevSecOps in terms of tools. So GitLab check marks for source code, Splunk for using for CI server, In terms of testing and scanning, you have contrast, which we talked about, sonotype for artifact scanning, Tanium Nexus for artifact scanning. Around deployment, you have Beaker, and then monitoring things like Metasploit, Evident.io, FireEye, Splunk can be used for that monitoring as well. So there are, as I mentioned before when we were talking about tools, again, every environment's going to be different, every development team's going to be different, and there's always new tools that are coming out. So this is just basically so that if you see one of these tools, you kind of understand where they play. So the bottom line with DevSecOps is that you want to be able to make sure that you test early, test often. You want to use the scanning tools available, make sure that they're tuned and they're not impeding deployment, because that's the one thing you don't want to do from a security perspective, is make sure that you're still enabling, you want to make sure you're still enabling the business and making sure that you're not adding hours onto a build when it should normally take like minutes. All the tools that we talked about, the RASP, the DAST, WAF, IAST, all the other types of security tools that we talked about, they're still relevant. Things like SAS may be something that, again, because of the latency there, you might want to consider that maybe that's not as important and can be relieved by a different tool. You want to have that constant feedback loop, so as things go into production, that feedback loop is going to be important to be able to push fixes out to production more quickly. Make sure your monitoring is properly tuned, and that you're getting vulnerability information that's actionable out of operations, so you can put that back into development and get development to create a fix that can be pushed out quickly. And then you want to also make sure, again, similar to what we talked about before, is make sure that you're monitoring for your third parties and you're getting notifications so that gets into the hands of development so that they can react to that quickly. And with that, I hope you enjoyed this lesson. Look forward to seeing you next one. Thank you. Welcome back, everyone. In this lesson, we're going to talk about abuse cases and misuse cases. So a use case in software development, and some of you may be familiar with this if you're already in software development, but a use case is basically a way to put a requirement in a story form. So in other words, it would come across as saying something like, as a user, I want to be able to log in and access my shopping cart or something to that effect. That's a use case. So the actor in this case could either be a human one or it could be another system, some type of external system. But basically, it's a way of putting a requirement into a story format. So a sample use case here, and this is a bit of a spaghetti diagram, no pun intended, because it's supposed to be about a restaurant. But you have a cashier, you have a client, you have a cook, and basically, and a waiter as well. And basically, there's lines that say, you know, as a customer, I want to be able to order food. As a waiter, I want to be able to take food. As a cook or a chef, I want to be able to make the food. And then as a client or a customer, I want to be able to cash out, and the cashier needs to be able to take it. So basically, this is a diagram that creates a bunch of different use cases. And you would state these in the sense that as a client, I want to be able to eat food. And that's how you build kind of your application around, you know, these use cases. So that's not important. The important part to think about here is use cases and how they relate to things like abuse cases and misuse case. So when we're talking about misuse and abuse cases, a misuse case highlights something that should not happen and the threats hence identified. So in other words, it's not necessarily malicious, but it's something in the system that just shouldn't happen. Maybe it's a hardware failure or something along those lines. But this will help you in identifying new requirements to, again, if it's a hardware failure, maybe you need to get more highly available hardware or redundancy built into the system and so forth. An abuse case is a type of complete interaction between a system and one or more actors where the result of the interaction are harmful to the system. So this is where there's an intentional activity to reduce the system in some way, create a threat against the system. So that's an abuse case where, again, think it's more intentional. It's a person or system trying to actually harm your overall system. So here's some sample abuse cases where a user is trying to enter username and password, and then you have your application as well that's trying to process some of that activity. And then on the right, you have a hacker or a malicious user that's actually trying to do some nefarious things. And drawing out this diagram helps you kind of identify, well, what is it that the user is supposed to do? How's the system supposed to actually process those things? And more importantly, what are the opportunity for the hacker or the malicious user to somehow compromise that system? But drawing this out will help you identify, well, what are the things I should do in order to make sure that this is done in a more secure manner. So you see some of the mitigations outlined here, specifically around brute forcing. You want to have a lockout feature, for instance. So, drawing out these diagrams helps you kind of identify the potential for malicious activity and the ways that you can mitigate it. And we're going to get more into some of that stuff when we get into threat modeling and risk assessments later on. But with that, I hope you enjoyed this lesson. I look forward to seeing you later. Thank you. Hey everyone, welcome back. And in this lesson, we're going to start talking about analysis tools and then get into static analysis. So some general guidance around analysis tools. A lot of organizations, most of them will use some or maybe even all of the analysis tools that we're going to talk about within their development lifecycle. Not each solution is a silver bullet, so keep that in mind. Just because you run something like a dynamic analysis tool or a static analysis tool doesn't mean that it's going to solve all your security problems. And one thing to consider too is that many of the analysis tools that are out there are platform or language dependent. So for instance, some of the static analysis tools only support a certain set of languages. And in order to cover your language, you may have to get multiple tools. Or if you have an enterprise that has multiple languages, which is common, you may have to use two different tools to cover all of your languages. Results are different in each solution, and there are many false positives. We're going to talk about that here in a minute. You may be mandated by the environment that you work in. So for instance, you may have government mandate, you may have regulations that mandate that you run analysis tools. So you're not doing it just to be nice, you're doing it because you're under guidance or regulations to do so. Every vendor will tell you their solution solves your problems and fits your needs. It's important for you or your organization to understand what it is you're trying to solve with an analysis tool and make sure that it actually fits the use case that you're looking for. So false positives of finding in a tool or through some other technique that turns out to not be a viable finding. So this is pretty common in analysis tools, where an analysis tool is going to give you a result and say, I found a vulnerability, and when you actually dig into it and look at it, it's not actually a vulnerability. So that's a case of a false positive. So a tool may claim, and this is common, this example here is a very common one for static analysis tools, is that the tool may claim that it found a password in plain text in your code. When you go and look, it may just be a variable named password, and the static analysis tool took that as being a plain text password. So a false negative is a vulnerability that is able to get past the scanning tool without being identified. So for instance, a SQL injection vulnerability that's not identified by a scanning tool. And the way you uncover those is because you have that layered approach, or because you're using multiple analysis tools. It may be found in one tool and not another. That's a false negative. So let's talk a little bit about static analysis tools. So how static analysis works, static code analysis commonly refers to the running of static code analysis tools that attempt to highlight possible vulnerabilities within static non-running source code. So the important thing to keep in mind here is that static analysis tools will look at the actual text of your code. So it's not looking at the code as it's running. And that's why I gave the example of a static analysis tool finding something like a plain text password or a password in the code, when in reality, it's not there, but it just sees that the word password is being used, or some derivation of the word password in your code, and it says, oh, I found a password in your code. And that's because the static analysis is just going through your code and looking at the text in there and trying to uncover possible vulnerabilities. Now, it is doing some logical flows and trying to understand that, and we're going to talk about that here in a minute. But most static analysis tools are used as an aid for analysts to help zero in on security relevant portions of code. So it's going to help you identify maybe some hotspots or some areas that you may need to focus in on. So there's two different types of ways that static analysis works, and that's through taint and lexical analysis. So with taint analysis, it attempts to identify variables that have been tainted with user controllable input. So as we talked about throughout this course, anytime a user has influence over the input into the application, that's a potential point of vulnerability. So that's how static analysis tools look at it, and they call it taint. So because it's been tainted by a user. So it'll also another term that's used here is the sink. So basically, where that input has come into the application, it's going to follow that through the code until it finds a sink where it goes into a function, and it's going to zero in on that and try to identify whether, for instance, has that variable been reviewed from a security perspective to make sure that it's been scrubbed and sanitized and all that before it goes into that function. If it hasn't, then it's going to flag that as a finding. The other way is lexical analysis, which converts source code syntax into tokens of information in an attempt to abstract the source code and make it easier to manipulate. So with that, it's more doing a bit of a block type of scan, where it's putting the code into different blocks or components for easier identification of vulnerabilities. So from a high level, the way static analysis works is there's a translation phase and a scan phase. And with the translation phase, it's going to take a compilation of the code when you compile it, and it's going to then create a model extract, which is basically the language that the analysis tool speaks. So it creates a file that is able to be scanned by the static analysis tool that you're using. And in the scan process, again, this varies per tool, so don't take this as how every tool works. It's just from a high level. So it's then going to look for things like pattern matching. It's going to try to find password in the text, as I mentioned before. It's going to do some control flow analysis, making sure that connections are properly closed and so forth. And then also it's going to do some data flow analysis. So it's going to look at the parameters that are coming in and making sure that it's been properly sanitized and following it to potential sinks. So in terms of the strengths of static analysis, it helps identify code flaws in the code, which is what its primary purpose is. You do need some trained software developers that are familiar with the code that it's being scanned, because when vulnerabilities are found or when something is identified, you want to have somebody with knowledge of the system or software to be able to triage that issue. It's a fast and easy way to fix errors, so you can find issues early on in the development lifecycle before they get out to production. You have the ability to be able to potentially stop a vulnerability from going out. With automated tools, it becomes fast to scan and review the software because it's automated. It's doing basically a code review for you in an automated fashion, and this provides mitigation recommendations as well, which is a pretty good strength for static analysis tools, and it's true for most analysis tools. Is that not only does it discover something, but it's also going to give you some recommendations on how to mitigate it. So with static testing, it's possible to find errors at an earlier stage in the development lifecycle. Like I mentioned, that obviously is huge because you want to be able to get what we call shifting left or further left, is being able to find vulnerabilities before they actually make it out to production. Static analysis provides that ability for you. So some of the weaknesses for static analysis: it demands a great amount of time when done manually. So if you're doing any kind of review of the analysis, the output from the analysis, that has to be done manually. It takes a lot of time. It typically takes somebody that's very familiar with the code, so therefore it's probably a seasoned person that's looking at it, or at least you may have less seasoned people looking at it, but eventually your more senior SME for the product is eventually going to have to weigh in on it. So automated tools work with a few programming languages. Like I mentioned before, you may get a static analysis tool that doesn't work with all the languages that you use. It may only work for a subset. Automated tools may provide false positives. That's a very critical part of static analysis tools, is that they're pretty well known for creating false positives, or at least reporting false positives. And then these automated tools, these static analysis tools, are only able to see the code. So it's not actually seeing it while it's running. It's only seeing it as it sits in your either code repository or in the build process. Automated tools cannot pinpoint weak points that may create troubles in runtime. So again, it's only looking at the code as it sits. It's not looking at it while it's running. So there's some examples of tools that are out there that you may see as you work in this space. But SonarQube is one. Brakeman is one for Ruby. AppScan, Fortify, Spotbugs is another one that we're going to talk about here, because that's a free Eclipse plugin that you can use. But there's a lot of companies out there that are in this space, so this is just a small portion of those that are out there. So with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. All right, welcome back, everybody. And I'm going to show how to use Spotbugs here in Eclipse. And like we spoke about before, Spotbugs is a static analysis tool, so it's looking at the code and determining whether there's security vulnerabilities within the code itself. So I'm going to show you how to set it up here. I do already have it set up in Eclipse, so I'm going to walk through just how to get that going. But the first thing you want to do is go up to Help and go to the Eclipse Marketplace, and you want to make sure that you actually have Spotbugs installed here. So I'm going to do a search here for Spotbugs. And you'll see here it says it's already installed, which is fine. I just actually installed it a little bit ago. But it'll give you some information about what Spotbugs is. It's an Eclipse plugin. It'll give you some updates on, or some information around what it checks. So it's looking for 400 bug patterns, such as null pointer, dereference, infinite recursive loops, and so forth. Now, Spotbugs is a static analysis tool, which is basically looking for any kind of code quality or other types of issues. However, it can be configured for security checks as well. So in its pure state, Spotbugs is basically an analysis tool looking for just code quality issues. So, okay, so since I already have it installed, I'm going to go ahead and cancel out of this. And then I'm going to go ahead and take a look at my project here. The project I'm using is eSAPI, which is a OWASP. It's an OWASP project, and it's basically for secure code. You can pull this into your Java project that you're working on and use it to pull in secure coding that you don't have to write yourself. It's already been written by OWASP. So it's handy to have, when you don't want to use your own, or you don't want to write your own security code. So if I go ahead and look at the properties here, I see Spotbugs is already listed here because I added it as a plugin. The other thing you may need to do here is to look at whether the plugin is actually installed and where it's installed from. But we'll skip that part here. What I would say is that if you have issues getting Spotbugs to show up here as a plugin, Google's your friend, so go out and look and see what's out there. So as I mentioned, Spotbugs is basically a static analysis tool. So you can see here where you can set it to look for bad practices, correctness, performance, and so forth. What I'm going to do is set it to look for malicious code vulnerabilities, security issues. We'll leave the other stuff out here, so you can have it warn on certain issues. So maybe you don't care so much about things that are of concern or troubling. You're only worried about the scary and scariest things. So I'm going to go ahead and apply and close here, and then what I'm going to do is right click and go to Spotbugs and do a find bugs, and you'll see here it's going to start running. You should see the progress as it goes through. Now, this can take some time, so just be aware that it, depending on the size of your project, could take a fair amount of time to get through this. But in this case, hopefully it should be pretty quick. Okay, so it's almost done here, and said it found 31 warnings, and you want to switch to Spotbugs perspective. Sure, let's go ahead and do that. So here it's showing a couple things. So normal confidence and high confidence, meaning high confidence means that it's fairly fairly sure that it's an issue that you should take a look at. Normal confidence means, it's somewhat sure. Now, a couple ways to filter this. If you are looking for the scariest or scary issues that come across, you probably want to, if you have your settings to look for of concern and other, lower issues. If you're trying to focus on the high priority issues first, you probably want to look at scariest with high confidence. That's probably where you want to put your focus. So we'll go ahead and take a look here. Scary, high confidence, hard-coded key. Let's take a look at that. And here you'll see, which is correct, there's a hard-coded key here. This key is putting into this byte key and then passed into this secret key spec function or object here. So yes, that's a hard-coded key. Now, of course, that may or may not be of concern depending on your use case, but this is something that you definitely want to take a look at. Nice thing about spot bugs that it's going to give you this information around the common weakness, like we talked about before. Here's the rank. It's a scary high, hard-coded key pattern, and so forth. So to give you information about the issue, that it found, why it's a problem, and that'll hopefully get you along on your way to fix. So that's a quick overview of spot bugs and how to get it up and running in Eclipse. And hope you enjoyed this talk, and I will talk to you later. Hey everyone, welcome back. And in this lesson, we're going to start talking about dynamic analysis. So dynamic analysis, or DAS tools, which stands for Dynamic Application Security Testing, it's basically a black box type of testing. So it's looking at an application while it's running. So if you remember, we were talking about static analysis tools, and those tools look at code as it sits in a repository or as you're developing it, and it's looking at the actual text or the code that's sitting. Whereas dynamic analysis is looking at the application as it runs. And if you remember when we talked about static analysis, one of the weaknesses of static analysis is that it doesn't test the application as it's running. So dynamic analysis is looking from the outside in, and it's trying to determine whether there is weaknesses within the application by having that outside in view. So for the most part, dynamic analysis tools are platform independent and language independent, meaning that it doesn't matter whether you wrote the code in C# or Java or Ruby or any other language. What the dynamic scanner is looking at is the application as it's running. So there's less dependency upon the technology that's running. Now, it also depends a little bit about what type of analysis tool that you're using. There might be some instrumentation that you may have to do that bleeds over into a different type of analysis tool, which we'll talk about later. But there are some cases where the dynamic analysis tool may need to have some kind of hook into your application to get better results. And that's where the technology dependency may come in. But for the most part, dynamic analysis tools are technology independent. So some of the strengths with dynamic analysis, again, it's not technology dependent in most cases. It can be run in production, which isn't really recommended, but you can do it. So for instance, you can point a dynamic analysis tool at a production environment and run. Now, obviously, there's a lot of concerns with that because you're essentially trying to attack an application that's running in production, and you could cause some issues there in terms of maybe making the application unavailable or causing other kinds of issues with perhaps the data, and that may not be the results that you want. Now, you can typically try to configure the dynamic scanner so that it doesn't have that large of an impact. But it's mostly recommended not to run a dynamic tool in production and instead run it in a lower environment, like a testing environment. With dynamic analysis, you don't get as many false positives, but you also don't get you don't get the same amount of results that you would get from a static analysis tool. So static analysis tools tend to have a lot of results that come back. Dynamic analysis tools are usually a little bit shorter in the results, but a lot of them are not false positives. Now, again, it depends on the tool that you're using. But this is generally a good rule of thumb that you're going to get fewer false positives than you would in static analysis. The other thing is that you can run dynamic analysis tools against applications that you don't own. Now, obviously, you want to make sure that if you are going to run a dynamic analysis tool against code or an application that you don't own, that you have permission from the owner of that application to do that, because otherwise you could end up in some legal trouble. And it can also be used to enhance penetration testing. So a lot of pen testers will use tools, obviously, to help them navigate a penetration test engagement. So they're not always doing a lot of manual testing. There's going to be a lot of tooling that's used in order to help enhance that testing engagement. Some of the weaknesses that may be found in dynamic analysis tools is that you're not going to necessarily be able to find the line of code where a vulnerability may be found. So an analysis tool may tell you that the UI is susceptible to SQL injection or cross-site scripting, but that's not going to give you, in most cases, it's not going to give you the line number for where that code can be found. Sometimes it can, but again, it depends on the tool and the way it's configured. Findings are found later in the SDLC, so that's one of the strengths, if you recall, from static analysis, is that you can do that further left, as we were saying, so further earlier on in the development lifecycle, whereas a dynamic testers, because it has to be run against a running application, well, your code's already pushed to an environment in order for the dynamic analysis to work. So therefore, you're already further right from the development than you were with static analysis. And it doesn't locate code-specific security issues. So, for instance, hard-coded passwords or other types of issues that are within your code. It's not going to locate that because, again, that's not the job that it's supposed to do. And then findings still need to be verified by a subject matter expert. So somebody still needs to be able to review those findings and make sure that, hey, is this really a true positive or is this a false positive? So just some examples of different dynamic analysis tools, similar to what I said with static analysis. This isn't the end-all list. There's a lot of tools in this space. And that's true with all the analysis tools that we're going to talk about here. There's a lot of players in the space, but in terms of dynamic analysis, the ones that usually rise to the top here are OWASP, ZAP, White Hat, Qualys, Veracode, and Arachne. So these are all dynamic analysis tools. So if you see them, now you understand what they are. And some of these do other things as well. It's not just dynamic analysis, but these are some examples of tools that are out there. So with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about interactive application security testing, or IAST. So what is IAST? Well, it assesses application from within using software instrumentation. And basically what that means is that in most cases, you're going to have to embed a library from the vendor into your software build. So just as you take on other third-party libraries when you're building your software, you would take a library, a jar file or DLL or something like that, and embed that into your software build so that it's actually part of your application. And this allows for IAST to really bridge the gap between static analysis and dynamic analysis by having better visibility into the vulnerabilities as they're being exploited. So it provides a method for accessing code, also being able to see the HTTP traffic as it's occurring, and be able to get information on backend connections and configuration as well. So some IaaS products require the application to be attacked. So that's one of what I would say weaknesses, and we're going to get to that in a second. But the one thing to keep in mind here is that in order for an IAST tool to be able to discover vulnerability, it actually has to see it occur. So in other words, if you have this embedded in your application and there's a certain functionality in your application that never gets touched, well, the IAST tool is not going to be able to see that. So some of the strengths, so there's an agent or something that you have to include within your build. That means that there's continuous monitoring, so that's good. You have that in there. It's continuously monitoring as long as that portion of the code is being exercised. It works well in DevOps because, for instance, with static analysis, some of the big complaints with static analysis is that it takes too long for static analysis tools to run. It sometimes, depending on the size of your code, it can take hours to run a static analysis tool. That doesn't work well in a deployment model that has you deploying code maybe even every hour or at a very fast-paced frequency. So there's lower cases of false positives since the tool can actually see the attacks as they're happening. So yes, it sees it and says, yes, this is happening. I see a vulnerability, and can have a targeted approach when defining the scope. So you may be able to just include certain areas of your application to be part of the testing. So some of the weaknesses that may be a part of IaaS tools is that agents, like it's a strength as well, Agents can be a weakness in the sense that it's something else that you have to maintain. You have to make sure that it's constantly up to date. There may actually be some development, as you see in the next one, development or deployment changes that you need to make as well in order to take advantage of it. So there is some overhead with using another library to add to your build, or there's some development effort that might be there. There's also some operational effort that might be there. So it's just something to consider, that it's something else you need to include, something else you need to maintain, and something else that could actually inhibit your application from functioning properly. So the other weakness is that in order for it to detect a vulnerability, it has to actually see it. And that means that, as I mentioned before, there could be corners of your application that never get touched or never get exercised. In that sense, it may not, the IS tool is not going to be able to see any vulnerabilities that might be in that portion of the code. Now, you can overcome that by writing automated testing that does actually exercise at least the most important parts of your application to ensure that it's able to see any vulnerabilities in those areas as they might occur. And then there's a steep learning curve for deployment and reviewing the results, since it doesn't point to the line of code. It's similar to what we talked about with dynamic analysis. It's not going to tell you which line of code has that vulnerability. So with some IS tools, you probably will get that, especially if it's able to view the code. But that's not always true with all IS tools. So it's just something that may vary per vendor. So as I mentioned before, there's some vendors that are out there that have IS tools, and some of these vendors also have other tools as well. So Acunetics, Checkmarx, and Synopsys are some of the top ones that have prominent IS tools. And again, there's other ones out there. Just this is so that if you ever see these vendors, you know what it means. And with that, I hope you enjoyed this lesson. I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about RASP, or Runtime Application Security Protection. And as the name implies, Runtime Application Security Protection is instrumentation that is inside your application that will block attacks as it sees it happening. So similar to what we talked about with IAST, or Interactive Application Security Testing, this actually acts to block attacks as it sees it, instead of just reporting it as a vulnerability. So this can improve the security of software by monitoring the inputs and blocking those that could allow attacks, while protecting the runtime environment from unwanted changes and tampering. So some of the examples of things that could be blocked are terminating a user session, shutting the application down, alerting security personnel, and sending a warning to other users. So that's an example of what would happen if it does see an attack that's happening. It's capable of being able to at least beacon out and say, hey, there's something going on, after it blocks. Now you can configure it to run in something what they would call like a passive mode, which is basically allowing activity to happen even though it may think that it's malicious. It may allow it to happen and then just simply alert. And the reason you may want to do that is because if you're in an environment that availability is your highest concern, you may not want to have a tool potentially block workflows and create an availability issue when maybe it's not necessarily malicious. Now, that's all depending upon your risk profile. Again, if availability is your highest concern, you may want to just put it in passive mode and maybe block on some certain high confidence vulnerabilities that may be occurring. But again, that's all based on the risk that you're willing to take. So some of the strengths with RASP, it can be configured to block or monitor, as I mentioned. So you can either block malicious traffic as it's happening, or you can just monitor and alert if it sees something. And because it can block when as attacks happen, obviously that's what you want. It gives you the protection that you need for your application in order to ensure that there's no vulnerabilities that are exploited. Since this is similar to DAST and IAST, you can see the same strengths that are there from those two as well. So, for instance, being able to provide protection in a production environment, being able to have a lower case of false positives, and so forth. So, some of the weaknesses with RASP, it needs to see an attack as it happened, similar to what we saw with IAST. And there's also potential for it to block legitimate traffic, as I mentioned before. If your main concern is availability, then you may not want to have this tool configured to block traffic, because it could create an availability issue. And then someone needs to own the rules that define what is blocked. Now that's another big concern, especially in a large enterprise, is who owns those rules. You may not want your security team as a development team. You may not want the security team to own those rules because you may have different things that change within your application that the security team may not be aware of. And again, that gets back down to where it could create an availability issue if, for instance, your security team tweaks the rules a little bit and therefore starts blocking legitimate traffic. So in most cases, you would want your development team to own those rules because they're the ones that understand how that traffic is actually supposed to navigate the application. So since this is similar to DAST and IAST, again, same weaknesses that you have with those two tools as well, is where you're further off into development and that may not be as big of a concern with RASP, but one of the other big weaknesses that's actually part of RASP and not really mentioned here is that in a case where maybe you're not actually fixing the issue with RASP, and that's the same with any kind of blocking types of tools that you have. It's not solving your problem; it's just potentially mitigating the issue from the vulnerability from being exploited. But that vulnerability still exists within your application, so that's a concern that you should have because the fundamental problem has not been resolved. So there are a couple different tools out there, and again, as I mentioned before, this isn't all the tools that are out there. There's plenty of them out there. These are just some of the more well-known ones. So WallArm, Imperva, and RXM are three of the ones that usually bubble up to the top. Again, there's other types of applications and tools out there. Not advocating for any of these, just so you know that when you see these, you know what they do. And with that, appreciate your time and look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about WAFs, or Web Application Firewall. So similar to what we talked about with RASP, a Web Application Firewall reviews the traffic that is coming into a web application and inspecting it for potential vulnerability or potential attacks. So it applies a set of rules to an HTTPS conversation, and it's able to block such attacks like cross-site scripting, SQL injection, and so forth. It's deployed in front of a web application, and it looks at both directions, the request and the response, and detecting and blocking any malicious content it might find. This can also be implemented either as a software application that's sitting on perhaps a different host or on the same host that the web application is running on, or it can be a separate appliance, what we would call appliance, like a piece of hardware that's sitting on the network. So it can be deployed in two different ways. And they can also be used as server plugins. So on your web server, you can use that. And also, WAFs sometimes are integrated with other types of technology that already exist on your network. So like a load balancer or firewall may have a web application firewall component of it. And sometimes you may hear the term ASM, or Application Security Manager. It's the same, similar concept to a WAF, and they're sometimes used synonymously. So there's two different ways that you can deploy a WAF: in transparent mode or a transparent bridge. Basically, this is where only a section or a subset of the traffic is put through the WAF and inspected, and all other traffic is allowed to pass transparently. And then there's the reverse proxy, where basically all the traffic goes through a proxy and is inspected through that proxy before it goes back to the web servers. And here's just a pictorial version of what a WAF looks like. You have your end user that browses to the application over the internet. You have a web application firewall in front of it that inspects all that traffic before it sends it back to the web servers that are serving up the content. So some of the strengths, it can be in blocking or reporting mode, similar to runtime application security protection that we talked about. It can be independent of the application, so you don't have to instrument anything, and that's one of the key differences between a WAF and a RASP. Is that you don't have to necessarily configure anything within your code or do any special development. It's something that can be separate from your actual application. And then it can block a lot of the common attacks that you see there: SQL injection, cross-site scripting, cookie poisoning, invalid input, denial of service attacks, web scraping, and so forth. So some of the weaknesses with WAF is similar to some of the other tools where there's potential performance issues. So because you have your traffic going through a proxy and it's doing an inspection of traffic, that could add some latency to your web traffic. So that could possibly be a concern, something that you want to keep an eye on. And then, like I mentioned with the runtime protection, you're not actually solving the vulnerability. So if you have a SQL injection issue that is caught by runtime protection or by a WAF, it's only going to block it or report that issue exists, but it's not going to obviously fix the issue for you. So you still have an issue of vulnerability that you need to code a fix for. And then it can't protect against every security issue. Similar to what we talked about with some of the other tools, where, like, for instance, it's not going to know that you have a password in plain text in your database or something like that. So, or security misconfiguration, things like that. So again, this is where that defense in depth comes into play, where you want to be able to use a static analysis tool, a dynamic analysis tool, runtime protection, and so forth to really add that layered security to your application. So there's a couple different types of WAFs that exist out there. There's the network-based. So with the network-based, you have low network latency because it's connected directly to the web servers. So that's obviously a benefit there. However, there's a higher cost and tougher management across large data centers. With host-based, it's affordable. There's no network latency because it's right there on the host that it's trying to protect against. But one of the drawbacks is that you have agents that you need to manage. I talked about agents before. And then there's also some engineering cost and time that's associated with making sure that it works correctly with the WAF. And then with cloud hosted, it can be considered the cheapest. It really depends. And then it's maintained by a third party. And really, this is just basically where you proxy all your traffic to a cloud hosted web application firewall. So you get all the benefits of cloud hosted, where as a service, software as a service, where the third party is maintaining it. They're making sure that it's up to date. They're managing all the rules and all that. However, there can be very high network latency because obviously you're going not even just in your network, you're going to a cloud service to be able to get that protection. And then there's no real ownership in terms of owning the rules and things like that. It's owned by a third party, so you don't really get that ownership. Now, of course, you can kind of negotiate that if you're a big player, but there's some drawbacks on that as well. So. And with that, I hope you enjoyed this lesson. Look forward to seeing you next one. Thank you. Hey everyone, welcome back. And in this lesson, we're going to talk about penetration testing. So there's several different types of penetration testing. There's white box, which basically means that the testers have full visibility into the application that they're testing. They may get documentation, accounts, network diagrams. Basically, they're not going to go in there blind. They're going to have a full set of information to be able to perform a very thorough penetration test. There's black box, where basically the testers may be given, in the case of like a web application, they may be given basically the domain that they're being asked to try to test, and that's it. They may not be given any other information, which means that they have to go out there and do some reconnaissance and pull the information that they need in order to perform a test. And then gray box is somewhere in between, where maybe there's some information that's provided to the testers, but not full system information. There's also internal versus external. So internal penetration testers, you can think of them, sometimes they're called red teams, but red teams also mean a little bit different than just regular penetration testers. Red teams do a little bit more threat hunting and threat intelligence. But an internal penetration testing team does basically the same thing that an external penetration tester would do, just from inside the organization. So your company may have penetration testers on a team that do regular penetration tests of the applications that exist within that organization. An external penetration tester is a third-party company or organization that you hire to come do a penetration test against your organization. So, and a lot of times, if you are, depending on what industry you work in, you may have requirements to hire third-party penetration testers to do a test annually. So there's purposes for each one of these, and there's use cases for each one. So some of the strengths with penetration testing, obviously findings are typically true findings because the penetration tester is acting as an attacker. So if they find a vulnerability and they're able to exploit it, well, it's a true positive. The other thing is that a penetration test engagement can be typically scoped to specific areas and specific times, and that allows you to be able to focus the testers in an area that maybe you're more concerned about. And then also, in terms of time, you're not opening the doors for them forever. You're giving them a period of time that they can do their engagement. And it can be used in combination with other security methods. So, for instance, you may want to give the penetration tester, especially in a white box type of testing engagement, you may want to give them your threat model or other information that you have, maybe some of your scanning output, for them to be able to focus on specific areas that may be hotspots that they need to potentially look at. Some of the weaknesses, so it's not usually a full system test because that can get expensive and also time consuming. So you're not usually only focusing your penetration testers on a given specific area. So you want to kind of risk rate where you want to have them focus, and that allows them to just spend their time there. It can be expensive and time consuming, as I mentioned, especially for external penetration testers. When you're bringing in a third party to do pen test, they tend to be expensive because they know that they're filling a need that you potentially don't have internally, and also they know that there's requirements given in certain industries where you need to have a pen test done on an annual basis. So therefore, they know they can charge a little bit more. So the findings need to be secured, especially by when you get a penetration test done by a third party. You want to make sure that those reports are properly secured so that it doesn't get out into the wider audience. And with that, I hope you enjoyed this lesson, and I look forward to seeing you in the next one. Thank you. Hey everyone, welcome back. And well, you made it. So this is the conclusion. We're going to basically wrap up and talk about some of the different concepts and principles that we've discussed throughout this course. So I'm just going to basically go through these. Configuration management. Remember that all sensitive data should be encrypted at rest. You want to catch all errors and display specific messages, but be careful. So in other words, when you have error messages, you want to be able to provide enough information for someone to understand what the issue is, but not overly share information to lead an attacker to be able to understand more about your system. Production data should only be in production. That sounds pretty simple, but it's not uncommon to see production data in development or lower environments. Follow all guidelines for server, OS, and database hardening. And then account management, so we want to make sure that least privilege, so database accounts should be least privileged, only read-write access to those tables and fields that they need. OS accounts for the database should not be domain, admin, root, or system accounts. Change or remove all default accounts and passwords, so that kind of bleeds into the security misconfiguration as well. Pick more difficult account names, so don't name your admin accounts admin. Use two-factor authentication, especially around privileged accounts. Password management. Make sure that you require a hard to guess password, so a strong password. You want to, when you're storing them, make sure you're salting and hashing them. Don't store passwords unencrypted, and having a strong password recovery system, one that's not easily circumvented or one that's not easily fooled. Don't hard code secrets. So put secrets in a configuration file and keep that in a secure location, preferably encrypted. Use hardware security modules where available. So these are hardware appliances that can do key management for you. Secrets should be stored away from the data that they secure. So if something happens to the data, the key to unlock that data is not in the same location. Restrict and monitor access to files on the server. So you want to make sure that you at least are not allowing everyone to have access to files on a server, and that you're actually monitoring and tracking who has been accessing that information. So for upload and download management, restrict types of using server-side code. So you want to make sure if you're expecting a PDF file that that's what you're getting. You're not getting executables. Configure directories so files cannot be executed unless it's absolutely required for your use case, but in most cases that's not the case. Restrict permissions on files so users can access only their own files. So you want to make sure that somebody can't push files to your application and be able to execute maybe under a different user, or be able to execute code or files that haven't been uploaded by them. Make sure that you disallow directory traversal and arbitrary file retrieval, and then use whitelist, not blacklist. So in other words, you want to make sure that you only, the list that you create only have files that are accessible. You don't want to be chasing down different types of files using a blacklist style. So the whitelist just means, I'm only allowing PDF files and Word documents or something like that. Whereas with the blacklist approach, you're going to say, I don't accept JPEGs, I don't accept PNGs, and so forth, and that list gets a lot more difficult to manage. If you learn nothing from this course, as we talked about before, the biggest takeaway here is validate inputs. So you want to make sure that you don't trust, especially across the internet, anonymous, you want to make sure that you don't trust any inputs coming from the internet. You want to clean that data, scrub it on its first entry point so that it doesn't have the opportunity to infect, potentially be executed on by a function within your application. Sanitize per program's context if reusing some user input from database internal storage. And then there's multiple types of injection. We talked about all of them: database, SQL, OS, and so forth. So be on the lookout for not just SQL injection, but all the other injection types that we talked about. Logging and alerting. You want to make sure that the logging that you do provides enough information so that you can put together, in case there's an incident, that you're able to trace it back to an individual. So you want to be able to make sure that your logging is able to assist in an investigation. But be aware of logging sensitive information. So not everything needs to be logged. You certainly don't want to log things like passwords, social security numbers, and other types of sensitive data. Data in motion, always use TLS. There's no excuse nowadays to not be using something like TLS, or for FTP. Make sure you're using secure methods like SFTP or FTPS. So use best practices for encryptions and ciphers. Don't roll your own. Don't create your own type of encryption standards. They're already out there. They exist. Just use them. Only use reputable certificate authorities. So we talked about digital certificates and certificate authorities in a previous lesson. There have been issues with certificate authorities issuing bad certificates or not doing the minimum of their job. So you want to make sure that you properly vet a certificate authority that you're using and make sure that they're reputable. And then also have a way to revoke certificates and keys that are associated with those certificates. So with security planning, you want to make sure that you involve the security team when planning a big feature, or when you have a release that has, especially when it's a high-risk release, or when you have functionality that has high-value transactions in it. You want to add security features or controls to user stories when you're doing that planning. And then make sure you create and maintain threat models like we talked about. Write and test abuse and misuse cases and make them part of your testing suite. You want to minimize the attack surface. So more points of interaction equals more areas to defend. So obviously in today's day and age where everything's API driven, there's a lot of openings. Having all those APIs means there's a larger attack surface. So that's something to be aware of. But having proper controls around those services will help reduce risk. Least privilege, as we talked about, not everyone should have access to everything. I like to use the example of Jeff Bezos, who owns Amazon. He doesn't need access to all the databases in AWS. So similarly, you want to make sure that just because someone's in a given role doesn't mean that they should have access to everything, even if it's somebody like Jeff Bezos in AWS, right? So make sure that your systems are set up to only allow people or services or systems to have access to what they need to do their job. So defense in depth, this is another big principle that we've talked about, throughout this course, and another big takeaway here is that, you don't want to rely on a single tool or single security methodology to protect all of your sensitive data. So a layered approach is a better practice in terms of making sure that you have a more robust security program. So this is important because sometimes things fail, and sometimes your tools fail, or they don't catch everything. And then there's also a lot of edge cases, and that you want to make sure that you have all the tools and processes in place to catch. And the more friction you add for an attacker, the more likely it is that they're going to go for an easier target. So remember, fail safe and fail open. So failing safe is failing in a way that will refrain from harm. Fail safe, system does not shut down during a failure condition. Right? So remember to keep those in mind as well. Don't blindly trust. So, that kind of wraps in the whole injection, least privilege, authentication, authorization. Your users, although may not be malicious, there's also the ability for users to maybe accidentally misuse your system. So, you want to make sure that you have all the proper controls in place, regardless of who's using your system, regardless of whether you feel like you don't have sensitive information, or whether you feel like you're not a target. You don't want to blindly trust your users. Remember the separation of duties. So we want to make sure that there's certain workflows that you don't want to allow one user or one person to be able to do that workflow end to end. So the example is usually the change of address and the authorization of checks. You don't want somebody to authorize checks on an account and also be able to change the address on that account, because they could change the address to their home address and have checks issued to their home for a different account. So that's a simple example of separation of duties, but you want to make sure that for your high value transactions and high value operations, that you have the proper changes in duties to make sure that not one operation is able to do an entire operation end to end. So avoid security by obscurity, and basically this means, like the example here of hiding your house key in a rock that you put outside of your house in case you get locked out, or maybe hiding your cash in your shoe because nobody's ever going to see that. But the reality is that it provides you a little bit. It's not out in the open. It's not like you're leaving your key, sitting out, or leaving your cash just laying around. But somebody that's really wanting to press hard will be able to find that, and your house key, they're going to be able to find it. Your cash, they're going to be able to find it. So it might discourage some passerbys, but it's not a persistent attacker is not going to be put off by obscuring security. And remember to keep things simple. You want to, the simpler the design, the simpler it is to be able to integrate security into that design. When you have a more complex design, and this gets down to the attack surface, the more complex your system and the more complex the design, the more opportunity there is for failures, and you're opening yourself up to higher risk that way. And then, as we talked about with WAF and RASP, those types of tools will only be able to block attacks from happening. So you may have a SQL injection vulnerability in your application, and you'll put a WAF in front of it, and it'll block SQL injections, but that WAF may not always be there all the time, or it could fail. And that means that the issue is still, your vulnerability is still there. So when a security vulnerability is discovered, the appropriate approach there is to fix the real problem. Now WAFs and RASPs, they all have their place in terms of being able to provide protection in real time until that fix can be implemented. But it's not a fix to the actual problem. And then the last thing, don't reinvent the wheel, as I mentioned, especially around encryption. You want to use standards and the security models that already exist out there. They're well vetted. They've been in use for a long time. A lot of times the newer thing's not always the better thing because it hasn't really been tested the way that some of the older technology, especially around security and encryption. So keep that in mind. Use the things that are already out there. And with that, I really appreciate everyone sticking with this course, and I hope you learned something from this. It was enjoyable for me to do this, and again, I really appreciate everyone's time. So look forward to speaking to you sometime in the future. Thank you.